Okay, good morning, afternoon, or evening, everyone. I think now we can start our workshop. So a very warm welcome to everyone to the International Workshop on Trustworthy Federated Learning, which is held in conjunction with the FL-IJCAI' 2022. Okay, so this is the first installment of the Trustworthy Federated Learning Workshop. And today we are going to carry out the online program. Due to the COVID situation, this time we split our workshop into an in-person program, which took place in the conference, as well as an online program for our authors and attendees who cannot make the trip to Vienna. Okay. A brief recap of the field of federated learning. As you may know, it has been a rapidly growing area of research in machine learning. It still has a very long trajectory of rising as well as maturing. For the workshop this year, we have received a total of 36 submissions. All of them have very good quality. Unfortunately, we still have to be selective about this. So in the end, we accepted 25 papers. You can see the breakdown of participation from different countries. And this year, we have a lot more diverse authors from diverse countries to join our workshop, which is very heartwarming. And for today's online program, we have a lineup of 5 very exciting invited talks given by leading experts in the field, including Professor Qiang Yang, Dr. Yongnan Ji from NVIDIA, Zuping Wu from China Telecom, Victoria Wang from IEEE Standard Association, as well as Martin Jaggi from EPFL Switzerland. And here we would like to acknowledge the effort put in place by our wonderful program committee to help us select the works to be accepted and shared with the participants of our workshop. Thank you very much. As well as the organizing committee led by Professor Yang, as usual, who has put in a lot of effort together with the rest of the committee to ensure that the split format of the online-offline workshop is going to be carried out smoothly. And last but not least, we also want to thank our sponsor, FedML, which is a company that provides end-to-end machine learning operating systems to support the formation of federated learning ecosystems. I think recently they just got an investment in the amount of tens of millions. So congratulations to FedML and thank you very much. Okay, so without further ado, I would declare this workshop opens. So let me now invite our first distinguished keynote speech from Professor Qiang Yang. I think Professor Yang needs no introduction. He's a very well-known expert in the field. I think now I would give the control to Professor Yang to give his keynote speech on the topic of trustworthy federated learning.
Thank you, Professor Yuhan. So let me start my presentation.
Hello, everybody. Very happy to be in this workshop. My title today is Recent Advances in Trustworthy Federated Learning. Let's first look at a few application cases. Suppose we have several banks, and there are new applications to bank loans. As they come down from the bottom, a new user, this bank in the middle, is looking at the application and wishes to know whether this is a fraud case. One of the fraud cases happens when we have the applicant applying loans from multiple banks. Therefore, they can pay off on bank with a loan from another bank, and this creates a very high risk. So to prevent against this case, the bank in the middle wishes to verify with other banks whether this new user has applied for loans from their banks. However, the data at other banks cannot be sent to the bank in the middle because of user privacy and security. So how can this be done? How can the bank in the middle know whether the new user has applied for bank loans elsewhere without actually seeing the application data at other banks? So this is an anti-fraud case, which supports federated learning. With federated learning, we wish to support this application by not transferring any data outside of each bank. and yet being able to answer queries like this. A second case is when a bank wishes to build a richer model of a user. For example, the model will not only use a user's financial history, but also other applications, such as tax payment, social network behavior, and e-commerce. But again, we face the problem. Each of these organizations on the right will not send any of its raw data to this bank. Yet the bank which knows the credit history will not know the necessary behavior information of the user at other places. So how do we enrich the user model? This is another question. So it reduces to we know the Y dimension, but we do not know the X dimension. The X dimension resides with other social media platforms. A similar situation happens when we wish to advertise to users. Say again, this is a bank which wishes to advertise only to a high potential user. So it's private. It's a personalized advertisement. But in order to advertise, the bank needs to know the user behavior information. And the social media platforms need to know the credit history of the user in order to know which ones are highly likely to respond to the advertisement. However, neither of them are permitted to transfer data to each other. How can this model be built, and yet the personalized advertisement be done to advertise to the user? And this is the third situation. The last one, which I used to motivate federated learning, happens in the medical domain where we have multiple hospitals. Here we have 2 hospitals. They each have their own data. And when a patient appears, we wish to use a global model to diagnose for the patient. The model should have the information from every one of these hospitals, not just this individual hospital. And yet we face the situation when we're not allowed to transfer data to each other. How do we build a global model without transferring data? This need is heightened by the recent media exposure of some high-profile cases where we have seen in the Western media cases on Facebook, Google, Microsoft, and others. And it's a high-stakes situation. This is a heightened case, partly because the government are tightening legal regulations. Like in Europe, the famous GDPR is requiring that all the personalized data usage has to get permission from the individual users before applications. And cases such as Cambridge Analytica is well known, and is already made into a documentary on Netflix. In China, the situation is likewise tightened. In the government regulation last year, there were 3 major data security laws, including the Personal Data Privacy Protection Regulation, Data Security Law, and Cyber Consortia Law, all of which requiring that corporations and organizations cannot transfer their data containing user private information elsewhere. That's from the technology perspective. We are interested in developing a new paradigm for artificial intelligence, particularly for model building involving multiple parties. So federated machine learning or federated learning in multiple, in short, refers to when multiple parties try to compute a global model and use the global model, and each party contributes some local data and information, and yet we do not wish any local data to travel outside its perimeter, and we do not allow other parties to successfully infer any local information or any model information that are sensitive. So we can see an example shown here. This example involves, raising a model is like raising a sheep. Traditional ways to bring the grass to where the sheep is, and the grass information containing the grass is leaked out. A new way, federated learning way, is to lead the sheep to where the grass is and protect the local information of each grass repository, data repository, and different ways to compute the global model have been developed, and the technologies are experiencing very rapid growth in recent years. The components of federated learning come from multiple disciplines, such as encryption, such as communication. So network communication, incentive building and economic mechanism design, an AI model and computation, and distributed machine learning. Okay, so the first version came out with what we call horizontal federated learning. And this is a situation where we have millions of Android phone users. These users, each phone has a lot of AI models operating in it, and they need to be updated frequently. The update will use local data. So for example, the typing model for a language model, which supports the next word computation in the Google typing software, or the face recognition software, they all require a constant update. But each phone holds local data that is highly sensitive. So the question is, how do we update the local model with so many phones, so many users' information? The horizontal federated learning method is to allow each local model to be computed, and the parameters of the local model is encrypted, and then the encrypted package is sent to a server, where the server computes a global model, without compromising the local encryption information without opening the package. And yet, the global model can be built and distributed to the local, and the local model will then use the distributed updated global model to update its local information, which completes a local update. Using this way, each local model can be constantly updated, and the local information is not leaked out, because every step is very careful in protecting the transmitted information. The horizontal federated learning protects information with the consumer information. But when organizations work together, we call this business-to-business application. We have a complementing picture where we have multiple parties sharing a lot of data features and sharing user samples, but not a lot of data features. So this is known as vertical federated learning, because different organizations are collaborating by vertically concatenating their data tables virtually, not in reality. Again, we require that the local information is not leaked out, and the local model information is not leaked out as well. And by saying leak out, we do not allow other parties to successfully infer back any local information of any party. This is known as the vertical federated learning, and it's often used between banks and e-commerce companies, between hospitals, between government organizations that are business. Here's an example concerning multiple parties working together. So on the left, we have data stores from party 1 and 2, and they can each exchange some local parameter information and allow both parties to grow its own model tree while protecting the information of the local tree from the other party. And yet a global tree can be built. The global tree is completed when we have the local information put together. So when inference time, when a new user arrives at party 2 can ask a question about party 1 by encrypting the user's information and send it to party 1. And when receiving that information, party 2 can continue its local computation and can produce inferred results, such as credit information or user diagnosis information in hospital cases. On the right-hand side, we see a tree, a building process for two consumer applications. So let's say we have multiple edge devices such as phones, all of which holds a local tree. And putting them together, we have a global forest, which can be updated using horizontal federated learning. Earlier I said, federated learning is a multidisciplinary research. And there are many works in the economic theory and multi-agent theory on how to incentivize different parties to join an ecosystem. Here we see only one data owner will decide to join a federated learning global model if it's worthwhile. It's worthwhile when the benefit it receives is bigger than its cost. So therefore it can earn something, and what it earns is bigger than joining other ecosystems. One thing about federated learning building is, it's very important to define a security standard, so everybody follows this standard. If we don't have a standard, but we want to build a security system, a secure multi-party system, it's like drilling a hole in a mountain, which is very secure. People can find it very hard to attack, but maybe in 100 years we can build just one house. If you want to build something in scale, we have to use parts that are mass-produced and standardized. And by putting these parts together, it's like building a city and building a building. We had to follow some standard code regulation, and these codes are called Federated Learning Security Standards. Right now in international level and national level, we are building these standards. So federated learning has in recent years grown to be a very large community. Probably 4 years ago, there were 12 papers each year worldwide, and now there are several thousand papers. So this was a workshop organized by Google, which you can see there are many authors from all different areas joining together in building federated learning ecosystem. So here are some application examples. Even though federated learning is only a few years old, there are many large systems already in operation. The first one is in a credit system in the bank. Credit system used to be built by people, and they are very carefully crafted and very simple, maybe a decision tree model. But today with digital economy, we have data from multiple sources and all contributing to a global model. And this is the case when we have an ecosystem involving internet company, other fintech company data services, other banks, money lenders, e-commerce companies, and maybe government agencies, all contributing their data and models. And if you want to build a credit rating system to evaluate the security risk of a user, we have to use as many of these data sources as possible. And today, using federated learning, these parties can join the ecosystem without worrying that their data will be leaked out. And on the right-hand side, we can see the blue line, which is with more data. The capability of the system increases in very fast rate. And we bank right now supports online services for 300 million users, 7 days a week, 24 hours a day. And 98% of the applications are supported by automated system like the FL-IJCAI system. With computer vision, a multiple construction sites can enjoy a better global model. A security camera application for ensuring the construction site safety, such as detecting fire, detecting smoking, detecting workers for lack of security helmet. And so the system is put to use in Shenzhen city. In e-commerce and advertisement application, a very widespread application is a user recommendation systems, which can enjoy multiple data sources to support very accurate, personalized recommendations of products. And today, many of these data sources do not reach their data to be transferred out. So federated recommendation system is very useful and popular. One application of federated recommendation system is personalized news recommendation based on mobile phone. This is a real application in China for a paid financial news application based on phone application, where we can see with more data sources involved, the page view reading time and the click-through data all increase, which make the system more profitable and more useful, and users are happier with user experience. So beyond financial news recommendation, we also have medical applications. And here we have an application case with Tencent and several hospitals in Hubei province, where their local health checkup data are joined together. And the global model is used to diagnose the stroke early detection of stroke cases. And the cross-validation reveals that the improvement is great, to the point that the system is actually used for early screening of stroke patients. Some people are studying from academic perspective, whether when multiple parties work together, some parameter sharing between multiple parties can leak out some model information, which can further jeopardize the security of the local data. This indeed can happen when we don't protect the parameters shared between multiple parties, like on the right-hand side. And the left-hand side shows that, with 0 character in a character recognition or OCR application, just by multiple influences on the parameter data, you can recover the local data from the other party. So different security methods are designed to prevent this from happening in federated learning. There are other cases which can further jeopardize the local information, such as using the generative adversarial networks, using other backdoor security information. And now there's a huge amount of academia and industry methods against these cases. One of the cases we design is against the Byzantine attacks, which are designed to by pretending to be a normal user. Their purpose is to destroy the model performance. We have designed several effective ways to detect and filter out these Byzantine users. And one of the methods we designed is using graph-based deep learning, which can find out the collaborative conspiracy users working as a clique, and they can be effectively ruled out. Earlier, I mentioned that building standards are important, and here are several examples of international and national standards. The first international standard was laid by us, and it was published with IEEE in March 2021 last year. And this was the first international standard on defining the basic structure for the federated learning system working together. And there are many worldwide famous companies joining it. Today, there are many standards within the financial industry, within the telecommunications industry, within different international and national standard organizations. As important as the standard, it is also important to have open source software to lower the entering barrier for application users. And we are the first to publish international well-known open source software called Fate. And Fate was donated to Linux Foundation. It is now used by more than 800 different enterprises. And there are many different societies and users contributing to the growth of the Fate system. Now Fate is the de facto international standard open source software used in both academia and industry. Now just building the model itself is not enough, because we have to support the whole life cycle of federated learning. Recently, we defined the term trustworthy federated learning, which involves not just in secure model building, but also in designing a system to protect the IP right of models. Our method is to embed the watermark within the model, so that the model parameters have the fingerprint of the owners. This is done especially for the deep neural networks where we can embed it. It's very hard to detect and very hard to remove, so that when multiple parties work together, we can use this to detect the adversaries and the free riders. So we designed a way to embed the private watermarks without hurting the performance, without reducing the performance of the original model. And we have a very easy way to detect where the model comes from and who has been owning the model if it has transferred different hands. Federated learning has become an international phenomenon, to the point that the Gartner has recently added it to the hype cycle of a Gartner curve. This curve shows which technology is being considered a rising star, and we can see federated learning is among them. Okay, so my talk stops here. Just to summarize, we know with the growth of AI, data has become a problem, a challenge, particularly because we want to use data from multiple sources, and yet we have to protect data privacy and security. Federated learning is a way to solve this challenge by allowing different parties to work together without transferring out local data. And we have introduced horizontal, vertical, and other styles of federated learning. And likewise, I have introduced ecosystem standard, IP protection, and incentive mechanism, and different applications in areas. I wish to invite everybody to join the ecosystem to contribute to federated learning, which is a new paradigm for distributed artificial intelligence. Thank you very much.
Okay, thank you very much, Professor Yang. Sorry for the interruption just now. I have been warned that by putting the Zoom link online, there could be some disruptors who try to come into our session and play sound. So I'm still monitoring. Whenever someone unmutes themselves and play sound, I just remove them and report to Zoom. Okay, so Professor Yang has given, as usual, a very inspiring talk. So are there any questions from the audience? If there are, please either type them in the chat, or you can unmute yourself or raise your hand and ask the question. Anyone? Anyone from the audience? So Professor Yang, I know you have done a lot of work working with the industry about deploying federated learning-based systems. So in your experience, what do you think is the most important factor those companies value when they want to build trust with a federated learning-based solution?
Okay, yeah, that's very important. First of all, there has to be a common standard everybody agrees to. Without the standard to safeguard the safety and usability of a federated learning system, everybody will talk in their own languages. So in order to build a global ecosystem, having different parties joining it we must ensure that there's a common standard. Secondly, there has to be a highly efficient and highly effective way to build models and share models. Efficiency is as important as security. And in order to achieve this, we not only have to have different encryption tools, but also have a mechanism to properly balance security, efficiency, and effectiveness in a trustworthy way, so that our system will reach a point so that the attackers and potential semi-honest users do not dare to execute their attacks, and to ensure our system to be as efficient as possible. Finally, we wish to build more use cases in order to show people how federated learning is actually taking place in the real world. And in order to do this, we must ensure that the federated learning system can explain its inferences, decisions to the users, to different users. So interpretability and explainability are important, as well as life cycle mechanism for ensuring that the whole life cycle of federated learning is properly managed, such as the IP right of models and different interaction and auditing mechanisms as well.
Yeah. Thank you, Professor Yang. Any other questions from the audience?
Hello, can I ask a question?
Sure.
Please.
Firstly, thank you, Professor Yang, for the great talk. So I'm Shibing from the Huawei Research Lab in Munich. So my question is, there's still a lot of engineering challenge in the federated learning. For instance, how we do the hyperparameter settings and how we do the feature selection and do the model design. And in this phase, we also need kind of exchange a lot of information between the parties. So it's like a very efficient and secure and privacy-preserving way to do that part of the federated learning. I think it's also very important for the industry application.
Agree with you. Yeah, that you bring up a very important point, which is the engineering usability, utility of the entire federated learning life cycle is very important. We not only have to ensure security, but also we have to ensure that the system is highly usable and easy to debug and so on. So I have several experience cases to share with you. One is that we firmly believe that open source is a good way to achieve the best balance in security and efficiency, because open source allows the whole community to come in and debug and find out security holes, as well as different communities such as the vertical business areas like medical and finance. They can develop their own vertical applications, which can use more domain-dependent knowledge to ensure that usability is maximized. And finally, we must have, as I said before, we must have a common standard in federated learning to ensure that people are talking about the same concept as they move forward. Yeah, thanks again for the question.
Thank you, Professor Yang.
Thank you.
Any other questions from the audience? So you mentioned about the auditing,
Yes.
which I guess the regulators would be very interested in. Currently, I think for auditing purposes, both the auditors as well as the model owners, intellectual properties, they need to be protected. For the auditor's perspective, they would not want their auditing test cases to be known by the auditees. And from the model owner's perspective, they would not want to make a copy of their model and give it to the auditors without any protection.
Okay.
So, is there any thoughts from you on how we can go ahead to make this work?
Yeah, I think auditing is on one hand is very important for ensuring everything is legal and properly treated, such as ownership is respected, and even in model training, we wish to know who contributed what in order to fairly share the benefit of federated learning applications. So therefore, auditing is very important. Secondly, we already have several tools to ensure to execute auditing, such as using blockchain. Blockchain is a very ideal tool, but unfortunately, there are several problems with it. One is efficiency. Another is not every stage in federated learning system, either model training or model application, are entirely within the realm of blockchain. So for example, when you train a model, the model is being built, and therefore it's not on the train in order to, not on the blockchain yet. And yet we want to embed some ownership information to know the IP right. Secondly, when we have multiple parties building a global model, we wish to record who contributed what data. And one, at inference time, we wish to know whether that part of the model is taking the most effect. And therefore, we can later on fairly distribute the revenues back to the contributors. And we wish to know which parties are free riders in order to rule them out from receiving such benefits. So all of these can now be done not just by blockchain, but also the watermarks. So we have with Dr. Li Xinfan leading the effort, we have worked out a way to embed secret watermarks into a deep learning federated learning system, so that the watermark from different contributing parties will stay in a lifetime in the global model and can be very easily traced.
It's a very, very useful technology. Any final question for Professor Yang? I think there's a question from the chat.
Can you hear me?
Oh, yeah, Professor 14. Yeah. Sure.
Yes, sorry, it took me a while to figure out how to unmute myself here.
Okay, hi boy.
So yeah, very interesting. So I wonder, there's this whole idea of crowdsourcing and everybody being in charge of their own data, personal data, and somehow we're getting a benefit when that gets contributed to a model. Do you think that we can develop the federated learning into a sort of ecosystem where there could be 1 billion people that participate and that contribute their personal medical data, for example?
Yeah, that would be one of the ultimate goals. In, for example, horizontal federated learning, we can foresee a future world in which our phone is our virtual doctor. Therefore, our phone or personal device will hold a lot of medical information. Such a thing is getting more and more true with the development of medical IoT devices. The next question is how do we pull this data together into a global system so that it becomes more and more accurate by making use of all the edge devices. And so the immediate issue is how to build a scalable, highly efficient horizontal federated learning system. Secondly, how to find out who contributed what, so we can give more benefits to those who contributed useful data. Thirdly, we have to have a way to figure out the semi-honest or completely malicious users who are there to make trouble and bring down the system. So recently we've been working on a system to automatically adapt in the face of Byzantine users who work in collusion, work as a clique in order to cheat the system. We have seen such systems, such problems being getting serious in, for example, paper review systems in large conferences. And we hope to test it there, and as well as medical systems. Yes.
Very good. Thank you.
Thank you.
Okay, thank you, Professor Yang. I think due to the time limitations, although we still have a lot of questions for you, but we will need to let you go here. Thank you very much, Professor Yang, for joining us.
Thank you, Professor Han and everybody. Thank you.
Yeah, thank you. So next, we will welcome our second invited speaker, Dr. Yongnan Ji from NVIDIA. So Dr. Ji is the NVIDIA Healthcare Ecosystem Manager in China, supporting NVIDIA Healthcare Ecosystem with their latest technology. As an expert in medical imaging and artificial intelligence, he has published core patents and academic papers covering areas like medical imaging, image analysis, and image AI. So Dr. Ji graduated from the University of Nottingham in the UK. He previously worked at GE Healthcare, Toshiba Medical, and Samsung Advanced Research Institute. Okay, Dr. Ji, I see that your talk is already up, so please proceed. Thank you.
Thank you. Thank you very much for the introduction, and it's a great pleasure to be here and presenting NVIDIA's work in federated learning. And I'm in NVIDIA's healthcare team, and my role is to helping the developers and the customers in healthcare industry to use NVIDIA's technology and to build their own products and solutions. And I think every of us that here should know that the recipe of AI, like models, computational powers, and data. And NVIDIA is a platform company. Many of us that already know that about the computational power, but NVIDIA is also providing and making effective tools to help developers to build their own AI applications. And we all know that data is a probably one of the hardest part of the AI. And especially for AI developing, that we not only care about the amount of data, but we also care about the quality, the labeling, and the quality of the data. And in many cases, it decide how the AI is effective and generalizable. And but data label is also covers a lot of diversity, especially in healthcare. And as Professor Yang just said, it could be from your iPhone, it could be from the hospital, from the images, it could be from the blood test and everything. And the key issue in healthcare is that the data privacy is also very sensitive, even without AI, without in the beginning that we all know that the patient doctor privilege, which means that the information during the healthcare process should not be leaked to any third party. And when talking about AI and how to bring AI into clinical, and we checked from the publications on how people doing experiment design with the AI. And we check from the few perspectives first, whether the study was externally validated or is only internally validated, whether the topic, the diagnostic design is cohort or it's a case controlled, whether it's from the one institution or from multiple institutions, because all of these requirements is actually required when you bring AI into practical applications. So for now, we have a lot of frameworks, we have a lot of open source codes, and we have also public data. It's not difficult to build AI prototyping for many kind of research purpose or prototype purpose, but to bring into the clinical, these kind of concerns, these kind of standard are required to put and continuously required to in clinical applications. And we found only 6% of them, like published AI studies, have external validated. And so how we bring this kind of AI prototype into clinical applications, one of the way is to use federated learning to bring up the collaboration between institutions and bring this kind of inter-hospital collaborations to build one models that could be generalized into different sites. So federated learning, as well, many of us knows that it can addressing the problem of data diversity and privacy with either horizontal or vertical federated learning model, and the models can be trained locally and but bring up into a global model and can update it and regularly, and so that to make the AI closer to the clinical applications, the standard. So what NVIDIA did is using federated learning, try to bring the AI closer from the concept closer to practical applications. And here we can see some trends in federated learning in medical imagings. For example, these are the kind of studies NVIDIA lead or participated that applying federated learning in healthcare research. It not only involves medical imaging, but also involves other like genomics and pharmaceutical. For example, the first one is from National Cancer Institute for Early Detection Research Network. We're collaborating and to use federated learning to find the signs of pancreatic cancer, which is quite deadly because most of them are found in their late age. But whether we can build a model that could find early indicators and found and discovered and diagnosis in the still curable stage. And in the Erasmus, and the researchers using the NVIDIA FL-IJCAI' framework for applications in genomic analysis. So it identified the genetic variants associated with the schizophrenia cases. And during the pandemic of COVID-19, NVIDIA worked with 20 different hospitals and institutions across 8 countries and tried to build this model to predict the oxygen requirement for the patients with the EMR data and also with the image data, and published in medicine, Nature Medicine. And the University of Minnesota is also developing their models with NVIDIA FL-IJCAI' for federated learning, and they try to diagnose COVID-19 with X-ray. And the Melody is a global drug discovery consortium based in UK. They demonstrated that using federated learning that they could share the same models and build the world's largest collaborative drug compound datasets for AI training without sacrificing the data privacy. So in pharmaceutical discovery, the drug compound dataset is very privacy, and of course it's also because it's also very beneficial. So when NVIDIA addressed the problem of using federated learning tools, we consider from 3 perspectives. The first is accuracy. Of course, when using the federated learning, how to reach the accuracy, improve the accuracy, and increase the, of course, the generalizability is the first issue. And the second issue would be the privacy. The federated learning mechanism naturally improve the privacy, but there are also, as Professor Yang said, there are also other techniques that could increase the privacy in the training process and the using process. And the third topic is what we're thinking is about is after these researches, after these works, how to bring all these knowledges and all these best practices into a platform that could be available to all the developers and customers to help them that build easier to build their AI applications easier. So the first about accuracy. Okay, these are some of the publications media did in medical imaging area. In these researches, most of these researchers is trying to demonstrate that the accuracy built with federated learning is higher than any model that built locally. So this is for the foundation of the accuracy pursuit using federated learning. And I give two examples in this talk this time. And one is this federated learning for the predicting the clinical outcomes in patients for COVID-19. And COVID-19, especially at the beginning, one of the toughest issues is take a lot of healthcare resources, especially ICU beds and also oxygen. So if we could predict the expectation of a patients when they enter the hospital, it could help the clinicians to organize the resources required for each sites. So this research, NVIDIA collaborated with 20 sites across 8 countries and use chest X-ray and also blood tests, oxygen saturation, blood pressure, and respiration rate, this kind of EHR data, and together to build a model to predict whether the patient is okay with the room air or it needs nozzle air, or it needed to use the ventilators. So at that time, ventilator is very rare resources for many hospitals. So for these 20 sites, all of them has the federated learned model has the higher accuracy than the local model in all these sites. And it shows 16% of performance improvement and also 38% of the generalizability improvement. And another case is collaborating with NIH, with Upstate Medical University and UCLA Health. And this time using with the similar purpose, using MRI images to do the prostate segmentation, which is a very common procedure for MRI for prostate cancer diagnosis and also for MRI applications. And it also shows that the federated learned models outperform any of these local trained models. So after addressing the accuracy, the next question would be the privacy. Well, different studies shows that even intersect some weights for updating the models, we can still somehow accumulatively recover the data set. And so it may lead into the privacy leakage. So how the question would be, what kind of method we can use that to countermeasure this gradient inversion attacks? So for security, there are many approaches And we can consider as basically 2 layers. One of the layers is how to make connection security, and so that we can use the basic key this kind of encrypt, and also use the SSL to increase the security in the transmission. And another is the use of the mechanism of differential privacy and homomorphic encrypt to encrypt the content or the weights that we transfer during the federated learning. Then it come to the question is, after using these security measures, are we going to still have to reach the accuracy? So it may, yes, these kind of security measures may hurt a little bit on the accuracy, but with a proper handle, and we can still, as shows in this experiment, also in this it's a brass TS, it's kind of pretty well used, well studied data set. It can show that with the differential privacy algorithm, the accuracy still increase, and to the one that in the federated average or centralized methods. So the conclusions is that we can that keep the privacy and also keep the accuracy. So the next question is how to make these studies more accessible, and NVIDIA, and that's why NVIDIA developed NVIDIA FL-IJCAI'. We call it Federated Learning Runtime Environment. It's an open source SDK for federated learning, mostly for horizontal federated learning, because most of for example, medical imagings are like horizontal more than vertical. But of course, with more with a horizontal, it's more like we diagnose from the image, and with vertical, we might develop into other domains, for example, for the payers, for the insurance, and this kind of more a wider scope. But for FL-IJCAI', NVIDIA FL-IJCAI', mostly for horizontal federated learning, it is under Apache 2.0 license, and it enable different kind of mechanisms to help the developers to develop their models, and also welcome to contribute more models and also more methods into this framework. And another question is whether how long NVIDIA is going to planning for this work. NVIDIA FL-IJCAI' has quite a roadmap. It starts from solving the problem of medical imaging AI federated learning. So how to bring this medical imaging data into training of one model at the beginning of August 2021, and then in November, this framework is cleaned and also prepared as open source, and now it has for FL-IJCAI', it's not only for medical imaging, and it can also be used for natural language processing, and also data analysis, and many other genomic analysis, as illustrated before, and for healthcare and beyond. And we continually to add more confidential computing into this framework. So with one of the question that we topic is how to monitor this learning process and auditing. And so we in FL-IJCAI', it has a management and a monitoring tools to show how this training process is. And on the base are the runtime and extensible APIs. And on top of that is, besides this privacy preserving and workflow, we have also, as I said, this monitoring tools. And on the top of these, we can build a different kind of applications for healthcare and for others too. So NVIDIA actually has two federated learning frameworks. So one is NVIDIA FL-IJCAI', one is also Clara media cloud train federated learning. So the basics are the same. So the open source part is NVIDIA Flare, and it only in charge of the communications, the weights updates, and the security. And on top of that, you can build a deep learning. You can build XGBoost and any like machine learning algorithms on top of this. But for cloud train, it is mostly for medical imaging. So it's more readily for medical imaging applications. Okay, by the end, and I would like to invite you to the video GTC that will be held in online on September from the 19th to 22nd, and there will be a talk on federated learning with FL-IJCAI'22, which is NVIDIA's leading a medical imaging open source project leading by NVIDIA, and also NVIDIA Flare. So you can learn from there how to build your medical imaging analysis with federated learning. So yeah, that's my talk. Thank you.
Thank you very much, Dr. Ji. So I guess for FL-IJCAI' and NVIDIA Flare, both of them are open source, so anyone can have access to it. Is that
yes? For FL-IJCAI', it's and also on Flare, all these are on GitHub. You can just search and find there. And FL-IJCAI' is for medical imaging, so it already has a lot of medical imaging tools in the like models, training workflow, and it also has some federated learning parts there. But for Flare, is for federated learning, and you can combine them to use for medical imaging, and you can use that separately too.
Wonderful. Are there any questions from the audience? You may wish to just speak up or type your questions in the chat.
So can I ask a question again?
Sure.
So thank you for the great talk. So I started NVIDIA has a different approach to protect privacy of federated learning system with homomorphic encryption, differential privacy, maybe in the future also the secure enclave. And could you please give like some comments on the security and privacy preserving capability of different approach? Thank you.
Well, I think I'm not the perfect one to answer these questions. I believe in this room that there are many experts knows more about this to me, and from my understanding, well, it's different mechanisms, and sometimes how to use them are in different applications is kind of more of interest to discuss. In my opinion, I don't believe like which tools could solve all these problems. It's more like in which kind of applications, what kind of tools we choose. For example, the homomorphic encryption is more like keep the data out of the server, so which means the server is not trustworthy. And the differential privacy has more convenience that we're leveraging on that. And probably in future that we have other like encryption technologies, and we may also add like a blockchain to this. So how to use these tools? It's mostly depends on what kind of federated learning mechanism what we're dealing with, or we are going to design, what kind of system we're going to design. And to promote the federated learning, the development of federated learning, and so to make it applicable into all these kind of scenarios, all kind of industries and all kinds of applications. These kind of tools, I would say the more the merrier. And so we can offer so that we can have more, more in our toolbox to deal with different kind of situation.
Thank you.
Okay, thank you, Dr. Ji. Any final questions from the audience?
Hello, Dr. Ji. May I ask one question?
Yeah,
As
sure.
I know, hospitals along the world are volunteered to join the FL ecosystem to build a global model. So how do you persuade them? For example, you can, after join the federal learning, you can improve the accuracies and improving the performance and so on. Or do you consider all the failures among them?
Sorry, what was your last line?
About the failures.
About sorry again. About what?
Fairness.
Fairness.
Yeah.
Well, that's a big issue. Actually, Professor Yang talked about a lot of fairness. And in my understanding, in healthcare, when people think about federated learning, fairness is not the first thinking of the issue. Mostly it's still about what we can get out from this federated learning. Because of fairness, fairness in general is not somehow a technical issue, at least from my understanding in healthcare. We can provide some tools to observe from some perspective, like we measure from the number of data, we measure from the weights updates, we measure from how much of the contribution of models. But this is only part of the fairness of collaboration. So IP is definitely one of this, but how to measure the IP, especially in this collaboration. I think we provide technically we provide index, and in this collaboration, the collaborators, they should settle more about okay, how to deal with this issue. And in healthcare, one of the topic other than whether valid and usability and fairness, another is when we're talking about auditing, is what's come into my mind about this word. It's more like the validity of this auditing. So whether your data is good enough, or in this federated learning, this kind of auditing, and to make the auditing of how to make this model valid. So that's more of how people think in healthcare in federal learning, I believe. Thank you.
Okay, thank you.
Thanks.
Yeah, thanks. I guess if it comes to auditing, we can also audit whether there's any bias in the model produced by federated learning, somehow related to how fair the model is to different group of people. Okay, so thank you again, Dr. Ji, for giving us a wonderful talk in our workshop. Okay, thank you very much. Okay, for our next invited talk, we have Zuping Wu from China Telecom. So she is from the China Telecom Research Institute, and her research focuses on federated machine learning, AI mobile device, and NR communication. She has been involved in developing several AI standards in IEEE and followed up the related issues in 3 GPP Standard Association. She's also the chair of the IEEE SPFML working group, as well as the IEEE CAISC FTFML. Okay, let me now welcome Zuping Wu. I see your presentation is already up. Please start when you are ready. Thank you. Sorry, you are still muted. Hi, Zuping, you are still muted.
Yes. What about now?
Okay.
What about now?
Now it's okay.
Yeah. Thank you. Yes, it's a great honor to be invited here. And my name is Zuping Wu from China Telecom. And today I will talk about the practice in privacy and security of federated learning from China Telecom. In fact, there are 3 parts in my talk this day, and I will go through the first and the second part very briefly and very quickly, because I believe all of you have worked hard in federated learning for many years, and maybe all of you are very familiar with this content. And as a time when artificial intelligence is becoming more and more popular, AI privacy and security is also attracting huge attention worldwide. At present, more than 100 countries and regions have enacted laws and regulations on data privacy and security. And as one of the key technology in privacy and security, federated learning is first proposed by Google in 2006, based on the distributed data sets. Federated learning is enable the participant clients to collectively learn a shared model and a shared model while keeping all the training data on the device, which can decoupling the model training from the need to access the raw training data. And for simplicity, we can see the workflow of the FML framework in this figure. And typically there are 4 steps. The step 1 is the algorithm download from the server to the client. And the client use this model M to do the model training. And next, the training results can be feedback to the server. And the server will aggregate all them and construct and improve a global model. And now federated learning have extended a wide spread of use case. And there are typically 3 categories. The first one is horizontal federated learning, whereas the data set share the same feature space, but differ in the sample. And the second is the vertical federated learning, that 2 data sets share the same sample ID space, but differ in the feature space. The last one is the federated transfer learning, where 2 data sets differ not only in the sample space, but also in the feature space. As mentioned by Professor Yang, federated learning is now in the Gartner maturity curve. And so we can see that it's one of the key technology to develop for the next generation of the privacy and security. And using federated learning, we can achieve the data isolation, because there is no leakage to the outside. The data can maintain in the federation. And the second is the model needs to be updated after training. So the model is better than the independent fragmented model. And the third one is that maybe using federated learning, the state of the participant can be equal, and maybe we can get the fair cooperation. The last is about all parties involved can maintain their independence, because they only exchange the encrypted information and other model parameters. But there are still many challenges to be solved these days. For example, the communication efficiency, or the privacy and security trade-off, or the lack of trust and incentive mechanism. So there are many people work hard in this federated learning, and many progress have been made. So I will talk about some progress in federated learning. For example, in 2022, no free lunch theorem for security and utility in federated learning is proposed. Is essentially dedicated that one have to trade the decrease of the privacy leakage with a certain degree of increase of the utility loss. In other words, if an algorithm performs well, then it has to pay for it with a degraded performance. But a balance can be achieved. And the second progress is about the trustee and incentive mechanism using blockchain technology. In fact, the incentive characteristic of the blockchain help to solve the pain point problem of the federated machine learning. There are many architecture based on the blockchain technology federated learning. The first one we can see from the left side, the block FL architecture. In this architecture, they can overcome the single point of failure problem, and they can extend the range to the untrusted devices, because the validation process of the blockchain And moreover, by providing some proportional to the training sample, they can get a reward. So the block FL architecture helped to promote the federated machine learning with a larger number of samples. And the second architecture is the blockchain-based FL system. In this system, the blockchain share the same peer node with the federated machine learning nodes. And the last one is about it use the MEC server. When using MEC server, they are responsible for the mining process. In fact, the client here can take part in the mining process or the federated process or both. Through the mining process, the local updates of all mobile devices can aggregated and store in the block of the chain. And the devices can download them and generate the block to compute the global model locally. And at present, federated learning is not only studied in the industry, but also in the academia. And a number of standards are related in the IEEE, for some are published or some are just underdeveloped. For example, the IEEE 2.1 is the architectural framework and application of federated machine learning. In fact, it's the first standard about the FML. And the IEEE 2.986 is about the recommended practice for privacy and security for federated machine learning. It's about the recommended practice, including the privacy and security requirements for the participant, for the system, the model, or some methods. The IEEE 3.127 is the guide for an architectural framework for blockchain-based federated machine learning. It can provide the guidance to improve the security, the auditability, and the traceability of blockchain-based federated machine learning. And the last is about the IEEE 3.187 is about the guide for framework for trustworthy federated machine learning. Is a new project in 2022, and I will discuss it in more detail in the later. Yes, and so we at China Telecom as one of the operator in worldwide, we have many efforts in federated machine learning too for many years. So I will show you some practical usage of our practice in federated machine learning in this part. And the first is about some standard. It's very great to see that we have dominant some IEEE standard. And the first one is IEEE 2.986. It's about the privacy and security of federated machine learning. We discussed the common failure in federated machine learning, including the adversarial attack, the non-malicious failure, the adversarial failure, etc. And the second is talk about the privacy and security requirements both for the model, for the participants. And the third part of our standard is about the defense method and fault recovery method. And the last part is about the privacy and security evaluation. And we can see from the right side, right figure, that it is about the evaluation workflow of our privacy and security. The evaluation contains 3 steps. The step 1 is identification, then the analysis, then we can evaluate the risks. In fact, the participants, the behavior and the motivation will be input as an input in the identification part. And after the identification, we can get the identified risk. This risk is put into the analyze part steps, and we can get the analyze risk. And we can get into the evaluation, we can guess how the risk level, about the risk level of the model. So, this is the whole workflow of our evaluation parts. In fact, we hope to provide a unified standard using this project, and about no matter what kind of industry you are in, and what kind of attack you are facing, and what kind of protect algorithm you are using, we can get a unified standard level about risk level, about the privacy risk, and the security level. So now there are more than 21 companies and researchers and institutes have worked hard in this standard, and we hope to finish the group study about IEEE P2986 this year. And the second IEEE standard is about the IEEE P3187. It's about the framework for trustworthy federated machine learning. It is a standard about the new stage of federated learning that is trustworthy. We need to come to the trustworthy stage. So we propose it to the IEEE standard and get an approval in June 2022 this year. In this project, we focus on three main aspects. The first one is the principle in trustworthy federated machine learning. And the second part is the requirement for different user roles. The third part is the method to realize this trustworthy federated machine learning. In fact, the first scope contains 5 characteristics. That is the verifiable privacy and security, and the controllable complexity, the optimal model utility, and the auditable process, and the explainable results. And in fact, the verifiable privacy and security means the privacy disclosure and security risk can be quantified and evaluated when using the model, when using the FML model. The user would know to what extent their privacy would disclose and the level of their privacy disclosure. In this way, we can help participants to trust our FML model. About controllable complexity, it means the overhead of the privacy preserving algorithm in computing we use is controllable. It needs to be computational and communicational efficiency. And the third is about the optimal model utility. In fact, the more optimal model utility is a trade-off, because we can get the model utility under the acceptable privacy risks and controllable computational complexity. So it's a trade-off among the privacy and security, the performance and utility. Yeah. And the fourth part is about the auditable process. It means it's regulatory and it can be traced back. It's traceability. And the fifth part is the explainability. That's the model we use in FML or the result of the FML need to be explained. It can be explained, and the whole FML process can be explained. And then we will study about the requirement for different user roles, including the data owner, the model user, the coordinator, and the auditor. Also, we will study about the technical method suggestion for each requirements. And now this standard is come to the call for participation stage. So everyone is welcome to this standard because it is an individual ballot standard. So everyone is welcome. If you are interested, you can contact me. Yes. And as a company, we need to make our creative idea into the practice. So we build a platform called 22 AI platform. It's a big data sharing based on privacy preserving techniques. We jointly built with China Telecom Research Institute and China Telecom Cloud Corporation. Our 22 AI platform includes two main models. The first one is service function model, and the second one is the computational model. In service function model, we have 6 parts. The first one is the partner management. The second part is data management. The third is permission management. The next is project management and task management and model management. In the service function model, you can manage the function of the participant. You can get access to the data. You can query and delete the data, or you can assign the project to one user, or also you can get the model training process here, model update, the model service launching in this model. And the next model is about the computational model. Our 22 AI platform supports the federated machine learning and security multi-party computation. In fact, the typical algorithm are supported here. The linear regression, the logical regression, or the tree algorithm, etc. As an state-owned enterprises, our FL-IJCAI platform is a self-developed commercial FML platform. We have 3 competitive characteristics. The first one is our FL-IJCAI platform is safe and reliable. We use our own edge ground system to ensure the data storage in security. We use the privacy computing technology to ensure the security of the data interaction process. And the second is our FL-IJCAI platform is a safe management system covering all data segregation process. We can integrate all kinds of data assets from the government, from the institution, the foundation, and others. And the third one is our FL-IJCAI platform is a mutual data application scheme with different scenarios. We can fulfill the customer requirement in the whole data life cycle. So I will show you the more detail about our FL-IJCAI platform, and because we have operated this platform for more than a year, we use it in many applications and many use cases. I will just pick 2 of them to show you. And the first application is we use FL-IJCAI platform to manage the customer lifetime in marketing and finance industry. In marketing, we can identify the customer we lost, for example, during the registration process, during the applying process, or the using process. We can pull them back when we've identified that they are high value customer. And about the dormant stock customer, we can cross marketing them. We can give them the wake up signal and improve their activity. In the financial risk control industry, we can use FL-IJCAI platform to identify the high risk fraudulent user, those users with poor repayment attention and low repayment ability. We can identify them and score them, and maybe we can consider whether we need to give them the loans. And those clients with loans, we can dynamically monitoring them. We can monitor their risk and maybe their repayment, etc. And the second application of our FL-IJCAI platform is we built a trusted data segregation center for government and enterprises data. We all know that China is now building their an ecology about the digital system, and so we built this trust data segregation center for government and for enterprises. And you can see that this is the architecture of our data segregation center based on our FL-IJCAI platform. We use, based on our intelligent edge ground system, we build 3 platforms in covering the data life cycle monitoring. The first one is data governance platform in the asset layer that we can get people can register here and confirm, verify their needs to get the data. And in data asset development platform, is in the transaction layer, that the data we get can process here, and we extract the feature, and we use this feature into the training, into the evaluation, then we get the data asset products. Then these products can be used in the data application market platform. This is a service layer that the data products here can be searched, can be consulted, or you can get solution or get access in this layer. In fact, this is a default product of our FL-IJCAI platform, and also the client can get our products itself, or they can, or we can help them build their own products based on their typical scenarios. And so I will show you the use case of these 2 applications. The first use case is the advertising precisely for high value stock customer. In this use case, the X company come to us and they want to identify the high value customer from their stock customer. Their stock customer maybe tens of millions. They want to utilize them. In fact, they have their own customer profile label, but the effect is not satisfying, and they do not want to interact with the external data. So we use our FL-IJCAI' platform. We use our feature proof from China Telecom, and we help them establish an efficient machine learning model. And we do not exchange the user raw data and label. And using our FL-IJCAI' platform, we help them improve the prediction accuracy because they want to predict their stock customer, their preference, and also we can reduce the cost of the finding new customer. After our FL-IJCAI' platform, and the average prediction accuracy is beyond 93.55%. You can see from the below chart that the proportion of the effective customer after using FL-IJCAI' platform can increase from 5% to 5%. And about the use case 2 is the promotion of bank financial customer. In this use case, the Y bank want to turn their deposit customer into their financial customer. So they need to labelize those high value customer, and they need to only reach those high value customer and not all the customer. So we for comparison, we use their own intrabank variation, and we use the intrabank variation plus China Telecom variation with same customer sample for comparison. And the high quality group label is developed use our China Telecom label, and we merge our submodel into their own model. And with our FL-IJCAI' platform, the app notify the top 10 user, and the change is recorded. And we can see from the chart that using our model with China Telecom label, the KS effect is improved, which means that our differential effect is higher. And you can see that the identification of high value customer is improved from 12% of the top 10 user to 30% of the top 1 user. And about the use case 3 is we build a data supermarket platform. In fact, the H province in China, some province in China want to build a provincial data supermarket trading platform and a public data utilization platform. In fact, now in China, we have no mechanism, no mutual mechanism about how to build a trading platform on the data. So, and it needs some professional institute to do the supervision through the whole process, from the purchase, from the trading or search, etc. So they came to us, and we help them build a supermarket platform based on our data circulation platform. Also, we also get them 3 platforms you can see from the picture. The first is data merging and storage platform, and the second is the public data utilization platform, and the third is the data asset operation and the application platform. And the data is stored in our TeleDB distributed data sets for the security, and we use some privacy computing technology and some decentralization technology and to operate these data assets, and we can give them some API service, etc. So when they build these supermarkets, their clients can search or purchase their products, or they can feedback what they need, and they can get the solution using the home pages. In fact, this whole process is auditable because we build a digital asset center which contains the supervision center. In fact, this platform now is applying in multiple industry in each province. For example, in tax administration industry, the social insurance, the tourism, the transportation, the finance, the operation, etc. And the last use case I want to show you is about the promotion of government data value. In this case, F is a data asset company. They want to promote their productization of their data operation service platform, and they want to expand their application scenarios. So we need to make sure that the data integrity and the data with high quality and the capitalization is traceability, and this system is easy to operate and maintain. So we introduce the federated machine learning and the blockchain technology in our FL-IJCAI' platform. The sensitive data, the value of the sensitive data is extracted and become a desensitive data, and then it can be used in the visual model platform, and we can complete all the whole model training process. The first use this platform in the national express data. We can gradually spread this to more application scenario. Now, more than 1 year's operation, our FL-IJCAI' platform have achieved a cross-industry implementation. Now we have more than 12 cooperative partner here. And yes, if you are interested in our FL-IJCAI' platform, or if you are interested in our P3187 standard, you are welcome to contact me. Yes, thank you.
Okay, thank you very much, Sufing, for the wonderful talk on China Telecom's venture into federated learning. Okay, so are there any questions from the audience? Please feel free to speak up or type your question in the chat. Okay, Sufing, I see you have a data trading platform.
Yes.
In there. So how does that work? Is the data being traded involving any private information?
Yes, and in fact, the data trading process is we build this platform based on our FL-IJCAI' platform. And then the sensitive data need to do some pre-processing. We need to extract some sensitive data outside and make them become the desensitive data. And we extract this feature in the platform, and we then the client can search what they need. And so it's really a good practice in the province in China, and now we are just pushing this platform more, and maybe to more industry in the few years. Yeah.
So in that case, whoever purchased the data would get a copy of the data set. Is that correct?
Yes.
Okay.
Yes. The client want to get some data from, if you are in an enterprises, you cannot get some data from about the governments, but using this platform, the client can purchase some government data without some sensitive data. Yes, using this platform. Yeah.
Yeah. That's interesting. We have some work. We have some work related to this, but what we are doing is that to use auction mechanism to match people together, so that whoever needs to have access to other parties' data, they form a federated learning group, so that they can train their model by leveraging other people's data without having to make a copy of their data.
Yeah, good practice. Maybe we can talk more in detail after this meeting. Yeah.
Yeah. Any other questions from the audience? Okay. So if there's no more questions from the audience, let me thank you again, Sufing, for giving us this wonderful invited talk. Thank you very much.
Thank you.
Okay. So now we move on to our first oral presentation session, chaired by Professor Guodong Wong from the University of Sydney, Australia. Professor Long, I see you're already online, so I pass the floor to you. Thank you.
Okay, thank you for Professor Yu to invite me to chair this session. And today's session will last for, I think it's 2 hours. We will have 8 papers to be presented, and each presentation include 10 minutes talk and with 5 minutes question and answering. If the audience have any question, you can type in your question in the chat area in real time, or you can keep your question after the presentation. Okay, and the first presentation is I think it's for an innovation award that is talking about the MetaFed, federated learning among federation with technical knowledge distillation for personalized healthcare. Yeah, so the president can share your screen if you have the slides.
But you are do not allow me to share the screen.
Oh,
you should change my role, you know.
Yeah, I just
Great.
give you a co-host, right, for the chat. Yeah. Are you able to share now?
Yeah, sure. Okay, thanks Godong and thanks Yuhan. So hello everyone. My name is Yiqiang Chen, come from Institute of Computing Technology, Chinese Academy of Sciences. And this paper is my student and also our collaborator, Jindong Wang and Xin Xie from Microsoft Research Asia. And our work is focused on the federated learning among federations with cyclic knowledge distillation for personalized healthcare. I will introduce it from 5 aspects: background, method, experiments, applications, and conclusion. This is the background. I think the previous three keynote speak also give the detail. I will be bypass this. Although we know there have many federated learning method, but no man now focus on the federated learning among federations. In real situations, clients are often grouped into multiple federations, and the learning among federations then is needed, just like the figure shows. But when learning among federations, there are 2 issues: personalization and the lack of servers. Different federations may have different distribution, and the federations often cooperate on an equal footing without a server. These 2 problems handle the development of federated learning. So to solve the above problems, we propose, we name the mental fate. That means the federated learning unfederated learning. We call this federated learning among federations. We use a method called cyclic knowledge distillation. We first using for personalized healthcare the theme. So as shown in the figure, the whole training process is split into 2 stages. In common knowledge accumulation stage, the federations are trained cyclically, and then the previous one served as a teacher for the next one. It lasts for several rounds to extract enough common knowledge. In personalized stage, it's trained sequentially, and the mode is sent to the next federations without local training to preserve the common knowledge. In the whole process, so lesson, you can see no server participates. To transmit the information among federations, we utilize featured knowledge distillation before the last layer, just as the figure says. We only in the final flow collection layer to do the knowledge distillation as the knowledge transfer. So the parameter lambda is a trade-off knowledge transfer and focusing on the current data while CLS is the cross entropy loss. So to achieve good models for each client, there are three key problems to solve. First is how to ensure enough common knowledge accumulation. So we can train enough circulated round or transmit enough teacher information or incorporate local information and so on. The second is to how to discard reduction information and obtain the personalized modes. And the third is how to determine inheritance or discard. That means we can, using the valid accuracy, can serve as the guidance. So I will give the detail. So in common knowledge accumulation stage, valid accuracy is used to determine how to preserve the previous federation's knowledge, while ACC valid I+1 beyond the LT1, the current federator had enough knowledge and we can discard unless information via knowledge distillation, while ACC validated I+1 less LT1, we directly initial the current mode with the teacher to make full use of the previous knowledge. To ensure enough common knowledge, we utilize a fixed lambda to incorporate the current knowledge. We transport the mode after local training. So in the personalized stage, valid ACCs are also utilized to determine how to deal with the knowledge. When the common mode performs terribly on the valid data, we refer later to it and set the lambda equal 0. When the common mode performance is acceptable, we adopt a dynamic lambda. The better common mode performance, the larger lambda is. And then I'd like to show some experiments on our method. We evaluate mental fit on 3 benchmark data sets, including time series and the image modalities. VLCS is about feature shift, while the others are healthcare related. We compared our method with 3 latest methods. Since these methods are all need a server, so we list this restriction for them. So all the methods use the same mode for fairness. So you can see the experiments. So you can see our method outperforms other methods on all benchmarks. You can see for feature shift, there are an improvement about 3.89%, and in the labels shift, there also will be some improvement respectively. So we also do some application studies as shown in the top figures. You can see both parts of our math works quite well. That means this the WI means without the first round, and the second is the fine turn, and the third is without the second accumulation round, and the last one is ours. You can see ours performance quite well. So for parameter sensitively, we change one parameter and fix another's. The results also reveals that the mental fit is more effective and robust. And then in realistic scenario application, communication cost is an important evaluation metric. As shown in the bottom, you can see in the bottom of our list figure, round and the local iteration, you can see when communication costs are limited, our method has stable results, while the fade average method drops seriously. We also implement our method in some realistic healthcare related problem, just like the COVID-19, which is the public benchmark. We first evaluated this for the posterior anterior chest radio graphic image dataset, our method can achieve the best performance with 4.07% improvement. And we also do some real world problems, like this is one. I mean the patient in the hospital and the outer hospital. This is the two federations. So these two data sets cannot be combined together for training one model. But in federations, in our method, we just to training one model based on the inner and the outer hospital data set to train this model. And we can, you can see that our method also achieves an improvement of 3.60%. So finally, I'd like to give some conclusions. In this paper, we propose a mental feed for federated learning among federations. Mental feeder can accumulate common law information and achieve personalized models for each federation through adapted knowledge distillation. So the key technology is cyclic knowledge distillation. In the future, I think mental feed is also extensible and can be applied in many healthcare applications. In the future, we plan to combine mental feed with common methods to implement a complete federated learning system. We also plan to extend mental feed for heterogeneous architecture and apply mental feed to more realistic healthcare applications. So thank you for listening, and any questions?
Hello, Professor Chen. I can see a question from the chat area. That is, what is the purpose of the common knowledge accumulation? Can we just skip this part and conduct personalization directly? Can you see the question and then give the response?
Yes, for the the common knowledge means that we want to using all the federations knowledge together. So if you only do the personalized stage, so just like the federated average means you have the 3-layer federated average. We compared our method. Our method is cyclic knowledge distillation, and we compared is federated average. That is what you said, only doing in the personalized stage.
Okay, so is there any other audience have any question? Can raise your hand, and I think our host can make you unmuted.
Hi, Professor Chen. Very interesting work. I'm just wondering, for now, the knowledge distillation is trying to adapt to different distributions, data distributions among different users. I'm wondering if it's going to be possible, if we can extend this to accommodate people with different device capabilities. Would that be?
Yeah, I just mentioned means in our future work. Yeah, in our future work, we wanted to extend our framework to heterogeneous architectures. Then it can be deal with the different device and also different distributions data.
Yeah, thank you.
Thank you.
Yeah, I just read that paper, and I have a question. Is about because the problem setting, you are assume there's multiple, I think multiple federation, or we usually think that is maybe one hospital or one company, and in each hospital you have multiple clients, and then these clients are separate to each other. So this is a bi-level structure. So does this the course clients and the course hospital, they have different privacy setting, or why have this kind of application settings?
I think this kind of settings is a real situation. You know, in China, the different hospitals will not to share their data or share their models. Even they only share their minimum data to their you know, their team hospital. So our assume is that one famous hospital maybe they have their own federated learning model, but they will not share this federated model to other famous hospitals. So this is the real situation. So we want these two federations can cooperate together. Just like, you know, now in China, China Telecom, WeBank, or a lot of, you know, companies, they provide a platform to provide their technique to help the hospital to build their own federated learning platform. So this also to be isolated.
Okay.
So we wanted to use this.
Yeah, but why?
Yeah,
but why the clients in that hospital is why use the federated model in that hospital? Because it sounds like
oh no, you know, not inside the hospital. When one hospital, you know, they want to train in their own model, they also using other hospitals' data sets they want.
Okay.
But I mean that model is also utilize a small data set from other hospitals. That hospital is that maybe they have a they have a same project to do.
Okay. Yeah. Thank you so much for the answer, and thank you for that great presentation. And now we are moving on the second presentation, that is about class-driven personalized federated learning for natural gas load forecasting. Yeah, I think is the first author will present that paper.
Thanks, Guodong, and thanks, Prof. Yang. This is Zhen Xiang from EN Group. It's my great honor to present a paper on personalized federated learning for natural gas load forecasting in FL-IJCAI'22. Before my presentation, may I give a quick introduction to EN Group. EN Group was started as an urban gas provider, but now we have covering the entirely clean energy industry chain. So we have branches in 250 cities in China. We're serving 25 million households in China and more than 200,000 companies. Besides the energy sector, we also expand our business to other sectors, including the real estate, tourism, culture, health for high quality life. So EN Group start our digital transformations journey since 2014, aiming at modern energy systems and quality life. Okay, sorry. Is the slides present well? Yeah.
Yes.
I think. Okay. So we have funded for our Internet of Things energy industry for energy industry, and ICON for health industry. That is aiming at our modern energy systems and the quality of life. And last year, we have transferred our headquarters to EW. We are targeting to build a industry intelligent ecological operations platform. So today our talk actually is based on the natural gas load forecasting that is relevant to our core business. So natural gas load forecasting is very, very important to build a modern energy systems. For example, the supply chain perspective, we are load forecasting is very important to best the resource correlation scheduling and also the pipeline network planning and operations. And to provide a high quality service to our customers, we have to provide demand management to ensure the safety management and enable them to do the proactive response to reduce the cost for the natural gas. As you can see, actually natural gas price is changed very, very dynamically, especially during the last few years. And however, no forecasting is very, very challenging, as large amounts of data are required to train the high performance deep learning models. However, some retainers, natural gas retainers, usually only serve a certain numbers of consumers within a region or even a very small city. So the data is usually insufficient for individual retainers to build a high performance model. And the other issue is that the retainers could not share the data to a centralized service provider to do the AI models. Due to that, they usually are committed to preserve the consumer's data. This is very important as it's very, and it is profitable to deduce the customer's operations and business confidential information from their energy usage patterns. Yeah, especially if you share their plannings and marketings to their competitors, is very, very dangerous and is also very harmful for our consumers. Luckily, we have federated learning. It can enable retainers as the participants to jointly train the global model without sharing their private data. However, according to our experiments, the vanilla federated learning model can perform even worse than solo models that is based on the individual consumers' data. This is because our consumers are quite diverse. They come from different corners of our country. The north part and the south part, they have different temperatures and climates. And also, they may come from different industry sectors. Yeah, so their no patterns will be totally different. So it means that our aggregate model, global model, could not perform well to all these diverse consumers due to their data heterogeneity issues. So to solve the personalized pattern learning is very popular way, popular methods or well research methods in the community to solve the problem of data heterogeneity. For time series data, according to our investigations, there are two main methods. First one is fine-tuning, and that means that we can pre-train the global model and then fine-tune it to our individual consumers. These have two disadvantages. First is the individual consumers' data is quite limited, so as a result, the model may be prone to be biased and overfitting. And the other issue is that if we maintain models for each consumers, then it will have a huge burden for our retainers to maintain and update these and monitor the performance of the models and update them accordingly. And the second part is doing the clusterings. It means that we will train a personalized model for each class of consumers with similar patterns. And this way, it also have some disadvantages because first, they can use the data within the consumers only. That means that they cannot fully explore the data in the whole ecosystems. Then another issue is that the performance may be not robust enough, or they are quite sensitive, the settings of numbers of customers. So actually they have two extremes. If there's only one cluster, that is the centralized, that is the vanilla federated learning. If they have the clusters, the same numbers of like consumer, that is equal to the solo model. So to take advantage of both these two methods, we propose class-driven personalized pattern learnings. So if we have made three main contributions. First, we, based on our domain knowledge to do the clusterings, that is categorize our similar customers according to different dimensions of variables into clusters in a privacy preserving way. And then we propose a two-phase federated learning. First phase is actually a vanilla federated learning. It can make use of all data from all the retainers. And then we have after that, we have fine-tuning phases, that is personalize the model to individuals clusters, also in a federated learning methods. And during the fine-tuning phase, we have proposed attention-based model aggregation to further improve the performance. For the knowledge-based clustering algorithms, actually we have decomposed the time series data in trends, seasonals, and residentials. So we treat these different parts separately. I also use the dynamic time wrapping similarity measures, which have advantages over the traditional calculated distance measurements. So as we can see in our data set, some of the customers have quite similar patterns. So if we use their data to train our models in a better manner, definitely we can improve the performance. And besides that, we have proposed federated k-means methods. It can clustering our consumers without seeing each other's data. That is also a privacy preserved way. So in each retainers, they can update their local cluster centrals by using k-means algorithms, and then they will upload their local centrals for the clustering server to do the aggregations, and this will be done iteratively. So it's quite similar to our federated learning steps. And after that, all the retainers know their customers are divided into different clusters. So they will use their corresponding consumers' data to train numbers of cluster models accordingly. And all the models have different performance the usages.
Maybe 1 minute left. Yeah, 1 minute. Sorry for interruption.
Yeah, thanks. Yeah. Thanks. For the two-phase federated learnings, we have, as I mentioned, first phase, we can leverage all available data. And the second phase, we personalize to each consumers. And then we have attention-based aggregation. We consider the contributions of individual consumers and then aggregate in a weighted manner. According to our experiments, as we can see, our proposed model can achieve optimal results. It can even outperform the centralized one, which is usually seen as the ceiling performance ceilings of federated learnings. And from the application perspectives, we have, as we can see, large numbers of consumers can improve their performance significantly. And also our proposed framework is less sensitive to the numbers of clusters. Yeah, for the summaries, our framework is the technologies developed in our framework is very beneficial for natural gas node forecasting and potential applications in the energy domains. For the future work, we will explore the graph neural network to mining the potential relationship between different clusters and consumers. And also we will investigate the self-supervised learnings to leverage the large numbers of time series data. Yeah, thanks for your attention.
Okay, so does any audience have other questions? Can raise your hand or type in the chat area. Okay, there's one question. If using cluster, the clients in one cluster cannot know the data from other clusters, how can address this situation?
Yeah, thanks for the questions. Actually, first of all, we have used two phases on this one. This is definitely the problem for traditional personalized federated learning using clustering only. Yeah, so to overcome this disadvantage, we have two phases. First phase, we have tried to build a pre-trained model. It takes advantage of all the data and then do the fine-tunings for individual clusters. So we can use the other data in this way and make our models more robust. Yes, Then the second way, actually, we are now doing try to use graph computing to explore to mining the relationship between different clusters. Then we can also leverage the data from other clusters.
May I ask a question, because that is quite interesting work. So that data set is able to public share, or maybe shared for the research community or some kind of way?
Oh, you mean the data set, isn't it?
Yes.
Yeah, we do have planning to share our data sets. Actually, as you know, Young Group have different we are also building some test bed. We are inviting collaborations to do the researches based on our federal learning test beds, and we also have some planning to release some of our data sets.
Okay, maybe you can talk to Henry about competition, host that competition on your data sets. That will be interesting.
we are working together for some time already.
There's one more question from the audience. For the clustering result, will the newly generated data change the clustering results?
Oh, that's a good question. Actually, in our pilot systems, we will update our models regularly. Yeah. So we have a newly generated data. Then based on that, we have some standard to update. We don't change the clusterings quite frequently. So we have set some thresholds for simple understanding. Yeah. But we do our pilot systems update our models and train our federated learning models regularly.
Okay, great. Yeah, due to the time issue, and thank you for your presentation, and congratulations again for your papers received the Innovation Award.
Thanks, Gordon, and thanks again.
Okay, let's move to the third paper, and that is about further assistant dialogue agents with two-side modeling. Can the presenter to share the screen? Yeah. Cool.
Can you see my screen?
Yes.
Yeah, I will go on. Thank you, Gordon. Good afternoon, everyone. I'm Haoran. Today, I would like to introduce our recent work, Federal Assistant Dialogue Agents with Two-Side Modeling. First of all, I would like to talk about some background about dialogue system. You can also call them as chatbots. They can be used for chit-chats and task-oriented purposes. And for chit-chat chatbots, MSRA developed their chatbot Xiaobing, and Lifeline implemented chatbots to show the emotional company for suicide prevention. And there is a monastery in Beijing, it's Longquan Monastery. They even built up their robot monk, Xian'er. Besides chit-chat, chatbots can also be our personal assistants with certain tasks. Like Siri on your iPhone, you can command Siri to play a music or set up the clocks. Also, when you go back home, you can wake up your smart home assistant, by saying 小爱 or 天猫精灵, to control your home. After GPT-2 shows up, more and more companies and institutions, they are trying to train GPT-2 as a more powerful chatbot. Such language models are future trendings for chatbots. They have improved generation ability, and they are knowledgeable. These language models can be applied to many tasks just by simple fine-tuning. Here is one extracted sample from the Microsoft Dialog GPT. The user can ask the GPT model, does money buy happiness? And the bot replies, it depends on how much money you spend on it. So you can see this kind of chatbots can be comprehensive and humorous. However, GPT-2 is not perfect. There are still some problems with it. Like first, if you just use GPT-2 on users' phones, GPT-2 requires a lot of computational resources, and this can be computational inefficient on those edge devices. So currently, to avoid the first problem, the most replies are generated on the client-server model. That is, we leave the generation to the server side with more computational resources. And your devices just send this text to the server, and the server will compute or generate the replies and send this replies back to you. However, this still may cause some privacy concern, because these companies can see or can hear whatever you say, and they just upload this data to their servers. Like for example, like when you are at home talking with your family members, like your smart home assistants may eavesdrop your whole conversation. To solve these problems, like we first need to consider the desired properties of using language models as our chatbots. Like first, we need to consider efficiency. We want our chatbot response quickly without heavy computational costs on our devices. Second, utility. We still want to maintain the good generation quality of language models. Another part comes from privacy. Here we emphasize that no plain text should be transmitted to the server side. Like for the first and second point, the client-server model setup can satisfy our needs. But consider the privacy, we also incorporate this client-server model with federated learning to improve the both privacy and the utility. Therefore, we propose our framework Fed Assistant. It's a combination of client-server setting with federated learning. Our data holders can be companies, organizations, and institutions that are willing to share their data together. As usual, our framework leaves most computations to the assistant and the parameter servers, so that this can be done on cloud servers. And also, we propose to freeze user-side model for better transferability. Then we consider using federated gradient update to update the server-side models. Federated learning allows model training for multiple parties without sharing this original data. So here is how we perform federated learning for the assistant side models. There are two benefits of using our two-set modeling. Like first, we don't need to transmit text as usual. Instead, we only need to pass this case and the values of transformer blocks. And then the assistant side can generate replies just based on this case and values. And the second, this parsed case and the values can be regarded as context. They can be reused to speed up the generation process. Also, we freeze the client-side GPT-2, so we can easily deploy this user-side model to every user, and the users just need to do the inference rather than do the generation. To understand why we don't need this kind of plain text transformation, I will show you the formulation of a attention mechanism of GPT-2. Now here, this lowercase q indicates one specific positions query, and the K and V uppercase, they means all positions, case, and values. Here we can see there's one mask operation that must mask out all future position, and there is no probability value assigned to the future position given the current position. That is, we can generate text only based on previous case and value. As for our framework, the assistant side can never have access to the inputs from the user side. So here these queries are kept locally, and the assistant do not know what's the user queries. Here is one example to see how this two-set modeling works. These queries are users' inputs, and they are tapped by users, and these replies are generated by models. Here's the user first query. Hey, can you order me some tickets to run the race? And then the user GPT-2 do one forward pass to obtain the case and values from the query. And these keys and values are sent to the assistant side for generation. After generation, synthesized keys and values are sent back to the user side. And the user side receives this generated reply and continue its new query, like the query 2. And then the keys and the values of all these 3 sentences, query 1, generated reply 1, query 2, are sent to the assistant side for generating reply 2. And this procedure repeats until the whole conversation is finished. Here, I would like to show the detailed algorithm about how we perform federated learning and how we perform our top K compression. Like for each data holder, we simply average their gradient for every batch for every data holder, and every data holder later can update its local model. Our top K compression just selects K largest gradient value to update the model to reduce the communication cost. Then we show the performance of our Fed assistant. We use perplexity to measure the test set of 6 data holders. Lower perplexity, the better model confidence on the generation. This table shows that Fed assistant has better generalization ability. It can obtain lower perplexity on all the testing data. Also, Fed assistant achieves competitive performance as normal GPT-2 over individual data domains. We also perform experiments on top K gradient specification and compare the perplexity of the assistant side with overall perplexity. Here, the suffix phrase means we only use the user side GPT-2 frozen. And the no suffix means we compute perplexity from both user side and the assistant side and report them together. And the suffix A means we only report the assistant side model's perplexity. So from this table, we can see that as we updated gradients are reduced by half, there is no more than 1 increase for perplexity for most local data holders. And our federated learning helps the assistant side to learn better. And also we show that we do this top 2% gradient specification, we can still achieve lower perplexity than training individual GPT-2 models for all testing data. Like for time consumption, we show that the cost for top K gradient specification for over top 1/50% of parameters. We show that the communication cost for any data holder of each round of Fed average is around 18 megabits. And this cost makes federated learning feasible for training large pre-trained language models. So in this page, I would like to talk about some limitation and future works. Like first, our setting is non-ID setting. It leads to no or little improvement over individual data domains. And we might want to try some more advanced Fed average algorithm to mitigate this problem. Like we may use some reinforcement learning-based Fed average. Also, we simply phrase this user set model. It leads to exploded perplexity for the user side. So actually, we might want to switch our pre-training method. We need a more dedicated pre-training method for the user side before freezing and distributing the user side models. Also, another problem comes from the framework itself, because even though our plain text is protected, the sensitive data may still be recovered from models' hidden states. There are some recent works for recovering models' input from the model's embedding. We are still working on including the defense objective during training to prevent information leakage of hidden states. And that's all for our presentation. Thank you.
Is any audience have questions? Can raise hand and type in the chat area. If the audience have no question, maybe I can have questions. So the model you used is GPT-2, is right?
Yes.
You're trying to use the top K comparison to exchange the model parameters.
Yeah.
So do you have plan to move to GPT-3, or what kind of computation workload you actually spend to your experiments?
I mean, the GPT-3 is far too large for federated learning, because when we want to perform some federated average, like we need the whole parameters from GPT-2, right? Like with billions of parameters, I mean, it's very difficult to transmit these parameters for every round of fed average, because there are too many parameters. Like GPT-3 has over 100 billion parameters, right?
Yeah, that's a different level of challenges.
yeah. Even doing fed average on GPT-2 can be very difficult. Yeah.
Okay. So that you actually apply this to a real case, or you just working on some experiment or benchmark data sets?
Yeah, we just experiment on the Google Taskmaster benchmark data set. We didn't put it into the practice. Yeah.
Okay, great. So can you go back to the page about your future work? Because that is, you currently have a very good base of about federated learning on a large scale pre-trained model. So can you explain more about your future work? Because obviously you are just starting at this point.
You mean which part of the future work? I mean, there are 3 parts.
Maybe the first one, yes.
Yes, because these 9ID settings for our experiments, we can see the improvement for all the testing data. But for individual data domain, there is not too much improvement. So we need to consider maybe like fed average. Just taking this average is not good enough. We might want to try some reinforcement learning based method. That is, for each data holder, I only care about my improvement during the fed average, so I can reassign the weights during the fed average term. Like for example, like I have 3 parties. Like party A can have more improvement after federated learning with party C, so A might want to be assigned more weights to get more improvement for its own data, its own testing data scenarios. So fed average is not doing average is just not good enough. So maybe we can doing it from in a reinforcement learning way.
Okay, so in summary, you are trying to use reinforcement learning to assign the importance weight for different clients.
Yeah.
Kind of updated fed average. Okay, that's great. And thank you for the talk. And that sounds very interesting. And I think this is a very good base for integrate a large-scale pre-trained model with federated learning. Yeah, it's quite challenging. And yeah, looking forward to seeing more work about this direction. Thank you.
Yeah, thank you.
Okay, now we are moving to the next paper. Is about RAPFL, a model agnostic plugin for industrial federated learning. The presenter can share your screen and start directly.
Is the slides going well?
Yes, all good.
Okay, I am Xueyang Wu. It's my great honor to have a presentation on our work on behalf of the authors. Our work is RAPFL, a model agnostic plugin for industrial federated learning. Our work is based on the following background. First, federated learning has been gaining more and more attention in the industry with the huge rising demand. there have been many federated learning platforms that allow federated participants to set up and build a federated model from the scratch. Also, the real-world businesses usually have mature serving models that are desired to get performance gain by joining a federated system. However, there are several practical challenges. For example, existing platforms are highly intrusive, complicated, and hard to integrate with built machine learning models. Thus, they have very high entry barriers and development costs, doubting the industrial users to develop a federated model for their business. To make federated learning more friendly to industrial users, we need to meet two major requirements. First, we should reduce the barrier and the cost of developing federated applications. Existing FL platforms provide comprehensive infrastructures for businesses to set up their FL prototypes and services. However, the application of such platforms requires the developers to be knowledgeable and familiar with not only the federated learning algorithms, but also the selected federated learning platforms. Therefore, it turns out to be a high barrier for many potential industrial users. One of our motivations is to reduce such a barrier. Second, the industrial users usually have their own existing AI models that have been sufficiently evaluated on the real-world businesses, which are valuable treasures for them. In contrast, the existing FL algorithms and platforms requires the participants to train the federated models from the scratch, which brings extra overheads and risks to the running AI services. These two requirements lead to two designing challenges. First, the insertion of FL should be lightweight without increasing significant efforts and expert knowledge. Second, the federalization should be pluggable, which means that the users can seamlessly switch its model between the federated version and the non-federated version. Motivated by this paper proposed a novel, simple, yet effective federated learning framework. We named it RapperFL, which can be simply plugged into an existing model machine learning systems with little extra effort. Our proposed framework meets three targets. First, it's pluggable. RapperFL is non-intrusive. That can be simply attached to it, and it reduces the input and output interfaces of an existing model. Second, it's easy to use. RapperFL provides a simple interface that can wrap an existing model with federated components. The users requires low knowledge and familiarity of federated learning. Three, recyclable. Users can reuse existing model without training from the scratch. In a nutshell, RapperFL aims to help business users achieve performance gains by federating the existing models at a minimum cost. This figure shows a general architecture of RapperFL. The left part represents the existing local models. They are deployed separately in different businesses. The right part depicts the federated system, where the existing local models of different businesses are extended with RapperFL. There are two characteristics of RapperFL. First, RapperFL reuses the input and output interfaces of an existing model so that it will not affect the interaction logic of the existing system. Second, like ensemble learning, RapperFL regards the existing machine learning models as the experts whose knowledge can be exchanged and improved with others in a federated manner. In abstraction, RapperFL contains four components: the translator, the aggregator, the scheduler, and connection manager. The translator is in charge of aligning heterogeneous models and producing the federated output. The aggregator fuses the output of the original model, that is the local model, and the federated model. The scheduler controls the federated learning flow, like many federated learning platforms do, including the status synchronization, life cycle management, federated update, etc. And the last one, connection manager, contains the function of network connection, including data transmission, authorization, and other security operations, etc. Inside the wrapper FL, the local model is empowered by two specific ensemble learning-based federated strategies. We name them stacking wrapper and the bagging wrapper. Stacking wrapper is inspired by the stacking method in the ensemble learning that combines the predictions from multiple machine learning models. Its workflow can be abstracted as the following. First, the client utilizes the existing local model for inference, and then the predicted feature along with the local data. For example, the hidden vector of the last layer in a neural network are then fed into the translator. The translators are then aggregated securely with the federated update, and the translator will finally give a federated prediction. As the figure shows, the stacking wrapper essentially stacks two models, the original one and the translator. Notably, we allow heterogeneous local models with the wrapper FL. In this case, although the local models could be heterogeneous, the translators are designed to be homogeneous across all participants. That allows us to apply fed average or secure aggregation to the training of translators. This architecture also implicitly conducts the feature space alignment across different federated participants. So it allows us to deal with the non-IID data. Stacking wrapper requires local models to be parametric models that naturally generate feature vectors. It is not compliant with non-parametric models such as decision tree and the support vector machines. Here we introduce the bagging wrapper, which leverages the idea of bagging in ensemble learning. We treat the data set in each client as a random sample from a global data distribution and ensemble the predictions from all local models. As shown in the figure, the translator essentially embeds local models received from other participants and infer predictions from all models locally, and then fuses the outputs. The workflow is as following. First, the local model are uploaded to the wrapper and also receive the external models from other participants. Then the translator simply ensemble all external models and the local models. Optionally, the local clients can tune the ensemble weights according to the local data. However, in our empirical results, we found that even we assign equal weights to all external models, we can achieve satisfying results. The advantages are apparent. First, it's model agnostic. Second, the whole process is fully decentralized, and the client can decide whether to join the federation automatically. And finally, without training the translator or training the federated model, the training cost and communication cost is very low. Compared to stacking wrapper, bagging wrapper does not pose any assumption on the architecture of local models. So it's more efficient, but it also poses another major issue, is that transferred local models might raise potential privacy risk. Notably, the risk of privacy leakage from the models could be eliminated by incorporating with trusted execution environments or fully homomorphic encryption. Sorry. Here, I would like to show our major experimental results. We evaluate our methods on 4 data sets of 3 tasks. There are structural data, image data, and textual data. The settings, we set up 2 settings to simulate the real-world scenarios. We named it imbalanced setting, where the numbers of incidences among clients are different, and the non-ID setting, where the class distributions among the clients are different. And we also varies the number of clients from 5, 10 to 20. Due to the time limitation, I will skip the details of our results. For the readers who are interested in details, you can refer to our full paper. we only need to bear in mind is that with the rapid FL, we can significantly improve the local model's performance. For example, in the bank telemarketing prediction, we have around 3 times higher F1 score. And also we evaluate on real-world multi-center medical data that is collected from the 3 medical centers and is naturally non-IID and imbalanced. The prediction result is also consistent to other settings. We achieve comparable performance of the centralized settings with 4 different kinds of machine learning models. Similar results can be observed from the image dataset and the textual dataset. It's worth noting that in all these experiments, we use different architectures of the models, of the local models, to show that our rapid FL is compatible with different kind of local models. I would also like to mention about the training cost. In these slides, we can simply compute the cost of training with traditional federated learning methods. Let's say is Fed average and our rapid FL. For the stacking wrapper, we can simply get the conclusion by comparing the size of FM and FT, where are the computational cost of the local model and the translator. In our setting, the translator is much smaller than the models and can also achieve satisfying results. With the smaller size of translator, we can significantly reduce the computational cost. And for the backing wrapper, without training a new model, the only cost comes from the model transition. That is the numbers of clients times the size of local model. In conclusion, Rapid FL is an easy to use plugin for industrial users that have already had a mature and existing model that have no experience on federated learning algorithms and platforms. Second, Rapid FL is model agnostic, lightweight, low intrusive, and require small development workload. The empirical results on both performance and deployment cost validate its efficacy and efficiency. That's all about my presentation. Thank you for your attention.
Hello. Yeah, I think there's one question is from the chat. From Joey Wang, thank you for introducing your simple practical framework. Could you please elaborate more on how privacy is protected during the process of the translator, the aggregate, and the collection manager?
Okay, thank you for your question. As I have mentioned, the privacy issue is protected. Let me turn to the slides. As we have 2 different kinds of the wrapping strategies, the privacy protection are different. First, for the stacking wrapper, the translators receives 2 inputs. First is the local data, which is also optional, and second is the feature. And we think the parameter of the translator have the risk to leak privacy, right? So in this case, we apply the secure aggregation to protect the individual translator. And in this case, the central server can only get the aggregated translator. So we believe that in this scenario, the local privacy can be protected. And for the backing wrapper, the external models are exposed to other users. So as I've mentioned, it is the major issue of the privacy risks. Currently, we believe that it is as safe as the federated average. In the future, I think it can be combined with the trusted execution environments or fully homomorphic encryption environments. Because in this case, we only do the inference rather than the training. So the computational cost should be as low as possible to apply such expensive homomorphic encryption operations. And during the connection management process, the connection management only manage the connection. It's about the network connection. It is have nothing to do with the security operations.
Okay, so I have a question. I'm just curious about the use scenario, because when we talk about the plugin, is that means sometimes the business will plug out, or they just plug in for maybe one time or for 7 minutes? Is that a special case you will handle, or have other use cases you are focused on?
Yes, as has been introduced previously, for many mature businesses, they are worried about that to switch their business to a federated model will affect their performance, because the existing models are sufficiently evaluated on their services. So our idea is to reuse the input and output interfaces of an existing system. And therefore, the user can efficiently switch from the original model and the federated model. And in this case, it's very useful for those who have running AI services, because they are not fully trusting in the federated model. For example, for the bank, they have their own risk management model, and they only want to use the federated model as another feature rather than to replace the original system. So we designed the plugin, the idea of plugin, to apply federated learning to their model.
Okay, I'm still confused about the application scenario. Maybe I will read your paper to get more information.
Okay, thank you.
Yeah. Okay, if there's no more question, thanks for Xue Yang's presentation, and then we move on to the next paper. The next paper is about the practical and the secure federated recommendation with personalized mask. The presenter can share the screen and then start.
Okay.
Okay, good.
Xue Yang, you should stop. Yes. Okay, I'm sharing my screen. Yeah. Are my slides and voice going well?
Yes, all good.
Please. Okay. Hi everyone. My name is Liu Yang, and I'm a PhD student of FL-IJCAI'22. And my presentation today, in my presentation today, I will introduce our paper, practical, secure, federated recommendation, this personalized mask. And in today's presentation, first I will introduce a background, which is a problem in federated recommendation system. And then I will explain why the related works cannot solve the problem well. Therefore, we propose FedMMF. I will show the methodology and experiments of our paper. And for the background, I want to first introduce the scenario of recommendation system, REXIS. In the REXIS, we have the rating matrix R as the training data, and the goal of REXIS is to guess the rating value that one user could give to a specific item, such as a book or movie. One basic algorithm of REXIS is matrix factorization, which decomposes the rating matrix R into two submatrices. P and Q. P stands for the scores of user tastes on latent interest categories, and Q stands for the atom latent scores. And P and Q can be optimized alternatively, fixing one of them using the known rating as the training data. Then the federated matrix factorization, FedMF, came out regarding mobile devices as participants of the federated process. The rating information is kept in the local corresponding party. Thus, privacy is protected to some extent. Each party updates their own user latent vector and computes the gradients for updating the atom latent vectors. Then each party transmits the gradients to the central server, and the server aggregates all the gradients and updates atom latent vectors. And that's the process. However, the uploaded plaintext gradients could still disclose local private data. The closure process is as following. First, the server could continuously receive gradients of atom latent vectors. Let's say the server receives the gradients at time t minus 1 and time t. Second, the server could also know the update rule or formula of the user latent vectors. Therefore, the user obtains 3 equations for 3 unknown variables, pt minus 1, u and ptu, and rui. The equation group could be easily solved to reveal the private raw ratings, RIU. And the existing secure FedMF works is to further protect data privacy utilizing HE or DP. HE-based FedMF utilize Pallier to protect the transmitted gradients. The server aggregates the received gradients in ciphertext state. Therefore, it cannot reveal any privacy of all parties. However, Pallier brings extra computation and communication costs because of the inflation of ciphertext and complicated cryptographic operations. Therefore, HE-based FedMF has a severe efficiency problem. And the second one, DP-based FedMF, choose to add differential privacy, differential private noises to ratings or gradients. Thus, it could guarantee differential privacy and could be theoretically provable. And the efficiency of DP-based FedMF is great because the processed data is still plaintext. However, DP-based FedMF has bad accuracy because the added noises could harm the model performance. In conclusion, they cannot satisfy the both kinds of work cannot satisfy the real-time feedback and accurate personalization requirements of Rexis. Yeah. Next page. Therefore, we proposed federated mask matrix factorization, which is FedMMF, to protect the data privacy without sacrificing efficiency and utility of Rexis. The main idea of FedMMF is a personalized mask. First, we train a local model at each party. Then the local model make predictions about each original rating. We call this prediction personalized mask, and we subtract the original ratings by the corresponding predictions. We found that the personalized mask could provide protections for ratings, and we tried to analyze the security of personalized mask by defining the privacy indicator of personalized mask as how much the personalized mask could have the original ratings, and we provide a theorem that proves the abilities of personalized mask depends on the quality of local data. Then we design adaptive secure aggregation methods based on the property of personalized mask. for the parties in the secure group, which means the parties own secure enough personalized mask, and they need not adopt extra secure methods for protection. Their mask ratings will not leak any privacy. While for the parties in the insecure group whose personalized masks do not protect well, we adopt the practical secure aggregation protocol based on random additive masks, which is also more efficient than homomorphic encryption. In the secure protocols, each pair of parties negotiates with each other about an additive mask. One of them adds the mask on their gradients and the other one subtracts the mask from the gradients. Therefore, the server could remove all the negotiated masks by simply adding all received masked gradients and obtain the aggregated one. And in the experiments, we first showed the efficiency promotion and privacy discussion. Compared with HE-based FedMF, FedMMF with all parties in the secure user group could largely speed up the training process where practical secure aggregation protocol. Besides, and furthermore, the personalized mask technique could further improve the efficiency if some of the parties have secure personalized mask and could directly share gradients without the secure protocol. Therefore, we conduct defense experiments against two kinds of attacks on the movie-lens datasets. The first attack is a recovery attack, which is an intuitive attack for the adversary to recover the original ratings of each party. We assume that the adversary knows the minimum and maximum values of the original ratings of each party. Then the adversary could scale the masked ratings to the range of original ratings for recovery. We define G at the little g as the error level. If the difference between one recovered value and the corresponding original ratings is less than G, then the recovery is considered successful. Thus, there exists a recovery rate alpha for each party's mask rating. As we can see in the left figure, when the error level is small, which means G is 1 or 2, the adversary could nearly reveal no party's privacy without recovery rate larger than 0.5. And as the error level increases, the recovery rate begins to grow. However, a higher error level means a more inaccurate recovery, and the utility of the recovery ratings is worse. And the second attack we conduct is shown in the red figure. Is the ranking attack. The ranking attack is much easier for the adversary than the recovery attack, which the ranking attack tries to find the high rating items from their mask ratings. First, for each party, the adversary ranks the rated atoms according to their mask ratings. Then the atom in the top each proportion of mask ratings are selected as high rating atoms. Similarly, given each little h, we also sort these atoms with regard to their real ratings at a true high rating atom set. Thus, therefore, we could evaluate the ranking attack with hit ratio beta, which is calculated at the ratio that atoms selected using masked ratings are in the true high rating atom set. If the selected top proportion is small, for example, H is 1 or 2, the attacks performed on most parties mask ratings obtain a hit ratio less than 0.5. Therefore, we could say a considerable number of users get their ratings privacy well protected with the help of personalized masks, which further improved the efficiency. And the
Hello, sorry for interruption. You have only 1 minute left. Yeah. 1 minute.
Okay. Okay, I'll accelerate. And we also implement 3 privacy models to construct personalized masks with different properties, which is 1-order mask, 2-order mask, and higher order mask. And as we can see from the experiments, FedMMF models with different privacy masks have no effectiveness loss compared with FedMMF in all data sets. Moreover, we found the FedMMF even outperformance FedMMF because of the ensemble training scheme. And that's all for my presentation. And in our next step, we want to extend the idea of personalized masks to more general tasks besides Rexis and try to combine it with DB theory and sensor.
Thanks. So does any audience have questions to raise? Okay, maybe I can just ask questions. Is because you mentioned that the personalized mask, is that used for personalization or personalized model training, or just used for the privacy protection?
I should submit. The aim of the personalized mask, at first we wanted to protect the privacy, but in the experiments as the last slide, we show that the personal mask also benefits the utility of the model, which means it will also improve the accuracy of model. Which because we consider it it is the reason that we use ensemble learning scheme, because the training of local model and federated model follows the scheme of ensemble learning. So we think it's the reason for the improvement of accuracy. So the answer is the personalized mask can both protect privacy and also improve the utility of model.
That is very interesting discovery. Yeah.
Yes.
I think it's the first time to have this kind of idea to combine the personalization and the privacy preserving together, use one methods. Yeah, that is interesting. Yeah, very interesting.
Yeah, thank you.
And by the way, for the personalization, because the metric factorization is kind of how to understand the personalization on the metric factorization in the federated setting?
Oh, I think the personalized mask, the personalized is different from the personalization in federated learning. It's different words. In federated learning, personalization, it means we should for each client we should improve its own accuracy, right? Not the accuracy of the global model. But for this for this paper, we still evaluate the model with the global accuracy.
Okay. Thanks. Oh, there's one more question from the chat, and thanks for the presentation. And I wonder why the mask will not affect the FL model utility. Can we regard it as a kind of DP, differential privacy based noise?
Oh, yes, for the first question, why the mask will not affect the FL model utility? As I mentioned 2 minutes before, because we use the ensemble training scheme, so the ensemble training will combine a lot of different weaker learners into a a stronger learner, right? So I think it's a reason why the marks will not affect the FL model utilities. And the second one, can we regard it as a kind of DP-based noise? I think I want to it's my next step work plan. I want to combine the idea of personalized marks with DP series. So maybe we can discuss this problem later. For now, I have no idea how to combine the two series.
Okay, great. Yeah, that is a very interesting topic, because the federated recommendation and also the privacy preserving is also very hot topic in federated learning. And looking forward your future work combine that with the DP noise. Okay.
Yeah.
Thank you. And now we are moving to the next paper. It's about the secure forward aggregation for vertical federated neural networks. If the presenter is ready, please share the screen and then start your talk.
Okay, can everyone see my screen now?
Yes, yes.
Yes, okay. Hello, everyone. I'm FL-IJCAI'22, and today I'm going to give a talk about our work, secure forward aggregation for vertical federated neural networks. But first is the background, and we focus on the vertical federated learning, which enables cross-silo data cooperation in a privacy-preserving manner. VFL enables institutions which hold different data features that can collaborate trains a model while keep their data secure. But nowadays, most works in vertical federated learning focus on linear models and tree models. Those models' capacities are limited, and we seek for more powerful models like neural networks in vertical federated learning. Split neural network is a framework that enables all parties in VFL to train a neural network. In each 4 sections in split neural network, each party holds a bottom model for transforming their raw data to a transformed data. And the bottom model will send the transformed data to the active party, which is the party with the label. And the active party will concatenate those transformed data and analyze it using the top model to make predictions. And then they will use backpropagation and send the gradients back to each participant for them to update their bottom model. However, the data security and the model performance is not well studied in split neural network. For the data security side, you can see that the transformed data is disclosed to the active party, and the transformed data contains information of the raw data, which is vulnerable to inference attack. And on the performance side, you can see that the bottom models here are isolated, and the transformed data contains only a part of the information in the raw data. And this result is from a paper which was released before. It says a significant amount of the low-level feature interaction for low-level feature information is discarded while the raw data pass through the layers. And however, the discarded information could be useful for split neural networks prediction because their interactions might be crucial to the participants. The discarded low-level feature informations and there exist interactions between VFL participants. So low-level feature interaction between VFL participants might lost. And here is an example. Suppose that there's 2 companies that wants to build the recommendation systems. So there are 3 models, 1 top model and 2 bottom models. The bottom model A received the raw data, which is a cotton diaper from a famous brand. And it is organized with its name, ingredients, and price. And we only show the cotton diaper on the image here to represent these features. And we feed these features from a cotton diaper into the bottom model. And we get a transformed data, which embeds the information called baby products. And we send it to the top model. And for the bottom model B, we do it the same way. And we got a raw data from Corona beers, and we embed it into drinks in the transformed data and send them to the top model. And the top model received leads to transform data, concatenate it, and make predictions based on them. And they do the prediction saying that I don't think people who buy baby products will buy drinks. The prediction is rational. However, it is also well known that people who buy cotton diapers may be interested in beers. It is because it is from a well-known data mining cases. So we can see that there's a low-level feature interaction loss because the diaper and the beer, the low-level feature interactions between them are lost in speed neural networks. So there is a model performance loss. And we can try to contain more informations, contain more low-level informations in the transformed data and send them to the top model. However, in this case, the top model may perform inference attack here. So in this case, the raw data is insecure. Therefore, there's a trade-off between the model performance and the raw data secure. And the core here is the informations inside the transformed data. So we conducted experiments to evaluate the trade-off. We use feature inference attack to analyze the transformed data and try to approximate the raw data using the attack. And to control the amount of the information in the transformed data, we just adjust the height of the bottom model according to the analysis in the paper, understanding the image representations by inverting them. And the right part here is the results. We can see that when the number of layers is low, the model accuracy is high, but the data is insecure because the attacked result is close to the raw data. However, when we increase the number of the height of the bottom layers, the model accuracy drops significantly while the data is secure. So we identify the trade-off between data security and model performance. To mitigate this trade-off, we present a protocol called secure forward aggregation to protect the transformed data at the topmost layer of the bottom model. And we claim that secure forward aggregation can protect the transformed data in two-party setting, and it will not import noise to the final model and resist to state-of-the-art inference attack. And when the security is ensured, we can arbitrarily choose the height of the bottom model to achieve good model performance. The core of the secure forward aggregation is using an encrypted weight mask to produce removable mask for transformed data. The figure on the right part represents the procedures of the two-party secure forward aggregation protocol. The block here represents the weights, the model weights of the topmost layer of the bottom model. And A here is the active party, and P0 here means the passive party, and it's a two-party thing. And the content between the bracket here means the data here is being homomorphic encrypted. In the preparation stages, the passive parties collaboratively generates write mask, encrypt it, and send it to the active party, just like here. It was generated by the passive party. And in the forward pass, in the first steps, all parties just do the plaintext forward, like here, and the ciphertext forward. It generated the data mask here. And in the step 2, they just shared unencrypted results. It's started by the active party, generated a random matrix as max for itself, and subtract it from the encrypted data mask, and send the rest part to the passive party. Then the passive party will decrypt it and add it on their own data on the step 3. In step 3, all parties just applied mask on their encrypted results. And then they will aggregate the results using sum and send them to the top model. And in the backward process, each party just receive their gradients and update it on their plaintext weight, just like here and here. They use stochastic gradient descent to update their gradients on their plaintext weights. And weight mask here keeps unchanged to reduce communications. Now first here, we state that data masks are removable. If we regard the weight mask encrypted here and the plaintext weights as the true weight of the topmost layer, of the topmost layer of the bottom model of the active party, we will find that the shared data masks are a part of the output of the active party's transformed data. So the secure forward aggregation protocol will not import noise to the training. And then on the security side, For the passive party's data security, the active party knows nothing about the data max, about the passive party, because the weight max here used for generating data mask is encrypted. So the active party knows nothing about the active party's transformed data. And for the active party's data security, the mask here is decrypted. It's a shared result from the data mask. So it is safe and it does not contain any information from the raw data. And one more thing we have to state that is that secure forward aggregation is able to perform in two-party sync, but some protocols other than like secure aggregations are not unable to perform this. It is because the active party can recover the result from the aggregated result by subtracting their transformed data from the aggregated results. But in this case, we use secure forward aggregation to obfuscate the active party. The active party does not know its true output of the transformed data because a part of the transformed data is encrypted and sent to the passive parties. So in this case, we can say that secure forward aggregation is able for the two-party setting. We have already shown the protocol, and now it's time for evaluate it. In the experiment setting, we choose a 6-layer speed neural network with fully connected layers and the centralized model with 6 layers, multiple layer perceptions. For the fair comparisons for security, we set the height of the bottom model of the speed neural network to 5, and the neural network with secure forward aggregation to only 1, because it's always secure. And we use the generative regression network to attack the transformed data. And we initialize the weight mask using Xaviers. And the data sets we used in our experiments are listed here. The top right corner, the table in the top right corner shows the result.
Sorry for interruption. You just have 1 minute left. Yeah.
Okay, I'll speed up. The speed neural networks performs bad in these data sets when ensuring the data security, but using secure forward aggregations, we can achieve the data security of the model with good performance. And this figure here shows that the secure forward aggregation protocols performs well in the multi-party settings. And the performance of the speed neural network drops significantly because more isolations between bottom models. And the last here is the evaluations of the trade-off. We can see that the performance drops when we increase the height of the bottom model in speed neural networks. However, when we apply secure forward aggregations on speed neural networks, it behaves much better because we change concatenates into sums, and the concatenates in speed neural networks treats each inert independently. But it cannot fundamentally solve this performance problem. But on the security side, we can find out that the network with the secure forward aggregations is able to resist the inverse attack. Attack 1 here means attacked on masked transformed data, and attack 2 here means attacked on the mask generated directly by the weight mask. And you can see the result is close to the random guess. And one more thing is that attack on the secure forward aggregations diverge fast. The mean square error increased when training, so which means that the state-of-the-art inverse attacks is ineffective. So we can say that secure forward aggregations enables arbitrary heights of the bottom model for good model performance while keep the data secure. And here's the conclusion. We identified a trade-off between data security and model performance in speed neural networks in vertical federated learning, and we proposed a protocol called secure forward aggregation to mitigate the trade-off in speed neural networks and achieve both good data security and both good model performance. And our further works includes to reducing the computations in secure forward aggregation and analyze the effects of the weight max to the training and ensure the secure of the protocols in other settings other than semi-honest setting. Thank you.
Thank you. And anyone has questions, please raise your hand and or type in the chat. Oh, there's one question. Is the bottom model trained collaboratively? You can see that question in the chat area.
Yes, I can see that question. The bottom model is trained collaboratively because the top model here sends the gradients back to the bottom model. but the bottom model is held by the passive party, and the bottom model will not be sent outside. So you can say that the bottom model is trained correctly, but it's relatively safe.
Okay, may I have a question is, because in your setting under this framework, so the raw data in each part will be transferred by each model, and then the transformed data will go through these secure aggregations and then be input to the top model. So I just wondering, the transfer data is aggregated or just per item or per user?
The transform data is summed at the secure for aggregation and then sent to the top model. And the transform data here is from different participants of vertical federated learning.
Okay, so in another way, say each user's data, for example, XA, XB, XC is represent one user and their profile in different banks. Is that kind of information and then be transferred and then go through a third-party secure aggregation server, or and then go through to the part C? Is that kind of application scenario? Is that my understanding correct?
The data, the XA, XB, and XC here are featured data from a same person.
Yeah.
And they will be transformed using the bottom model and then using secure forward aggregation to aggregate it and then to the top model to get the prediction. So that is, so your understanding is correct.
Okay, thank you. Just one more question in the chat. Can see the questions or you can answer directly. Yeah.
How to backward the gradients to each bottom model since the forward path is secure aggregation among clients. I'll return back to this part. The top model gets the aggregated result and it can calculate the gradients at for all participants and all participants and get this gradient. And then they have their bottom model. And then they can update their gradients using on the plain text weights. And then do the back propagation to their lowest layer in the bottom model. That's the way that secure for aggregation performs back propagation.
So there's two questions. Maybe you can you can read it and answer it. Hello, Joy. Can see another two questions.
Wait. Does secure for aggregation brings additional communication cost? Well, it's true. It brings additional communication cost because it sends an encrypted result to the passive parties. And this communication result does not happen in speak neural networks. So secure forward aggregation will be a little bit slower than the speak neural network.
Okay, thank you for your presentation and yeah, that is interesting work. And let's move to the next paper. Next paper is about the a fairness framework for federated learning. Yeah, if the presenter is ready, can you share the screen? Hello? Are the presenter ready for presentations? Maybe it's not here. We can move to the last paper.
Wenxin Wang is here. Wenxin, it's your turn to present. Are you ready?
can see the
maybe he just
author of
feel
this
for a
paper
while and with
yeah.
So if the authors for the last paper is here,
yes.
Can you do the presentation and share screen? The last paper is about an efficient industry federated learning framework for AIoT, a face recognition application.
Okay, I'm sharing my screens. Okay, does my slides go well?
Yes, yes. Yeah, please start.
Okay, I'll get started. My topic is about an efficient industrial federated learning framework for AIoT, and we focus on a face recognition application. So the face recognition is about given a face image X captured by an AIoT devices or the cameras. And our goal is to collaboratively train a neural network to determine the identity of each person. For privacy issues, we are not allowed to uploading the captured photos to the server. And this problem have two main challenges. The first challenge is about efficiency challenge. So actually it is very challenging to directly apply federated learning algorithms in this scenario since the IoT devices usually are resource constrained. The second challenge is about privacy. So as shown by lots of previous words, it's not safe to share gradients with the server, and the image used for training may be recovered via some attack like gradient attack, and this definitely leads to a privacy leakage. And our two solutions is use transfer learning. So we first pre-train a model on public available large-scale dataset at server and use that pre-trained parameters as a initialization of fed average. And second solution is partial sharing. Only the public module will be shared and uploaded to server for aggregation in each communication round. So the overall advantages of a solution is for efficiency challenge, we explore the sufficient computing resources of the server to undertake the heavy computation task of training neural networks, and that can provide a good initialization for the IoT devices. So in a way, we are aimed to lifting the workload of the end devices since their goal is to just slightly adjust the model parameters, or we call it fine-tune, to fit the local data in a collaborative way. And for the privacy challenge, we keep the classification head private and only upload the gradients of the public module. In this way, we can address the privacy issues by blocking the forward propagation needed for gradient attack. Let's first recap the methods for face recognition. So compared with conventional classification tasks, face recognition is an open set problem where in test data, the identities are disjoint from the training data. So in this scenario, our goal is to encourage more discriminating features. And there are lots of objectives proposed in the literature of face recognition. And in this work, we mainly focus on very effective called ACK-face, and its loss function is defined in this way. So as we can see, many use a margin parameter M to encourage a more discriminative decision boundary. And our pipeline of training is given in this feature. So given an input image, we send it to our backbone model to extract the face representation alpha, and we send it to our projector, and this projector corresponds to and the loss function layer we mentioned before. And we can calculate loss and creating the gradient with respect to loss to obtain the gradient for the projector and for the model. And note that only the gradients of the module of the public module will be shared with the server for averaging, and the gradient for the private model or the parameters of the private model will never leaves the clients for privacy. And so formally for forward passing, we first extract the face feature alpha, and we send alpha to a projector to get the classification logits. For the backward, we calculate the gradients with respect to the projector and the backbone model respectively. Only the public modules gradients were sent to the server for aggregation. For inference, we first extract all the latent representation of the photos stored in Oracle for each person, and we can obtain a set, which is the set of face features of all the people of interest. For example, all the people in the company. And so for inference, given an input image, we first extract its latent representation and compare it with all the representations in the Oracle. The decision is given by finding the closest representation in a Euclidean space. So, and we also design some training strategies for effective federated fine-tuning. So as we all know that in federated learning, where the data distribution is not identically distributed across participants, the local training may lead the model to learn a poor face representation due to the skewed local data distribution. And we aim to mitigate the negative effects of client bias during federated fine-tuning through the two strategies. The first strategy is to freeze batch normalization status. And batch normalization is a very famous trick to speed up training, and it computes the rounding mu and sigma of the features of each layer and normalize it to speed up training. But actually, this mu and sigma is keep updating using some like moving average. And our strategy is, when fine-tuning, we do not update these statistics and simply freeze it. And the original mu and sigma, which is pre-trained on the large-scale data sets, and our insight is that the original mu and sigma can already reflect some global distribution since it is pre-trained on a large-scale data set. And the first strategy is warm-up fine-tuning. So we linearly increase the learning rates when federated fine-tuning. And actually, this warm-up strategy is very useful and popular in training from scratch. And we found it also very effective when applying it to federated fine-tuning scenarios. So for experiments, we use this MS-EM dataset for pre-training the model. And this dataset is consisting of millions of face images. And it is worth noting that this dataset mainly consists of European and American people's face images. And for our fine-tuning datasets, we use a private dataset which consists of 20,000 face images of East Asian people's face. And as we can see, there is a distribution shift between our pre-trained datasets and our fine-tuned datasets. And these datasets also consider some challenges in the face recognition, like different illumination and occlusion like masks. we compare 3 baselines. The first baseline is centralized, where we collect all local data to train a model in the central server. And the pre-trained is we directly use the pre-trained model for inference without fine-tuning it. And solo is we fine-tune the pre-trained model only with local data and do not conduct federated learning. So in this page, we show our results. As we can see, our result is very close to the obtained under a centralized setting and can achieve up to 8% compared with the pre-trained model. This is because, as I mentioned before, there is a domain shift in the pre-trained dataset and our downstream dataset. And this is some communication efficiency and computation efficiency of our methods. And as we can see, in each communication round, we only need to exchange 1 megabits of parameters, and the flops and add is also relatively small.
Sorry for interruption. Just have 1 minute left.
Okay, so we also conduct attack experiments to verify the privacy preservation of our methods. The threat model is a famous duplicate for gradients, which aim to recover the input image given the shared gradients. So, and we show our effect of privacy preservation. And as we can see, if we in the baseline, we can nearly achieve an pixel accurate recovery of the input data, where under our methods, and the attack output is nearly blurry and the stroke can't be distinguished from the background. So our conclusion is we propose an efficient framework for conducting federated learning on IoT devices, and which can significantly reduce the required computational costs and communication rounds, make it suitable for AIoT. And we employ partial sharing for privacy preserving and against the popular gradient attack. Our experiments verify our effectiveness and efficiency of our methods. So we believe our approach is valuable to both academia and industry. So that's all.
Okay, so thanks for presentation. Does anyone have questions? Yeah, since there are no more questions, if someone has a question, you can type in the chatting area, and you can reply that message in the chatting area, or if someone is interested, and then can contact Yonong by sending email, and the paper is shared on the website. Okay, thank you for presentation, and we are moving on to the next paper.
Hello, sir. I'm ready.
Yeah, just go ahead. Yeah.
Hello, everyone. My name is Wenxin Wang. I'm so glad to have the opportunity to give a speech online. The topic I want to share today is about a fairness framework for federated learning. We named it RCM. The other comes from Beijing Electrical Science and Technological Institute. As we know, the federated learning incentive is important because it can enable high contribution participants to provide models with high similarity. However, There are two problems here. On the one hand, there are still some unfair phenomena in the distribution of incentive mechanism for federated learning. On the other hand, existing federated learning doesn't consider the role of interest when introduce cost. So these problems require our research to address. In this paper, we propose a method to achieve fairness in federated learning, proposing by setting a reputation system, reward punishment, and cost interest, compensation mechanism. Moreover, we introduced interest compensation to make the system work better. Experiments on fairness, accuracy, and compensation trends on benchmark datasets show that RRCM can achieve higher fairness than traditional framework. First, when propose a definition of RRCM fairness, it's divided into a quantitative relationship and a quantitative relationship. The former means that participants with higher contributions get more rewards. The latter is explained by the Pearson coefficient. A higher Pearson coefficient indicates more fairness. The operation of the RRCM framework is shown in the figure. First, the data owner uploads local models that must pass the reputation system threshold. If the reputation value is less than the reputation threshold, the federated system remove data owner with abnormal reputation. Models with good reputation will pass reputation system. Second, good local models arrive at the central server to form a global model. Federated system can get benefits with the exchange with the external systems through the global model. A portion of benefits is used to compensate reputable participants, and the other is temporarily turned on the central server. Finally, when the federated system training is over, the central server will return the temporary benefits to reputable participants. RRCM framework consists of three parts: reputation system, reward punishment measure, and cost interest mechanism. The reputation system distributes revenue commensurate with the participants' contribution based on the reputation. The reward punishment measure is divided into two parts. Rewards are given to data owners through incentive. Punishments are by setting a reputation threshold to remove participants with no reputation. The cost interest mechanism means that the federated system will only reward participants after compensation the data owners with the cost and the interest. Then we experimentally demonstrate the feasibility of RRCM. We use through metrics as the evaluation criteria for this experiment: accuracy, fairness, and compensation trend. Accuracy is obtained by comparing the federated system output to the test set. Fairness can be quantified by definition of RRCM fairness. A higher Pearson coefficient indicates more fairness. Compensation trade compares the reward of the incentive mechanism in the three schemes with no cost and cost interest. In the accuracy comparison, RRCM accuracy is almost the same as Fed average and higher than other frameworks. This result occurs because the RRCM framework is based on the Fed average algorithm. In addition, Q-FFL and CFFL are fairness frameworks. An increase in fairness may affect the accuracy of the results. In fairness comparison, the fairness of our CM training is better than Fed average Q-FFL and CFFL. The framework proposed in this paper can give more incentives to participants with higher contributions. In the compensation trade, the compensation of different schemes is as follows. The low-cost scheme will not be compensated in the system. The cost scheme is compensated and then incentivized in the system. However, in the cost interest scheme, the system first compensated participants for cost and interest. Part of the benefits is then given to the participants. The remaining benefits are returned to reputable participants at the end of the system training. Compared with the proposed two schemes, the cost interest of the third scheme is more in line with the actual training of the system. In addition, it provides abnormal contributions from participants. To sum up, according to the fairness, accuracy, and compensation trends, the RRCM incentive mechanism is superior and reasonable compared with the traditional framework. Finally, a simple conclusion. This paper proposes an incentive framework for RRCM. It can improve the fairness of a federated system and make the incentive more reasonable. In addition, the reward punishment measures still have room for improvement, such as setting ratios. Hopefully, this framework will be improved in the future. This is all. Thank you for your lesson. I'm so sorry. My English lesson and speaking are a little weak. Here is my email. You can send your question to my email. I will ask as soon as possible. Thanks again for listening.
Thanks for the presentation. So if anyone have any questions, you can type in the chat area, or you can send the email in that email address, or you can check the paper in details. The paper is shared in the workshop website. You can get the, I think it's, you can get the address from the paper as well, the email address.
Okay, thank you very much, Professor Long, for hosting the paper session. And now we have concluded the first paper presentation session. We will take a lunch or dinner break, depending on where you are in the world. It will be a 1 hour break. We will come back after an hour. Beijing time is 7:40 p.m. Vienna time is 1:40 p.m. Okay, thank you everyone. See you in an hour's time. Hey, Victoria.
Hi.
Everything okay? Yeah, we can hear
Yes.
you. Yeah.
Can you hear me?
Yeah. Yes. Yes, we can hear you. Okay.
Can you see me?
Sorry, we cannot see the video yet.
Okay, just
maybe can you try to share the screen to see if we can see the screen sharing well?
Okay. Let me adjust this. Can you see me now?
Yeah, now we see the video.
Okay, great.
Yeah, let me introduce the.
Hello, Victoria. Can see you.
Professor Yang, I'm so glad to see you.
Me too. Yes. Are you in Europe or in UK?
I'm actually in Beijing.
Oh, okay.
My flight has been canceled many times due to COVID, so I'm still here.
It's hard to travel.
Okay, Everyone, welcome back to the second half of today's workshop. So today we're very happy to have Dr. Victoria Wang to kickstart our second half of the workshop with her invited talk. Dr. Wang is the CXO of the IEEE Standard Association. In this position, she engages in global technology community and enables them to use technology standards for the benefit of humanity, particularly for its sustainable development goals. So she advised a range of technology standards and ecosystem building, including IEEE standardization of federated learning. Dr. Wang is also IEEE Standard Association's China strategy lead. Dr. Wang, if you can please share your screen.
Oh, thank you, Professor Yu. We're going to have a very special talk today. So Professor Yang and I will just take the flow of our conversation.
Oh.
So we not distract the audience with our PPT. I know it's very special, but it seems it works very well between us.
Sure. Thanks. Please, the floor is yours. Thanks.
Thank you. So there's no need to introduce Professor Yang because everybody knows him here. So I really want to thank you, Professor Yu, and thank Professor Yang for having this session and invite me to be here. And also thank the audience here online. And this topic is about the ecosystem of federated learning. It is not like the technical talk given by the AI scientist. I'm really inspired by Professor Yang's conversation with Blaise, who is the VP of Google's AI, Google Brain. And back early this year, they had a fantastic conversation. And in that, they talked about a grand vision of federated learning, which is a virtue, a giant virtue network of federated learning. I know that I just give this will not make much sense to the audience. So what I want to do is I wanted to, summarize that kind of conversation so you get an idea of what it means by this giant virtue ecosystem of federated learning. I guarantee you it is beautiful. There are two beautiful minds meet and spark this.
Sorry, Victoria, you are muted now. Sorry, Victoria, you are muted now. Sorry, Victoria, you are muted.
Then we will discuss what it takes for us to get that grand vision. And first, I want to summarize this grand vision. I mentioned at the beginning of the conversation, Professor Yang actually posed a kind of question, and he said, one day we're going to run out of the data, however big it is, from Google or from other big organizations. And then the next step would be that we're going to use a network of the data silos to build small models. And then these small models can join a network of models and building a virtual pre-trained model. But then he posed the question, that is the key part of what he want to point out a trend. That is, he said, but when we use a network of distributed smaller model, privacy issue suddenly occurs again, because this model somehow reflect their local privacy information. Then he asked the question from Blaise about his solution. Blaise has been a very sharp mind. Of course, he picked up this is not just a question, but a vision, and a very special one, which challenging his thought to another level. So he said he agreed that we are heading to that direction depicted by Professor Yang. And then he certainly delighted with this question and developed it further by saying that, maybe just as a thought exercise or sketch as to what might work. So he said, let's imagine something like the basis network. He said the idea of the basis network is that you make a network out of the linear mixture, and you have a basis network combined using coefficients into a target network. And he then said that imagine you also add an idea of sparsity. and the weight of the basis network themselves are sparse, and the weight of the coefficient that combine them are sparse, that means that you will have 1,000 of this network, but you only have 5 basic ones active at a time. So you can imagine there is a giant virtual network that includes all of these sub-networks. And he thinks that this might one day be possible. You know, Bliss has this very interesting background studying bacteria and biology. So he made a very beautiful metaphor about what it looks like. And he said, and I think it's a bit like the way the metagenome of the bacteria work. He referred to this, the ground ecosystem. He said, you know, a fair amount of oxygen we breathe is created by a kind of bacteria. And it's very small scale of bacteria that live in the ocean. It is such a small bacteria that the length of the genome that every single one of them have is very limited. He said, but there are so many of these bacteria and they fill all of the ocean, including many niches of ecosystem. He said, so there is a meta genome, which is basically the set of all the genomes they have, which is much larger. And then he said, you know, with many, just like with many bacteria, there are this genome exchange kind of system that allow for genes to move, to do lateral transfer from one cell to another. So it's like a giant distributed organism that has a metagenome that is much larger than any particular cell that can actually express. So he said, you know, and the mechanism for swapping this gene around to him, that picture looks a lot like the federated learning with a kind of sparse. So he said, as a result, you know, we might have a giant distributed model that Professor Yang and him both are talking about. And Professor Yang at that point actually said, you know, this is really exciting. So it sounds like that the federated learning is like a living organism that can continue to evolve. He said we can even write science fiction about that. And that before writing science fiction, I actually further developed that. He said he can imagine this is not just the one meta system that can integrate everything. Because when you think of the mathematical model behind this, it is actually the principal component of a multiple dimension space and giving any collective behavior and collaborative behavior. There can be multiple basic sets, and each one can develop its own universe and many universes, so to speak, actually. And he said, you know, actually that also gives rise to our current universe. So we can see that, you know, there are many clusters and star systems, and it's very colorful. And he said he can imagine the federated learning system is like living in an ecosystem like that. So this is a kind of the ground vision and they have. I was really inspired by this. I have been thinking about it a lot. This is at the beginning of the year, and we actually said Happy New Year to each other, so I do remember. And I've read that conversation, I listened to it many times. And it's always delighted me to see, you know, these two very beautiful minds coming together and have this, the ground vision. So I have always been asking, you know, why can't we get there? And how we can get there? And that brings the question where we are now. So when Professor Yang invited me to give this talk, I said, you know, this is the opportunity for us to revisit this ground vision and see where we are now and what it takes for us to get there. So this is about the ground vision, and I want to revisit it. And following that, I want to come back to the question about where we are now. Because by doing this, I want to share with our audience, you know, the situation, the work we have achieved. And then I'll pose a further question about how we get there. I don't think we are here to give all the ultimate solution and answers, but we want to take this opportunity to actually inspire our community to develop it towards this ground vision. So I would want to start to ask Professor Yang to give us some idea about where we are now. And I know that Professor Yang has been really the driving force, and with a big community, excellent AI scientists like Professor Yu yourself has been working towards this open source community, and in fact, the ecosystem, and been building standards as well. So Professor Yang, would you like to give us an overview about where we are in terms of the building of the ecosystem of federated learning, and perhaps give us some idea about why you think of building that?
Thank you, Victoria. That's a very beautiful description of our joint vision. Indeed, to build this, so first of all, what we are aiming at. Now, computing has been through more than 60 years, ever since Alan Turing's vision for computers and Bill Gates' vision for computers to be on everybody's desk. But now we are facing a new generation, a new stage, which is how can we go from computers, computing power, and data that are individual on individual sites into a paradigm of shared knowledge. So knowledge is really what we are talking about. In view of AI, we finally found a way to distill knowledge from data. So now we have two entities. We have data that resides on everybody's phone, on every single silo in organizations, and we can have knowledge that are shared among a network, among multiples of sites that are interconnected. So interconnection is a physical way of ensuring that knowledge is created jointly and shared among multiple sites. But when doing this, we have to respect the individual's rights, such as privacy and security and ownership, and encourage incentive to be distributed fairly. So therefore, we have a strong need to arrive at a network of federated learning ecosystem. And so this is the background behind Victoria's thinking. Now, where are we right now? I can say we have made progress in several fronts. First of all, we have federated learning as being recognized by academics, by industry, by government organizations, and by almost every industry and society, such as the medical society, such as biology society, such as financial society. So that's a phenomenal achievement that for federated learning to be so widely recognized. Secondly, we have a number of very popular open source software. It is vital to have open source software platform to as enabler for federated learning, because at the beginning, everybody is stuck because federated learning is such a deep, multidisciplinary technology. You need to know encryption, you need to know security, you need to know AI, you need to know computer networks, you need to know databases, and so on and so forth. And you also need to know economic theory. And nobody is a master, is an expert in all of these. So therefore, it is important to enable the barrier to entry is low enough. And so therefore, open source is vital, particularly because security is at the heart of federated learning system. So it is important to invite everybody to come in and debug and find out where the bugs, potential bugs are. And so to have this healthy system going on. And thirdly, we now have a number of standards, one of them being championed by EEE, with which both Victoria and I worked on, and it was published last March. Since then, both at the national level in China and in international level, there are multiples of standards that are arising or are being created. Having a standard is actually very, very important, because it enables people to talk to each other. It's like before, you know, we had English language, Chinese language, and French. There may be a million different languages, and people find the Tower of Babel is so difficult to climb that they will collapse at the beginning effort. So now we have the standards so people can talk to each other. And also we have accumulated a number of important use cases. For example, the very first federated learning system used by Google for Android system is now being cited as horizontal federated learning. The organization-wide cross-silo federated learning system is now very popular as well, especially in China, to enable financial industry and other industries to interconnect. And these are called vertical federated learning systems. And there are transfer learning combined with federated learning in federated transfer learning to enable the heterogeneous federated learning systems to be created to allow different data sources to have different formats, different distributions, and to have different models even to let them interconnect and talk to each other. So we are, even though we are into maybe the 4th year of federated learning term being coined, we are actually very far along. But having said that, I should also mention that we are still very far from our goal, from our objective, which is to have a gigantic virtual model building facility enabled by federated learning. So just like Victoria mentioned, it's like a giant soup of bacteria and living mechanism that are interacting, that are evolving, that are creating new beings. To enable that to happen, we are still far. So we can see examples of computer systems which give us a insight into where we should go. We had a Windows operating system. We had Unix and Linux operating system. These enable individual computers to survive, to operate, and to compute. We had internet protocol to allow the internet to connect different people together. And we have, today we have IoT networks to allow devices to connect to each other. But we never ever had data networks that respect security and privacy, and that can automatically distill knowledge from the data, from the massive distributed data. And so federated learning allows that to happen. So that is a new civilization goal for the humankind, in my view. Victoria, I'll stop here.
Yeah, that's great. Thank you very much, Professor Yang. And also, I wanted to probably jump a little bit ahead and then come back again for the details, because I want the most important thing to be the first, in case we don't have sufficient time to discuss. That is, what are the conditions that you think we need to have or create in order for us to get to that ground vision in, for example, 8 years time?
Okay, what are the necessary conditions? So first of all, we should have internally, we should approach this grand goal from several angles. There's one dimension known as a technology dimension. So now we have, for example, multi-party computation, encryption software. We have the hardware devices for execution environment, and we have distributed computing for model building for AI. When we put all these together, we actually have the hardware and software infrastructure needed to create such a system. But today we are still in the stone ages of federated learning, or maybe a little far, but not too far from stone ages, because we are still building one-off systems. We still haven't turned it into an industrial platform where we have partitioned standard tools and individual building elements. So I used to take the analogy from making a city. Before we had industry, modern industry, when we build a house, we dig a hole in the mountain and think it's very secure. But the process is very slow. We can only dig a hole in 1 year. And so over time, we only dig a few holes. We are no longer, we are no near to a giant city. To build a giant city, we must have building elements like bricks, glasses, doors, and then we have a way to assemble them together. That's the way to scale up the city building, the infrastructure. But when we do that, we should be careful to have commonly accepted standards for safety, for livability, for utility, and so that is the soft part of federated learning building, and so we are still far from that. Another dimension is the government and legal dimension. We are very happy to see, for example, GDPR, CCPA, and the Chinese data security law are being enacted, and like laws, similar laws are enacted everywhere in the world. But to execute the law, to create cases where people feel compelled to comply with the laws and to embrace federated learning as their next software and hardware infrastructure, we are still far from that. So the legal and social aspect still needs a big push. So I can see these both directions needs to make major progress.
Mm-hmm. And relating to this, very key standardization and the legal requirements and the condition. I do recall that in your conversation with Blaise, you both uncovered the issue of the ownership of this planetary good, that is this virtue, federated learning ecosystem. What is your thought about that? It's about equity, it's about who owns it, and then you can incentivize people to actually build that. Is that a kind of key condition? What it should be look like in terms of ownership?
That's right. Yeah. So now we have IP right, for example, for audio and video products. We have IP right, even copyright for books, but we don't have copyright and IP concept for models. And so that is a needed element for federated learning ecosystem to grow. Because unless people can take responsibility and to be able to claim benefits from their teamwork, and such benefits are distributed fairly, people will not embrace the technology. So just like we have a real estate property, we have individual wealth protected by law. We also should have models and knowledge protected by law. So from the technology perspective, what we have achieved today are very encouraging. For example, recently, Dr. Fan and I have worked on IP right for deep models, and we have achieved quite a lot to enable multiple parties, I would say, genetic imprints to be embedded into a deep model, so that when the model is being used, you can actually use a detector to know which part comes from which creator in order to give them benefit, feedback, as well as assign blames when things go wrong.
That's very encouraging and very important.
Mm-hmm.
And suppose we build this one day, who do you think should own this giant system? Could it be owned, collectively by the contributor? Of course, the kind of technical solution you mentioned, and perhaps when we have copyright for the model, would help. And but would it be owned by certain entity or several entity, or is this like collectively owned? What it should be look like ideally for it to be doing the good for the whole human being.
Yes, I think we can take analogy from the internet. The internet is not owned by any individual or by any government or by any organization. It is collectively owned by civilization, by humankind. And so likewise, I think the future, a knowledge internet is what we are looking at, supported by a federated learning system, maybe a extended federated learning system that respects IP right, that encourages open source, that have legal protection and have individual rights, and all of these being owned by collectively by the community as a whole. And so in the past several months, I also was exploring along the side of how to build a ecosystem of organizations and people. So here in China, we have built a community, federated learning community for open source. It's known as Open Islands. Supposedly, if we have the individual closed silos and closed islands, we wish to build bridges to connect them. But then we wish this to be supporting an open source ecosystem, and to have not only large corporations, but also individual small and micro size companies, as well as academics and students to join. So right now it's very encouraging that we have more than 100 different organizations in this community, and it's very, very active.
Yes, I have noticed that. That's very impressive. And I noticed that there are new fees as well. It given a lot of emphasis on, to put it together a very proper structure. So you have actually legal professions, technicians and domain experts, and even regulators in that community. So I think it's very encouraging.
Yes. Yes.
And standards. This is what brought us together. So I want to ask a little bit more. Professor Yang, when you brought the standard to IEEE, how did you decide what you wanted to standardize instead of just leave it for the open source community to develop a protocol and technology solution or de facto protocol?
Yes. So I think we first approached each other probably 4 years ago when we first worked on the open source software. I immediately thought about having a reputable organization to help us build a standard, and we identified IEEE. And we are very lucky to have you in charge of this standard and gave us a lot of guidance. So the reason why we thought about it is because we thought hard about the business model of a open source software. So being open source, it is free and it's contributed by many individuals. But then how are people financially encouraged to benefit from it is vital, because otherwise it's not sustainable. So that led us to think about an open source platform ecosystem is more like creating a language. Let's consider when everybody lived in a small village and they didn't need to talk to each other at the beginning of history. And then gradually people start to communicate across villages, across continents. there's a strong need to have a common language so they can communicate with each other. Now, let's say a group of people then took the challenge and started creating a language. Should they charge everybody for the language? I think not, because a language, it should be a common knowledge. And so, but then on the other hand, how do you encourage this group of people to incentivize them to create more and more functions in the language? There are actually several ways for people to benefit from creating a common language. One is education. So now we have schools to teach languages. We have teachers, and we have education programs. We have books on learning languages. That's one way. Another way is consulting, is for people to use languages in different disciplines properly, such as in medical, in science, and in politics. Then we have language will develop into literature, language will develop into arts, into poetry, and so more byproduct will be created, and they will feed back to the creators of the language. So open source business model, I think, is more like a business model for a language, for creating a language. So that's the answer to your question. So that is why we thought about having a standard is the very first thing for such a language to be widespread.
And Professor Yang, given that we don't have a lot of time, so finally, I just want to call more people to come to contribute to the ecosystem, the open source, and also have you on your mind? Of course, I know a bit further projects of standardization that you would like people to pay attention and join, because it is not just one or two. I think it's a set of standards and codification we're considering.
Yes, standards on one thing can be a guidance. On the other, it has to be executable. Let me give another analogy. We have cars running on the road, but we have to ensure the safety of the car. So there are government organizations that certify the safety of car every year. So once you pass the exam, you put a sticker on the car so it can continue to run for the next year. I think we should have similar organizations and mechanism for federated learning for ensuring its safety and efficiency and usability. And such a thing has to be created in order for the car of federated learning system to be running in every highway. Therefore, we have to have a standard that is checkable and estimatable on standard, on safety. So we can have safety based on potential threats, based on models used, based on federated learning systems and security measures you have, and finally, based on the utility of the model. And so once we fix all these, we can give the system to a certified organization to give a certification and for other people to trust the system. So we have yet to build such a certification, and I hope you or IEEE can help us in making progress in this direction.
It has been a privilege to be able to support you and the community to develop that. And I want to ask actually, Professor Yu, how are we doing with time? I know we probably are a little bit over the time.
Yeah,
and
it's okay, maybe just overrun by a little bit, we can still manage.
Is that, so we run out of time, right?
Yeah. It's we can.
It is all time just fly by so fast when you talk with Professor Yang.
Yeah.
Because this is full of inspiration
very
in
inspiring.
the conversation. I really enjoy
Victoria,
that.
if there's something important that you still want to discuss, so you can still continue.
I have probably more than 20 questions. So probably we can't finish all.
One last one, the most important one. That our participant can benefit the most.
Okay. So Well, that's something interesting. I want Professor Yang to give a little bit, observation. Not every, standards has very different culture from the culture of open source style. So do you find that they are actually complementary to each other? And do you find that actually it's very difficult for the AI scientists who have get used to the open source culture to work on standards?
Right. I think you are very right. On one hand, we have to build standards so that we can have scalable construction of federated learning infrastructure. And many enterprises and companies will be very eager to get into it, because by mastering and leading a standard, they can actually benefit from patents, from services that they can provide. On the other hand, open source has been championed by academia, especially people who are active in computer science. For example, in AI, TensorFlow has been dramatically enhancing the usability of AI software, enabling lots and lots of ideas to be quickly tested, and so that's a big moving force behind AI development. But these two are really the different cultures behind industry culture and academic culture, and now the line between them are blurring. So some industry people are doing academics, like industry labs, and academics are doing industrial research, which is a good thing. This enables us to mix the building of standard for profits only and open source for the benefit of humankind to be mixed together so they can respect each other. So in the future, I can see these two communities will find a common ground to find a proper balance of the goals on two goals. One is to make profit, another is to make progress.
Yes. And also I found that the open source community has the culture of, based on the merits, who developed the best technology, everybody use, then that's it. Everybody use it. And in standardization, it is based on consensus. It's about, people have to vote finally, maybe 75% people agree and 50% agree. So you have a compromise. It's a little bit different culture. And it could be very fascinating to see how it converges. And of course, in standards, people would normally vote on the merits. So there is some convergence there as well. So, but anyhow, I do notice that, and I thank the generosity of Professor Yu to give us, a little bit more time. We have a lot to talk. So I would rather think this one is a tease for a series of talk of how we build towards that grand vision that benefits the planet, the human being. I know we're going to have more conversation, and Professor Yang, thank you so much. And thank you so much, Professor Yu, and all the audience.
Thank you, Victoria.
Thank you very much for the inspiring talk. And really gives us a glimpse into how communities and ecosystems can be built from the ground up. Thank you very much. And once again,
thank you.
We really enjoyed the time.
Thanks.
Thank you. Okay, next we have our fifth invited talk given by Professor Martin Jägi from EPFL Switzerland. So he's a tenure-track assistant professor at EPFL, heading the machine learning and optimization lab. Before that, he was a postdoctoral researcher at ETH Zurich, at the Simons Institute in Berkeley, and École Polytechnique in Paris. He has earned his PhD in machine learning and optimization from ETH Zurich in 2011, and also a Master of Science in Mathematics, also from the same institution. Okay, Professor Jägi, if you can share your screen. Okay, now we can see it. Okay.
Thank you so much.
Please go ahead. Thanks.
Does this work? So
yes.
thanks so much to the organizers for this great workshop and also for inviting me and for the inspiring discussions. So I hope this will be a bit a natural continuation of the discussion we had, because we heard a lot about the security and trust aspect of like federated learning, and I want to continue a bit on that, talking about the Byzantine robustness, like learning in the presence of malicious agents, also to give people more trust into federated learning. And then in the second part, I would also talk a bit more about collaborative learning. So the outline will be this one, that first we would talk about Byzantine robustness in one aspect in the federated setting, and then in the second aspect also in the decentralized learning setting. And then in the second part also to talk a bit more about collaborative learning, in the sense that when every learner has their own objective and there's not necessarily a server present for coordination. So this will be the plan for the next 25 minutes or so. And I guess you are all already very familiar with what federated learning is and the few variants of it. If we are collaborating, we are a certain number of devices or users and exchanging updates for getting a best possible model, which is either then communicated with the server or maybe directly between the devices. In both settings, the goal is the same. Usually the goal would be to achieve the same accuracy as if all the data would put in one place. So we want to be as good as that, but we want to keep the data on device to respect privacy. The tools we're going to use for that are also very standard. There's nothing new on this slide. I will hopefully not have too many scary formulas. So this is just standard stochastic gradient descent, which you're doing. The point here is that every device only has a subset of the data points, so that we have to work with those gradients which are coming from that device, and we can communicate them to other clients or to a server. So this will be the basic building block. But what we want to study in the next few slides is going to be the robustness aspect of these training systems, to see how easily they break down if some clients are present which are trying to break the system, or are maybe just not stable, so that they might not intentionally deliver still bad updates or be unavailable. So that's like the client on the left, the unstable client. So if such a client is present, does the federated learning system still work? And then the slightly more difficult case, if clients are really malicious, like they're trying to send the worst possible updates to really try to derail the training, try to make it fail, such that the resulting model might not be correct anymore. This is the goal of Byzantine robust training in the federated setting. There has been a lot of work in this topic. I think it's interesting because it really relates to the trust that people have in such systems. Traditionally, if you don't care about robustness, we will just aggregate the received gradients as normal, which means that we would just average all the resulting gradients that we receive from our clients. So the average, as you know, is not a robust estimator. What does that mean? That what I'm trying to say is that even if there's just one malicious gradient here, it might arbitrarily change the result. So the result being the average. So the average doesn't have any statistical robustness property, and that's what used in federated averaging, right? So this is the problem we're trying to solve. So what people have done is they would try to replace this average with other averages. The idea is basically to use a median instead of a mean. So the median is a robust estimator, right? So those entries which are exactly in the middle, that there are equally many entries above and below the value. It's clear for if we're aggregating numbers, but here we are aggregating vectors. So what people usually do is a coordinate-wise version of the median, for example. If we mention a few more examples, that there's been a lot of such aggregation rules. They're not only doing median, but there's very many variants of it, like geometric mean, and also this early work CRUM, which was the first aggregation rule, which is trying to really give such a robust aggregator. So this seems all fine. So you could ask, are we done already? Have we solved the problem by just plugging in the median? But the problem is it's actually not that simple. This would not solve the robust training yet. And the problem is the following. So why on this slide, the title here is that because there was the title of a paper which pointed out this problem. And the problem is that you might as well be robust in one aggregation round, right? So this is what we said we want to achieve, because you use the median in your round. So the round is now robust, which means that the result you get should be close to the desired result if you have no Byzantine actors, which is the case. The problem is that we're not just doing one round, we're doing many rounds in federated learning. So, and that's why just being robust in one round is not going to give you the guarantee that the final result is going to be the same result as you have no bad actors present in the training. So there's like two papers which pointed this out. The one we mentioned already, and the point here is that those attacks are time coupled. They have the ability to change you a very tiny bit in each round, but what they're clever in the sense that this direction which they try to pull you, I mean, the adversary tries to make the model go in a certain direction, and the adversary is smart enough to keep that direction correlated over all the rounds, so that by even making only very small changes in each round, there's very limited effect in each round. But the effect over the entire training with 10,000s of rounds is very substantial, which then still destroys the training and gives a wrong model at the end. So this is a problem, and this actually can be formalized to show the failure of basically all the existing aggregation rules for robust training, namely the ones which did not use the history of the training, which means the ones that do not remember of the history of each client giving you the gradient. So if you don't remember which client gave you what, there is no way that you're going to be able to find a robust training. So this can be written as a theorem that they will fail because the attack will be able to imitate other clients and so on to slowly derail the training. So this is bad news. We cannot have robust training. But the good news is that we can fix this by actually having aggregation rules which do have memory, which do remember the time aspect, which do remember who sent what over the past. And the way they use memory is really simple. So it's really the simplest thing you could use to use history. And that is to use momentum. So the momentum here is local on each worker, so that every worker in each update round, they do some update, which is G here, but they also do remember what they've updated last time. So this is exponential moving average happening over the past gradients that we applied, so that we keep moving in the same direction we have moved. And the good thing is that we trust ourselves, right? As one of the, if you see from the perspective of a good worker in such a system, they know that their own gradients are correct, right? We are a good worker, we play with the rules, so that the good workers are trying to be more confident in their own updates to actually then also use those to actually detect the what are the bad updates. So this just uses the past gradients, averages them. And instead of doing the robust aggregation on the gradients, we do it on this stabilized version, which is the momentum version, which is much more stable, much less noisy than the original gradients. The aggregation rule is simple. There's not much we need to do there, but the trick is really that we need to remember the history by using the momentum. The aggregation rule itself is just clipping. So it means we do not trust when we receive gradients from someone who is very far away from our gradient, or our stabilized gradient, if you want. So the question is, what do you use as a reference point? And that's exactly the same thing as we discussed before. So this momentum stabilized version of our own updates, this we use as our reference point. That's the point GI here, which sorry, V is the reference point. So V is the center we trust, and that one will enable us to actually have a robust aggregation rule. So of course we can do that, but why is this better than other rules, or can we trust this, right? It shouldn't just be an empirical study, but hopefully we could convince people that robustness is there by giving theoretical guarantees, and that's what I want to discuss next. So the guarantees we can give are quite strong, and they are in the same in the sense that the result of the training will be basically the same quality as the result when you have no bad workers, when there's no Byzantine clients in the federation. What he's saying here is that an aggregator needs a certain property, which we call this delta C robustness, which means basically that the aggregator is kind of a constant multiplicatively close to the one if there would be no present malicious workers, which is the case for the aggregator I just showed you before. And then if you have that, then you get the optimization conversions for entire training. But there is a limitation here that we are only allowing a certain fraction of Byzantine workers. And this is completely standard in all Byzantine results. Also, if there is all literature as well about reaching exact consensus in Byzantine settings. And the key quantity there, and also for us, is always like, what's the percentage of the bad workers in the federation? So that's delta. Otherwise, it's a completely same assumption as a standard stochastic gradient descent, so sigma square variance. And we get these conversions on non-convex objective functions, but they need to be smooth. So then we have convergence to a stationary point, basically to a small gradient. The nice thing here is that also this convergence becomes faster the more workers are present in the federated learning. So that's n is the number of workers. So we see if there's a very small fraction of Byzantine present, then we get a very nice speed up with the number of participants. So if delta is very small, then we would be almost 10 times faster if you have n equal 10, right? If you have a lot of helpers in our system. However, if the fraction of Byzantine workers is substantial, maybe 1/2 of the participants, actually that would be too much for our theorem, but hypothetically, then you can see that you do not get much speed up anymore as soon as you reach maybe a similar number of co-workers as 2, then the speed up is going to diminish. But still, it's a speed up, which is going to be more weak. So this is nice because it really is the kind of first provable conversions of training in the robust setting under standard assumptions of SGD. So we can trust this, which hopefully people will be a bit more convinced that they should use these robust rules, and hopefully more trust that the system is going to do its job, right? Which is it should deliver the same quality solution as without Byzantine workers. One caveat as well is that this theorem here is for the IID data case, and we do have an extension paper where we do almost the same result for the heterogeneous data case, which is an important case. And how we do there is that there is an additional small sampling step before then this machinery here is applied. And the step that is additionally done is that instead of just aggregating everyone's gradient, you first try to form a subset or a bucket of a few of the gradients, because you hope that the few which get into the same bucket are already representing the heterogeneity of your data, so that you don't have only one strange worker and you're trying to aggregate it. Because the problem is it's fundamentally impossible to distinguish a genuinely strange worker from a malicious worker, right? This is a definition question. So what you show then is if there is a bounded heterogeneity, then this theorem basically applies, but you go to actually only a neighborhood of the best solution. And this neighborhood depends on the level of heterogeneity you have between the good workers, right? The Byzantine ones can be they can do whatever they want. They're not bound to any assumptions. So this is about robust training in the federated setting. Are there any comments and questions on this one?
Okay, thank you, Professor Jay. Yeah, any questions from the audience? If you have any questions, feel free to unmute and speak, or type your question in the chat. Yeah, Professor Jay, we did some work in terms of making federated learning more robust. We had some experience guarding against external attackers from eavesdropping on the communication channel and try to manipulate the gradients that are sent back and forth by purchasing the service of a signal jammer. We try to optimize that we model that as an optimization problem to see how much money we are willing to pay over the long term, and at any given point in time, how much jamming we would need in order to prevent external eavesdroppers from knowing there is a federated learning training taking place, while still enabling our participants to be able to complete the training. So this is from a different perspective. I see there's a part of your slides talking about the clipping the gradients that are received. I wonder if in the case there is there are some hard samples in the data set to be learned, which could cause the gradient to be larger. Would this method be able to distinguish this situation, or are you assuming there is no such thing present?
Yeah, thank you for the question. This is a great question. If we could even ask about standard SGD, like if we add clipping to the standard SGD, is it still going to work? Is it still going to go to the same solution? And the answer, I think, is no. In general, it's not really the same. Although if you look at, for example, Adam, the Adam optimizer is basically almost the same as clipping to 0.1, so it's very related. But they might sometimes go to a different solution. But here, if you add the momentum, then actually we can show that they go to the probably same solution as if you have no clipping. It's just the intuition is that it's just gonna take a little bit longer to converge, because maybe, as you said, there might be one gigantic gradient and I clip it, so then but what's happening is that I then would just have to revisit that data point maybe 10 times to get this 10 times this radius to then result in the true magnitude of the gradient. So, but it probably converges to the same result. So that's nice in this case.
Yeah,
thank you for the question.
Any questions from the audience? Okay, so if there's no more question, thank you again, Professor Jackie, for the interesting invited talk.
I have a few more slides. If do you have time for?
Sure. Yeah, we still have time.
How much time do we have left?
5 minutes.
5 minutes. Okay, I'll do quickly to show you that this can also be extended to decentralized. The result we saw.
Yeah, thanks.
I just want to briefly mention that, yeah, the decentralized setting is also interesting in the robustness setting. That can we be robust if you're in a decentralized setting where users directly exchange gradients with each other, but now a user is still maybe a Byzantine user. It's really interesting here what the topology of the graph now comes in, because this Byzantine user here is not so bad. It's not having a big impact because the good ones, the green ones, are still, everyone is connected to each other. But now if I have this one being a Byzantine user, then this connects the good ones into two components. So there is a big impact that this Byzantine user can have. So we have a result which combines the topology with this Byzantine robustness. And it turns out that now it doesn't matter anymore what is the fraction of the percentage of Byzantine workers overall. What matters now is that the weight that among your own local neighbors, how many of those are Byzantine and how much weight do you trust them? So what we can get here is basically the same kind of result as showed you before, but the results are kind of a bit stronger because, again, by trusting yourself more, you can even have robust convergence here, even if you have a kind of infinite number of Byzantine workers. Even if the majority around you is Byzantine, even then this convergence might still work because you will just give a little bit more self-weight to yourself in the gossip process which underlies decentralized SGD. So, and we also have a text which show that it's kind of unavoidable that topology matters a lot if you do a decentralized Byzantine robust training. So this was this, and if I have maybe 2 minutes, I would just talk maybe about personalization just very briefly to take a step back to see a bit the wider context. Is we have made a lot of progress by going to federated learning, right, to have really tremendous benefits in terms of privacy and enable new applications. I mean, federated learning is going to stay for sure, and there's lots of applications which are solved by it. I just want to, in the longer term vision, also say that there might be there is also a few applications where we do need to go a step further to actually enable use cases. If there's a use case for which there's no central server defining the objective, if the users themselves want to team up, bottom up, and design hey, let's train something together, but they did not find a central entity which supports the training task. So the user each have their own training objective. They want to decide who to work with. So in that setting, we are a bit more in this collaborative learning setting. There's a similar evolution also in the internet, which was also mentioned before. In this setting, we have every worker having the same. In Federated, there's a shared objective, right? And in this setting here, the key difference is that every worker has its own training objective, its own loss function. It's completely different training task. Like maybe I have a classifier, I want to learn about chicken and ducks, and maybe you have a completely different classifier. You want to learn about cars and boats. But there's still a valid question if you can collaborate, if you can be helpful. You can be helpful for my objective F0, I can be helpful for your objective Fi. And the question is if you can get a speed up in such a setting. To get speed up in training, which means we get help from our collaborators to do faster training. It's also related to mean estimation. Can you estimate a mean of some random samples more quickly if you get additional random sources from a different distribution? Because here it's really key that the data is very heterogeneous on each worker. A very simple thing is just to average the gradients you receive, but then you might need to figure out how much you want to trust them. So there's kind of a selection going on here, which is maybe in this alpha coefficient. You need to figure out who to learn from. One way to do that is to also try to learn how much different are those workers from your objective. So to learn kind of a bias correction, to have a difference vector, which maybe describes the difference between your own gradient and the gradient of your collaborator Fi in this case. Our objective is to minimize F0. This is similar to scaffold in federated learning. And we also analyze this, and we can see that sometimes under strong assumptions, if the objectives are sufficiently similar to our objective, if you have a selection mechanism to only select workers which have high enough similarity to us, then we can get a speed up from these collaborators. So here it would mean that we have n collaborators and they have a Hessian similarity to us, which is very small. If we have such a selection mechanism to select the useful ones, then we can get a speed up in training, also in this more general setting of collaborative learning. That's almost all I have. We have a JavaScript library for federated learning, which I wanted to mention. Allows both federated and decentralized. It's completely open source. And what's special here is that I think it's the first one which is purely written in JavaScript. It's not because I would really prefer JavaScript, but it's because it's really good for mobile support and running in the browser. Everyone can just run in the browser and collaborate on their phones or anywhere where JavaScript runs. We also support secure aggregation and differential privacy, and we really would encourage you to give us your feedback and play with it. And it's completely open source under this link. And that's all from my side. I hope I didn't use so much time, and thank you so much.
Yeah, thank you, Professor Jackie. A very interesting follow-on talk about the robustness against Byzantine attacks. I'm wondering, in the distributed setting, I think there are additional steps people need to perform in terms of discovering who are their neighbors, who are in the network they can collaborate with. I don't know whether there is assumed to be any lookup table where they can find others, or is this supposed to be done also in a fully distributed fashion? And if that's the case, if that's the case, there could be some trade-offs in terms of the cost involved. Whether if everyone fully relies on themselves to make a decision as to who are potentially Byzantine users, they could take a lot of communication rounds and a lot of trials. But if there is some kind of a word of mouth or reputation system going on, which can allow people to reduce the cost in this respect, you also need to worry about people colluding in terms of bad mouthing or ballot stuffing other people's reputation. So I don't know whether you have any thoughts on such issues.
Yeah, that is very interesting. So actually for the setting here, when we robust, clipping is actually enough. We don't need an additional selection mechanism, so clipping works. But you also mentioned that the topology of the graph, right? So in that setting, it's a bit limited because we say the topology is given by nature, right? It's maybe a physical network that has been given to us. Maybe the fiber communication links between all the continents, or if you have Bluetooth. So these are physical constraints, right? There you actually have already a set of neighbors which cannot be physically overcome. So even the Byzantine ones, they will be somewhere in this topology. They can choose where they want to be. So that's about that. But then about the selection mechanisms to select useful clients, which are particularly helpful for your own task. That is indeed harder. That is harder than to just filter out Byzantines when everyone has the similar task, right? Because we have bounded heterogeneity. So if you have unbounded heterogeneity, everyone has completely different tasks, then you're right, then you need a selection mechanism. And that, I think, is a really interesting research direction. And I agree with you that maybe a credit system could work there. But that is difficult. I agree. Yeah. So.
Okay. Thank you very much, Professor JD, for the interesting talk. Thanks so much for joining our workshop. Thanks.
Thank you.
See you. Yeah. So now we can move on to our paper presentation section. So may I invite Dr. Tiu Xingyi from A-Star to be the chair for this session. Dr. Tiu?
Yeah, thanks, Han. Can you hear me, right? Yeah.
Yes. The floor is yours.
Yeah, so I think we go to the second paper because first paper request to do it later. So we invite the second paper about privacy preserving federated cross-domain social recommendation. So we invite presenter Jianbing Cai. Jianbing Cai, you can share your screen and start your presentation. Yeah.
Oh, yes.
Yeah.
Okay. Let's start.
Yeah. Can you share your screen?
Okay. Wait a minute.
Yeah.
Okay. Can you see?
Yes.
Okay. Oh. Sorry. Okay. Let's start. Okay. Hello, everyone. My reported paper is Privacy Preserving Federated Cross-Domain Social Recommendation. I'm the first author, Cai Jianping, and the corresponding authors of this paper are Liu Yang and Liu Xiwen. First, let's see the background and motivation of research. Many works have shown that social networks can improve the effectiveness of recommendation systems. But unfortunately, user feedbacks and social networks often don't come from the same websites. Besides, due to some policy and privacy protections, most websites cannot sell their user information. Okay. Based on the above background, the following reasons motivate us to study this work. One is federated learning can promote participants who cannot sell data to build federated recommendation models. Another is the application of federated learning on cross-domain social networks recommendations still face multiple challenges. Okay. Here are the challenges we faced. First, existing centralized social recommendation methods cannot be simply extended to federated cross-domain recommendations. Second, how to ensure the security of the user's individual privacy in social networks while federated cross-domain recommendation learning. Third, some privacy preserving techniques trade off the cost of significant computational overhead to secure local data, such as homomorphic encryption.
The latter is social networks are often large scale and sparse. Whether they can be processed efficiently determines whether the algorithm is practical or not. For the above challenges, we give the following solutions. First, we propose a learning model for federated cross-domain social recommendations. Second, we introduce random response mechanism to preserve individual privacy in individual privacy for social networks. Third, I propose a matrix confusion method to efficiently update encrypted user filter vectors. Fourth, we apply LU decomposition to improve the computational efficiency of large-scale sparse matrices. Okay, let's see the system model of our work, FCSR. And so in the figure, we consider two federated learning participants, which are the information-oriented websites and the social service platform. Their shorthand are IOW and SSP. IOW holds user item ratings to realize recommendation systems. To systems, it has the service requester in our model. An SSP holds the user social connections for improving the recommendation quality, which is the service provider in our model. Okay, for the system model above, we designed the workflow with the following main steps. First, IOW built a cooperative filtering model such as NCF SVD model. Second, SSP generates social networks with uniform differential privacy. Then they apply PSI to find the common users. In the training loops, IOW trains CF model and upload encrypted user filter vectors, and then SSP update user filter vectors securely by the noisy social networks. Finally, after receiving update user filter vectors, IOW restore it and finish the training step. Okay. Let's see how we apply random response mechanism to achieve differential privacy for social networks. And so in the flow chart, we regard each social connection as an independent random response, and then return fake social connections with a certain probability. Here, we have two issues. One is the density of social networks was significantly changed after sanitizing. For this issue, we calculate the noisy density law with equation to differential privacy, and then keep the density of the sanitized social networks by post-processing as noisy row. Okay. Another issue is all connections are so numerous so that it is inefficient to perturb everyone. So we apply the binomial distribution to achieve equivalent perturbations for reducing the complexity. Okay. Next, I introduce how we update the user filter vectors. The idea refers to this work proposed by Wang. It considers two object functions for smoothness constraint and keeping the consistency of the user filters as these formulas. Notably, the updating has an analytical solution such as the formula. Okay. Based on the above updating, we propose a matrix confusion method for encrypting user filter vectors. Also, in this figure, IOW randomly generates a matrix file with the sun shape of the common user feature vectors you see and stacks them horizontally. Then multiplies a random matrix. The random matrix right to obtain UC and then upload it to SSP. And then after updating, SSP multiplied by the inverse of phi and then retain the first decoherence as the updated user filter vectors. There is a problem. Since the analytical solution involves the matrix inverse, even if the social networks is sparse, the updating for large number of common user vectors still face huge computational challenges. So we apply LU composition to keep the sparsity. Here, we attempted for LU decomposition methods and find the decomposition P3, that is the median degree ordering on the structure of Q18. Its transposition has the least density as this table. Okay. The last part is our experiments. We adopt 3 classical datasets for testing, which are Trustworthy, Trust, KLDVD, and opinions, and their details are as follow table. Okay. In the first experiment, we evaluated the training effect with RMSE. The results showed that the cross-domain federated learning based on social networks effectively reduced the RMSE on the test datasets. As emission increases, RMSE tends to decrease overall. That means more accurate social networks lead to more accurate predictions. And smoothing constraints with higher weights can reduce the RMSE more, as this figure. Okay. The second experiment, we compare our FCSR with the existing schemes. which are FED-MF, FED-GNN, and FED-SOG. The result shows that our proposed FGSR significantly improves the accuracy of existing federated schemes on all three datasets. That our FGSR is effective and practical. Okay, and that's all. Thank you.
Thank Jianping. Any question for Jianping? Jianping, may I ask, right? In this, in your approach, right? Do you just use differential privacy? Do you using any other encryption scheme, or just differential privacy in your approach?
I use my work is use differential privacy and then try to do some things to improve its efficiency.
Okay. I think audience, you can still ask question in the chat box. So thank Jianping. So we invite for next paper. Let us invite for next paper, T-based cross-silo trustworthy federated learning infrastructure. Let's invite the speaker, Wei Yi. Wei Yi, you can share your screen and share your slide.
Okay, yeah, can you hear me?
Yes.
I think do some wish. Okay, let me share. Yeah, can you see my screen?
Yes.
Okay, thanks, Chairman. It's my honor to present my paper in this workshop, and our paper introduced our paper introduced a TE-based cross-silo trustworthy federated learning infrastructure, which is an excellent pipeline protection, including runtime environment and all data like input, output, intermediate data protection in all parties. And our team are from many business units of Intel, and I'm from Intel PRC Data Center AI support team. The motivation of our work is first, federated learning itself may not be secure enough and needs to be enhanced by confidential computing technologies like MPC, HE, DP, etc. And second, we want to use confidential computing. We need to balance security, accuracy, and efficiency. And we all know that TE is a high efficiency confidential computing method. Although there are quite a few TE implementations as we list in the paper, we didn't find a TE-based federated learning infrastructure is developed with integrity check, runtime protection, and remote attestation so far. That is why we developed this infrastructure with all these features. In our implemented infrastructure, AI framework are running on label-as gramming in order to minimize the change of the application. This implemented infrastructure can be modified and adopted for commercial usage. Here we introduce the infrastructure to enable trustworthy federated learning over multiple organizations with the help of SGX technology. So the data provider can secure their data from illegal usage. The federated learning cluster is composed of two types of workers, governance workers and compute workers, both secured by SGX, which are distributed over each organization. The governance worker is to attach the compute worker within the local organization, as well as the governance workers across the other organization, and manages the secure communication across the compute workers of different organizations. The compute worker is to run the core business like federated learning process, etc. As the SGX enclave size of the third generation Xeon scalable processor increased up to 1 terabyte, we can redesign the FL infrastructure for more workloads. All the enclaves do remote or local attestation to prove themselves, which prevent malicious or even malicious collude to data or program an enclave on the fly. SGX has integration check of the loaded data and the program, so the infrastructure is more trustworthy. Within our FL infrastructure, a trusted third party is not needed. A large but protected aggregator by TE can be deployed to any party. Once a governor worker is started up, it should perform a bi-direction peer-to-peer remote attestation with the governor workers from the other organization. In consequence, the governor workers from all the organization forms a trusted cluster. When a governor worker gets started, it should upload its metadata to the storage service. Here, a storage service can be any kind of service which can be accessed by all organizations. In our infrastructure, we use the blockchain as a storage service so that we do not rely on any other third party. The metadata may contain the information shown here. After uploading the metadata to the storage service, the governor worker will pull the list of governor workers of the other organization from the storage service and perform the peer-to-peer attestation one by one. The detail of the attestation process is given in the algorithm shown in the right side. And all the compute workers within one organization are managed by local governor worker. Once a compute worker is started, it should register itself to the governor worker. To achieve this, the compute worker should send the metadata detail to the governor worker, and then bi-direction peer-to-peer attestation is performed between the governor worker and the compute worker. If the registration succeeds, the governor worker should upload the metadata of the compute worker to the storage service so that the other organization can be aware of it. Please note that the attestation among the compute workers are not needed. Since the compute worker trusts the governor worker, it should also trust the other compute worker attested by the governor worker. So by this method, we can add and remove the compute worker within the cluster easily. All we need to do is to upload the list of the attested compute worker within the governor worker. Moreover, since the encrypt keys and the verification keys are generated randomly and protected by SGX, we can upload the keys of the SGX workers without the help of certificate authority when this key expired. The communication among the SGX workers can be conducted over untrusted network. The randomly generated keys of the SGX workers help protect the privacy. We implemented 3 workloads within our infrastructure, just 3 demos, which is ResNet Collective Machine Learning Network and Horizontal Federated Learning for using the 3D UNet or BERT-based models. We evaluated the workloads in our infrastructure from 3 perspectives, the correctness, performance, and security. For correctness, we run the ResNet Collective Machine Learning on Linux system and also running in Gramming without SGX, and also the Gramming with SGX, respectively, to compare their final loss and accuracy. The execution either on Linux or in Gramming are in plain text, while the execution in Gramming SGX is protected by hardware encryption. For performance, we also measure the time cost of 3 workloads. The figure here shows the time cost of the 3 workloads when running in different environments, all over 60%. For security, we simulate the attacks by grabbing the training status and the model weights in the memory space of like a BERT-based federal machine learning running in multiple parties. We also did a memory attack check with the implemented infrastructure. We dump the memory during the training process on the collaborative node and aggregator locally. When running in Grameen directly, all the data like training status, training data, model weights can be easily got from the dumped memory, while nothing will be exposed when all this running in SGX. So in summary, we implemented a TE-based cross-silo trustworthy federal learning infrastructure. It has the following major advantages. This is an excellent pipeline protection, and the infrastructure is with very high efficiency. The efficiency of our tested workload is at least 50%. Actually, it's even 60%. And the infrastructure is easily deployed. We support Docker, and we have set up GUI embedded. So far, no federal learning infrastructure can be 100% secure. If we want to promote the security, more confidential computing technologies could be used together. TE-based federal learning is not conflict with other confidential computing technologies like MPC or HE, etc. They can be combined to the infrastructure to generate a better solution for a dedicated task. The limitation of this implemented infrastructure, we need a CPU hardware support SGX features. Right now is the third generation Xeon SP. And the second, the infrastructure does not support heterogeneous computing platform. So our future work include like we can add a disaster recovery module into our infrastructure to add and remove nodes with primary nodes, like recover from the blockchain. So far, we also can implement the infrastructure through the attestation as we customer wanted, because right now the infrastructure do attestation only when started. To be more secure, the infrastructure can add a timer according to customer settings. The overall performance could be also further improved, like the optimized network communication. So far, the source code and the doc image of this infrastructure will be shared under the non-disclosure agreement. Open source will be scheduled according to the market's feedback. Okay, that's all for my presentations.
Okay, thanks, Wei. Open to floor. You got any question for Wei? You can open your mic or type your question in the chat box. I think no question. So Wei, I got one question. Normally, you know, for TE based, right? Still have the kind of the signer channel attack. Do you try with that one as well? When you
actually, we have fixed all the known issue of the side attack. If we actually this is protected by the chip itself. We didn't test this, but our SGX team will test the attack. Yes.
Okay. Yeah. Okay. I think no further question. Thanks, Wei. Okay. So our next paper will be the called the robust one-round federated learning with predictive space Bayesian inference. I think presenter should be Mohsin Hassan. Mohsin Hassan, can you share your slide? Yeah, thanks.
Yeah, are my slides visible?
Yeah, can see that, yeah.
Okay. So I'll be covering the work that I did with others at Waterloo and Huawei. So let's get into the problem setup. So just to recap, I'm sure everyone is familiar with federated learning, but in federated learning, we have this global data set that we've split into shards for each of the clients. And the distribution over this data set might be the same among different clients, or it might be different. So depending on the setting, we can say that we're in the IID or non-IID setting. So current approaches to federated learning mostly involve some sort of optimization algorithm in that we try to approximate an optimization algorithm run over the global data set, but we're basically doing some sort of local optimization to approximate that procedure. So for example, federated averaging is the classical FL algorithm, and this starts from some set of model weights, and over multiple rounds of communication, it'll communicate these weights, do some local optimization, and then aggregate them back at a server. So I'll highlight two issues with these current methods, with federated averaging and its variations. One of them is that these methods require multiple rounds of communication in order to work well. And the reason is that the sort of guarantee, the optimization guarantee, happens when we only do one step of local optimization. In that case, federated averaging becomes equivalent to just running SGD on the global data set. And if we wanted to try to be more efficient by reducing the number of communication rounds and increasing the number of local optimization steps, then federated averaging can start to diverge in the heterogeneous data setting. And the more local optimization we end up doing, the less stable federated averaging is in the setting. The other issue with these techniques is that they're trained by some optimization algorithm, and they generally aren't robust in terms of uncertainty. So, for example, when we train with maximum likelihood, that can be prone to overfitting. So if we have a small data set, particularly on a client, we might overfit to the data on the client. And it's also well known that especially models like neural networks tend to give inaccurate uncertainty estimates when they're trained with maximum likelihood. So in particular, they're overconfident about their predictions. So here I have an example where in the first case, the network predicts this person as the labeled dog and is very confident in its prediction, 98%. And on an actual dog, it's also very confident. So to go about solving these problems, I'll discuss Bayesian inference. So Bayesian inference is essentially a different way of learning a set of good model weights. But instead of learning a single set of model weights through optimization, we instead want to learn a distribution over the weights. And this is called the posterior distribution. Here I've just written it as P of W given D, the conditional distribution. And it's called Bayesian inference because the way we go about getting this posterior distribution is by using Bayes' rule. So if we have access to this posterior distribution over the weights, then we can compute a distribution over our predictions. And this is known as the predictive posterior. The way we do that is by computing this integral, integrating out the weights. In practice, we can't actually compute this, and we instead try to obtain samples from the weight posterior distribution and then approximate the integral with samples. So it just ends up becoming this summation. So what's the point of all of that? The point is that with Bayesian inference, we get accurate uncertainty estimates. And if we have accurate uncertainty estimates, then it'll also be difficult for a model to overfit. So for example, if you look at the figure here, this is an example of doing a regression task with Bayesian inference. So the green data is the true curve. The red line is the mean of the predictive distribution. And the light red around it is a measure of the uncertainty of the predictive distribution. So the blue point is basically a noisy observation. It's a data point that we get. And we can see that if the model is only given a single data point, it will be more certain near that data point, and its uncertainty will increase away from it. So we see that in the other plots as well. As we give it more data near the regions where it sees data, the model is more certain, and away from them, it's less certain. So this sort of behavior is particularly useful in federated learning because an individual client might have a very small data set. So now we get to our method. The idea of our method is to approximate this global Bayesian predictive distribution given the local predictive distributions. And the main sort of result, the derivation in our paper is that we can factorize this global predictive distribution into a product of the local ones divided by an additional factor. So because, so this factored expression is easy to work with because y is a low dimensional quantity, it's the output of the model, and we can make approximations easily to this sort of distribution. So our algorithm works by, for each client, they'll run some sort of MC-MC algorithm to get samples from their local posteriors. Then they'll communicate these samples to each other. And at inference time, it will basically compute the local predictive distributions and then use the product formula I had above in order to compute the global predictive distribution. And that will be the final predictions that it makes. So for classification, that product formula can be applied directly because y is a discrete variable. It just has different classes. One insight that this product formula gives is that if client I has little data, then the predictive distribution for that client will coincide with the prior distribution, which I've written as p of y given x. It's what appears in the denominator. And the factor that it contributes to the product effectively becomes 1, which means that if a client has very little data and it's very uncertain, then it doesn't contribute to the global prediction much. And for regression, we have to change this formula a little bit because y is continuous, we can't directly apply the product. Instead, we approximate all of the factors as Gaussian distributions with some mean and variance that we can estimate. And the aggregation results in an overall prediction that's also Gaussian. So the formulas here aren't too important, but I'd just like to highlight that we have this pattern again where if the prior is uncertain, which we generally want, this overall prediction basically becomes a weighted sum of the individual predictions, where the weights are given by the uncertainty that each client has. So if a client is very uncertain, then it contributes less to the overall predictions. So in terms of experiments, we evaluated on multiple classification data sets and found that within a single round of communication, our method performed best. And similarly for regression, so within a single round of communication compared to the baselines, our method generally performs best. And another set of experiments I wanted to go over was using data heterogeneity. So here, we basically set up a data set where we can control the amount of heterogeneity present with a setting of 1. Each client just got completely different data distributions. In this case, completely distinct class labels. And a heterogeneity of 0 meant that all of the clients had an identical distribution. So in this setting, as we increased the amount of heterogeneity, our method performed more gracefully in more heterogeneous settings than the baselines. And that's because each client has a better understanding of its uncertainty. So in conclusion, this method gives an alternate method for training federated learning models. It's more communication efficient and it performs better in heterogeneous settings. Yeah, thank you.
Then Mohsin, open to floor. Any question you want to ask Mohsin about this paper? Okay, Mohsin, let me ask you one. Is it your method still work for, do you handle the non-IDD data or you just handle the IDD data?
Yeah, so these experiments with the heterogeneity were done with non-IID data. So for a heterogeneity setting above 1,
Okay.
that the data distributions between clients are different. And in fact, the product formula that I showed earlier, this one, this result doesn't need every client distribution to be identical. So they can be different so long as they're independent.
Okay. Okay, thanks, Mohsin. Yep.
Yeah, welcome.
Okay, so we go to our next paper. The paper name is vertical federated knowledge transfer via the presentation distillation. We invite the presenter. I think it's called Chongru Wang. Is it Chongru Wang? Okay, thank you. Yeah.
Can you hear me?
Yes.
And can you see my shared screen?
Yes, yes.
Thanks. Hello, everyone. I'm Chongru Huang, a first-year PhD student from Peking University. Today, I want to present a new vertical federated knowledge transfer method via representation distillation. Thanks to Le Wang and Xiao Han, co-authors of the paper, for their support. First, let's talk about the motivation of our work. Current vertical federated learning methods are highly dependent on how many overlapping samples exist between the two parties. Most vertical federated learning collaborations are conducted by involving at least one giant data holder with abundant data. However, this makes the giant data holder occupy a dominant position over other small data holders in vertical federated learning, which could lead to unfair trade and data monopoly. Besides, most vertical federated learning models focus on shared samples and often neglect to improve the learning performance of local samples from different parties. As shown in these figures, existing models usually use shared samples to complete a specific task, and this part of the samples, called the local samples, are not fully utilized. This means that many existing vertical federated learning models are highly task-dependent, and each party that provides samples cannot use its own local samples for independent task process. To overcome these defects and extend the applications scenarios, a vertical federated process is urgently needed to benefit the ordinary data holders. Our research has three main objectives. First, we want to design a new method that can transfer knowledge from multi-party shared samples for better local learning. Second, we hope that the new method will be able to learn new representations, helping ordinary data holders to better conduct local learning. Third, on this basis, each party is able to perform different and independent tasks via the representations it has learned. For the sake of illustration, we have made the following definition. Test party has a set of samples with features and a test label to predict, and data party has a set of samples with features. For client A, it's the test party when it's running its own tests, and the client B, who is providing data to client A, is the data party, and vice versa. Therefore, for the sake of simplicity, we will use only one test party and one data party to describe the method. Let's move on to the overview of proposed framework. Both the test party and the data party divide their data into private samples and shared samples. Sharing samples does not mean that each party has direct access to the other state. Shared samples of both parties will be input into a secure vertical federated learning model for federated representation learning. The federated representation is shown in this part of the figure. We then distill the local representation of the test party state. For private samples and shared samples, we distill them with different loss functions. In this step, we can get enriched features of original data. Then we align the original data with enriched features to get a new enriched representation. Eventually, we can use machine learning or deep learning models to perform different tasks of new enriched representation. We simplify the process into the following 3 steps. In step 1, we use the vertical federated algorithm called Federated Singular Vector Decomposition. In fact, the choice of vertical federated learning model in this step is arbitrary. We use this quotient to recover the federated latent representation. The process is secure and almost lossless. In step 2, we define a new loose term called the distillation loose. The first half comes from the hidden encode of the autoencoder, and the second half is the federated latent representation from step 1. This is complete loose function. The non-shared part of the local samples, we only use the reconstruction loose, while for the shared part, we add a knowledge distillation loose. This new loose term ensures that the features generated after distillation are as close as possible to the original shared samples. We use 5 different types of datasets to test the proposed framework. The first 2 are the main datasets. The method we proposed compare with the following 2 methods. Local leverages only the test party's local features for training the test-specific model. 4 assumes that all the features of test party samples are used to train the machine learning model. Therefore, the result of the local can be used at lower bound, and the result of 4 can be used as upper bound. Next, we will show the results of the method in various experiments. As you can see, our mechanism can obtain good performance on these 2 datasets. By varying the number of features in the task and the data party, results show that our method can consistently outperform the local, which verifies the generalizable effectiveness of our vertical knowledge transfer mechanism. Besides, when the feature number increases, our mechanism's accuracy gradually goes up. It's also known from the figure that our mechanism performs well by changing the number of shared samples between the test party and the data party. This is because the knowledge transfer source is the shared samples. The more shared samples exist, the better knowledge transfer performs. As shown in these 2 figures, with the increase of data parties, the performance of our mechanism grows obviously. This means that our mechanism can obtain effective information from multiple data parties to make up for the shortcomings of insufficient data volume or fewer features. We also tested other 3 datasets. Our mechanism consistently outperformed local, verifying the generalized effectiveness of our knowledge transfer method in various datasets. Moreover, we check how our mechanism can facilitate inductive learning. Inductive learning requires new samples with different distributions that were not used to train the encoder. Results demonstrate that our mechanism can achieve better performance than local for both IID and non-IID new samples. This reveals the good generalizability of our mechanism's enriched representations. Here we change such parameters to verify the robustness of our method. We can see that our mechanism can get resultant accuracy when the structure of autoencoder is modified. And this figure plots the prediction accuracy when applying different machine learning algorithms to train the test-specific prediction model. And this verifies that our mechanism can consistently outperform local. In order to further verify the effectiveness of our mechanism on knowledge transfer, we compare the changes in prediction accuracy before and after using our newly designed loose function. This prediction accuracy was significantly improved with the use of novel loose component for knowledge transfer, and our mechanism always performs better than the mechanism without knowledge transfer with the features of test party change. This means that adding the novel loose term into the loose function of autoencoder as a penalty can provide a more reasonable auxiliary conversion means for knowledge transfer. And this experiment showed that the computation time of our mechanism is linearly proportional to the number of data parties and the number of shared samples. This linear relationship indicates the good scalability of our mechanism. And finally, we summarize our work. This work is a first to explore how vertical knowledge transfer from shared samples to local samples of each party can be achieved in a task-independent manner. We propose a new federated representation distillation autoencoder framework that can transfer knowledge from shared samples to local samples. And experiments on several real datasets verify the effectiveness of this mechanism in knowledge transfer and the generalizability of our enriched representations of local samples. Thanks for listening.
Okay. Thank Chongru. Any question? Audience, you got any question for Chongru? I think no question. Thank Chongru. I think you still have question. You can type in the chat box. I think Chongru will try to answer you. Thank Chongru.
Thanks. Thanks, Chu.
So let us go to the next paper. The Federated learning with the GAN-based data synthesis for non-IDD client. They invite speaker Zhijian Li. Yeah.
Yeah, can you see my slides?
Yes, yes.
Okay, thank you, Chairman. I'm Li Zhijian. I'm the newest PhD student from Hong Kong University. I'm going to share a paper, Federated learning with GAN-based data synthesis for non-IDD clients. As we all know, Federated learning has achieved significant performance in collaborative learning without sharing the local data. However, non-IDD problems still constrains the performance of the Federated learning. The data heterogeneity among clients will easily lead to the local model divergence, which will degrade the performance of Federated learning after aggregation. And actually, there has been several solutions focusing on optimizing the local training or the server aggregation procedures, but the performance improvement of them are still very limited. Therefore, we propose to address the non-IDD issues from another aspect. Each client will share the synthetic data with others to alleviate highly skilled data distribution. Specifically, when we use the GAN to generate the synthetic data, we adopt the WGAN GP, which will include the gradient penalty into the WGAN to stabilize the GAN training. And this simple but effective architecture can be deployed to each client and compatible with both supervised and semi-supervised settings. To protect the privacy of the clients and the synthetic data, we also introduced the ipso delta differential privacy for the GAN training. According to this work, we can easily compute the Gaussian noise according to the ipso delta setting, sample probability, and the batch number in each round. And then we can inject this Gaussian noise into the gradients of the discriminator. And according to the post property of the differential privacy, we can the generator also satisfy the differential privacy. Please note that the synthetic data is still unlabeled because we adopt the unsupervised GAN for the semi-supervised setting, right? So we propose a pseudo labeling mechanism for the synthetic data. Only the label whose prediction probability is larger than a threshold will be regarded as the confident pseudo labels. We will utilize the local model WJ to assign the pseudo labels for the synthetic data from the client J. Both of them come from the same client because they are more confident. And with such a pseudo labeling mechanism, we can filter and obtain the high quality synthetic data with the confident pseudo labels. And then let's go further to our framework. Before the federated learning begins, we need to construct the global synthetic data set. Each client will be trained again and use it to generate the synthetic data and upload the synthetic data to the server. The server will make an aggregation for all the synthetic data to construct the global synthetic data set. This global synthetic data set will be shared with all the clients, and so that all clients can obtain a lot of unseen class data during the local training, which can help us to alleviate the NID data distribution. So please know that this global synthetic data set will be kept fixed during the variation learning process, and only the serial labels of them will be updated in each round. So and then after the global synthetic data set construction, the variation learning process begins. So each client will download in each round, each client will download the global model and the updated serial labels from the server, and then the clients use the real data and the synthetic data to update the local models as usual. And then these local models will be uploaded to the server, with the stronger local models, the server will utilize them to update the serial labels again. Because with the stronger local models can help us to generate the more confident serial labels for the synthetic data set, which can help us to improve the performance. So as usual, the server will take an aggregation for the local models to construct the global model, right? And then with the synthetic data set in the server of course can utilize it to update the global model directly in the server, which will further improve the performance. So with the above explanations, there is an interplay between the local models and the pseudo labels. The uploaded stronger local models can help us to generate more confident pseudo labels. And then these pseudo labels with the synthetic data set can in turn help to train the local models in the client side. So there's an interplay between them, which can help us to alleviate the NID issue and improve the performance. So let's go further to the experiments. The first experiment is the Federated supervised learning. We compare the SDFL with the baselines in different NID settings in ANIS, special ANIS, CIVA-10, SVHN, as well as the COVID-19 data sets. From the results, we can see that SDFL outperforms all the baselines by a large margin in all the data sets. And then is still working in the high data skewness distribution, but the baseline cannot work in such an extreme data distribution cases. So an interesting thing is that SDFL even outperforms the variety averaging with the ID settings in the COVID-19 data set. So this is because the game can generate a lot of high quality set data to enlarge the local data sets, which can improve the performance. The second experiment is about the Federated semi-supervised learning. The results also show that SDFL outperforms the baselines by a large margin in terms of the overall performance as well as the convergence rate. Personally, that this is the semi-supervised setting. And the final experiment is about the comparison with the supervised game. Supervised ACW game GT is the supervised game, which can generate synthetic data with the pseudo labels. So from results, we can see that SDFL with WGame GP performs better in terms of the FID scores and the accuracy. FID scores is the metrics to quantify the quality of the synthetic data. So this results show that WGame GP can provide high quality synthetic data, and our proposed framework SDFL can provide more confident pseudo labels for the synthetic data. So so the WGame GP plus SDFL can provide can achieve a very significant performance compared with the supervised game. Yeah. So let's make a conclusion. We propose a novel framework namely SDFL, which utilize the game to generate synthetic data to solve the NID issue. We also propose a pseudo labeling mechanism to extend the SDFL application to the semi-supervised setting. So of course, there's some problems. Right now, when training a game still requires a lot of computational costs. So in the future, we need to develop a more effective game for the federated learning framework. Maybe we can develop the other algorithms for the data synthesis instead of just training the generator or the discriminator, which requires a lot of computational cost. At the end, we also need to develop the better privacy protection algorithms. In this work, we just utilize the differential privacy. Maybe in the future we can just develop the better privacy protection algorithm. So that's all my presentation. Thank you.
Thanks, Zijian. Any question, audience? You can ask Zijian.
Yeah.
Zijian, I got one question. I think you say you're using the GAN to generate the synthetic data, then you're using differential privacy to protect the data. So actually, how do you ensure your privacy budget, right, when using DP, enough to cater the synthetic data you generated?
Actually, in the paper, I also just conduct the abrasion study about the differential privacy, how to affect the performance. Yeah, but because of the time problem, I didn't show here, post here.
Okay.
Yeah. Actually, because if you just inject the more gradients or more Gaussian noise, the different privacy protection into the models, of course, the quality of the synthetic data will be degraded. So yeah, it's very normal.
Okay. Yeah. Okay. Thank you.
Thank you.
Okay. Thanks, Zijian. So we can go to our next paper. Our next paper is called Secure Federated Analytics for Set Intersection. Let's invite the Amit to do presentation. Amit, you there? You can share.
Yes.
Your slide.
Yep. Let me share my screen. So do you see my screen?
Yes.
Okay. So hi everyone. I'm gonna present our work, which is Secure Federated Analytics for Set Intersection. This work in collaboration with Yahya Isa and Salman Avestamir. So we start by giving a quick introduction about federated analytics. So basically, federated analytics is more about applying analytical functions on users' private data without any data collection. In fact, there are several applications where federated analytics take place. So for example, it can be used in heavy hitter, where it's used for learning trendy out of dictionary words to improve the autocomplete features in smart keyboards. It can also be used for accuracy evaluation in federated learning, and it can also be used for generating heat maps. In general, analytical queries can be classified broadly into three main categories. The first category is more about statistical queries, which include statistics such as mean, median, mode, histogram, and heat maps. The other category is hierarchical queries, which is represented by clustering and dimensionality reduction. And finally, set property queries, which includes set unions and set intersection. The analytical problem we are considering in this work is set intersections. Specifically, we are considering a variant of set intersection. We call it K private set intersection. To give a high-level discussion about K private set intersection, we consider this example where we have a server. We have four parties, party 1 to party 4, and each one of these parties has its own private dataset SI. The objective here, we want the server to only learn the elements that appear in at least, for example, two of the sets, or 3 of the sets, or more generally, in at least K sets out of all the sets. In addition to that, we want the server to only learn the elements in the intersection and learn nothing more than that. So to formalize the problem, so again, we have a server. We have n parties. Each one of these parties has its own private data set. And here, each data point is represented by identifier. We can think of identifier something like user ID, and there is a value associated with this identifier. This could be transactions, and we'll give more examples about that in the upcoming slides. Here we assume that the server has only access to a set of identifiers, so the server doesn't have any values. And we assume that this set of identifiers are shared across all the end parties. So the questions that the server trying to find an answer for it here is, does a given identifier U show up in at least K out of the n parties coupled with the same value? So basically, there are several applications where KBSI can be used. So we can think of having an application like double feeling insurance claim. So basically, if we have a federal agency, and this federal agency has a set of suspect ID, and the federal agency wants to know the individuals who double feeling the same insurance claim in at least K insurance company. And in this setting, the insurance company are not willing to share any private information about their clients. Another application could be the email spam detection, where we have, for example, an online marketplace like Amazon. And this online marketplace has some suspicious seller email IDs. And this online marketplace wants to know the sellers who send the same spam emails to at least K of the buyers. So the state-of-the-art protocol for a multi-party BSI don't lend themselves directly to our problem. So basically, there is some works which consider pseudo-random permutation of the data in the space. The main limitation of this approach, when we think of using it for our problem, which is KBSI, is that the server, by using random permutation, will learn more statistical information about the parties' data. For example, the server can learn the number of points that can be found in the intersection between two parties, even though this wasn't the original goal. Another method that is used in the literature for multi-party BSI is using oblivious transfer. And again, using such approach in solving our problem is not direct, because the server in our setting has access to a partial data with just identifier. And using such techniques requires the server has identifier and value. And there is another work in the literature called threshold BSI, where the main difference between this line of work and our problem is that in threshold BSI, the threshold is on the number of elements that are shared across all the parties, while in KBSI, the threshold is on the number of parties that share a particular element. So basically here, we are not focusing on the number of such elements in the sets. So to solve the problem of KBSI, we proposed an algorithm, we call it here Federated KBSI, where the key idea is to design a programmable random distributed linear map, which allow users to jointly encode their data such that the data of the users can keep private, so the privacy is guaranteed. And second thing here, any linear aggregation of the encoded data across any K users gives 0 if and only if they have the same value. I will look through some basic parts of our algorithm or the details in the paper. So in the first step, the server can select K users out of n users to test their values if they are the same or no. And the value here again could be like a mail body associated with a given address. In the second step, something called secure function computation is implemented so that the server can test the values of the key users. So how our proposed secure function computation work? So we give an example for the encoding process for an identifier U. So basically, all the key users will jointly encode their values using this equation here, where Y represent the encoded data from the key parties, V here represent the vector of values for a given identifier from the key users. And here is the random encoding matrix, which jointly designed by the key users, which can be used to protect the values of the users. So if you think of having one party, so party I basically encode its value vi using the encoding matrix z, which results in an encoded vector of size k-1, which we call it y here. The details of generating the matrix Z is given in the paper, but the key point I would like to highlight here is the key properties of the matrix Z. So basically, the matrix Z is drawn uniformly at random, such that it has a full column rank. And the second property for this matrix is multiplying a row vector V by the matrix Z give us 0 if and only if all the key values are the same. In other words, V just a scaled version of the all ones vector. Otherwise, it gives a random vector. So from this design, this ensures the privacy of the parties' data, but still not secures the identity of the parties. And one remedy for that is to use secure aggregation, which rely on additive masks. So at the server, the decoding process is easy. So the server can simply add the rows of the matrix Y, which mathematically can be represented by multiplying by a row vector of all ones from the left. And by using the properties of the matrix Z, the server can get all vector of 0 if all the key values are the same. And otherwise, it gives a random vector, which ensures the privacy of the user's data. For our empirical evaluation, in this figure, we show the run time of our algorithm for the different component of the algorithm. And in x-axis, we vary the threshold k. And this figure is for the setting of having 10 parties. So as a key observation here, we can see our FED-KBSI is giving low running time when the threshold k is getting closer to n, which is 10 in this case, or 1. And the second observation is we can see that the total running time is dominated by the encoding phase. And also the maximum running time is reached when k get closer to n/2, which is 5. So in summary, we have proposed our FED-KBSI, which allow us to evaluate the k-set intersection for a given set of identifier at the server. We propose an algorithm which is ensure information theoretic privacy for the users. And one drawback of the proposed algorithm, which is the communication complexity, which increase with increasing the number of users. And this is the references, and thank you.
Thanks, Ahmed. Any question for Ahmed? Ahmed, I got some question. In your PSI, right? Do you consider malicious setting or semi-honest setting?
Yeah, so this is a semi-honest setting where we assume users can collude with each other while the server is honest and do no colluding with the users. So
Yeah.
it is honest but curious setting.
Okay. Another question I want to ask: do you handle when you do PSI? Do you handle kind of the imbalanced data set? Let's say one site got maybe just few data set, another site got million data set. How do you do this kind of case? Do you consider case?
Yeah, so basically for our algorithm, we assume if all users have, for example, the data set, we do a kind of iteration. So we go over each data points. We apply our algorithm for each identifier in each round. So yeah, so basically the algorithm is applied on every data point. So if the data is imbalanced, dummy data can be used. So, but at the end of the day, users will use the same set of identifier as the server, which means that the size of the data set at the users at the end will be the same if they restrict themselves to the same set of identifiers at the server.
Okay. Yeah. Okay. Thanks, Amit.
Yeah, thanks.
So our next paper is called sketch to skip and select communication efficient federated learning using locality sensitive hashing. I wonder the presenter for this paper is here.
Yes, I'm here. I'm here.
Hi.
Hello, how are you?
Hey,
let
good,
me share my screen. Okay.
Yep. Oh, yeah.
Okay. Okay, let me share my screen.
Yeah.
Okay, perhaps I will make it full screen. Okay, can you see my screen now?
Yes.
Okay, perfect. So hello everybody. My name is Georgios Kolaias. I'm going to talk about, let's say, two techniques using sketching for federated learning. And these are novel techniques. They use basically sketching for deciding whether to communicate and how to do client selection. We don't use basically, and this is the idea, we don't use sketching to produce the models that will be used in training. We use it for decision. Now, this is joint work with Theodoros Alonides and Sikyang Wong, and we all come from IBM Research. Now, so the basic idea is to define a predicate, a model proximity predicate based on sketching, and embed this predicate into the typical federated learning training procedure. And we use this to decide when to communicate, meaning when the predicate indicates that the model snapshot at the receiver side is closed, then we skip the communication. So this technique is called sketch to skip. And we also can decide which clients to participate when we do client selection. So we try basically to select clients that have models that are not close to each other. Again, based on this, let's say, proximity predicate. So this technique is called sketch to select. Related work, local updating methods, trading computation for communication. There is some work on heterogeneous data distributions, emphasizing the fixed number of local updates there, which can generate some problems. There is also some work on adaptive number of local updates and adapting the frequency of communication to the server. But our main emphasis is to exploit data similarities across clients and servers. So this is one thread. Another thread is about model compression, federated learning and model compression. There, the compression has been, let's say, implemented by means of sparsification, quantization, randomized data structure sketching. This is what we do, but we do not perform federated learning training based on compressed model parameters. We use it for deciding, as we will describe later. About the client selection methods, there are random selection methods. There is clustering of full models and then do selection on top of clustering. Now, we also use clustering, but we use clustering of sketch models for client selections, basically getting lower communication overhead. Let's now move to this model proximity predicate. It's a very, how to say, it's a very simple, let's say, primitive. We have a sender and a receiver. A sender has a vector, a receiver has another vector, and the sender wants to decide, okay, should I send my vector to the receiver or not? So the idea is to skip the communication if the two vectors are close to each other. So what does the sender do? He generates some random directions, some random vectors, organizes them into a projection matrix, and basically multiplies his vector with this projection matrix. So, and this is the sketch of his vector. Now the receiver does something similar using an identical projection matrix. So he also computes a sketch out of his vector B, and he sends the sketch to the sender. And then the sender computes the relative norm difference between the two sketches and decides whether to skip or not. So it is as simple as this. Basically, they compare some light white versions of the data. This is basically the idea. And the light white versions are basically the sketches. Now, how we use this inside the federated learning loop? The server sends a sketch of its global model to the client. So the vector is basically the flattened model. This is what the vector is all about. And what about the clients? The clients update their model parameters by performing local stochastic gradient steps in the sense of federated averaging, compare the updated model sketches with the global model sketch, send to the server the outcome of the comparison, and then the server says, okay, if all client models have not deviated much from the global server model, where the comparison is based on the sketching technique, then he decides to skip the uplink update, the aggregation, the downlink update, and the client selection step if one is at work at this particular round. And this is basically all this idea, the sketch to skip strategy, how to say, embedded in the federated learning loop with all the details, basically the decision at the server side whether to skip or not. And this sketch to skip has some interesting properties. It can be applied to both uplink and downlink directions. It is one comparison protocol. We just project and compare the projections. It is modular. Somebody can use different, let's say, sketching methods, sketching randomized ideas than what we do. Basically, we use locality sensitive hashing, but somebody could use other randomized projection ideas, perhaps more performant computationally. So it also has a potential for very high communication savings because, for example, if we take the sketching dimension, which is typically 100, and we have a model with hundreds of thousands of parameters, like in our experiments, then if we can skip, let's say, the communication, then the communication savings will be of the order of a few thousands. So this could be very dramatic. Now, in order to implement this, we don't need much in terms of computation. So low computation complexity, amortized cost of generating the projection matrix. We can generate it at the beginning of the rounds. And there is also the cost for sketching, which is basically a matrix vector multiplication in our implementation of the randomized data structure. With that said, let's go to the next technique, the second technique, the sketch to select. So what we do here is when we want to do random client selection, we do the following. All end clients sketch their flattened model parameters. They send them to the server. They send sketches of their models. And then the server clusters on top of those. Clusters sketches, does not cluster full models like other approaches. So after clustering, basically the server samples one vector per cluster. And clients for which their sketch vector was sampled are added to the new subset of selected clients. And this is how the client selection works on clustering, on top of clustering of sketched client models. And all this procedure is done at the server. So this is the algorithm. This is how this is organized, the sketch to select strategy. We use the Lloyd's algorithm for clustering our n vectors of k elements each, where k is the sketching dimension, into C clusters. And k means plus plus is used for initialization of the coordinates of our C centroids. Some overhead complexities, some computational complexities for the sketching, the randomized projection, I mean, for the Lloyd's algorithm, and some communication complexity for the uplink part of the sketches. So, having these two techniques in place, one is the sketch to skip. Okay, decide whether to communicate or not based on sketches, and then sketch to select. Okay, decide based on sketches how to cluster the clients and basically pick some of them, do the client selection. Now we put these two ideas together, sketch to skip and sketch to select. Sketch to skip, again, if local models are sufficiently different than the global server models, only then communicate. And sketch to select, basically sketching is done and then clustering is done on top of sketches. So we put these two ideas together and we have, let's say, the full sketch to skip and select federated learning algorithm, where there are places where we call sketch to skip for each communication round. And we also call sketch to select when it is one of these points in time when client selection is going to be, let's say, applied. So it happens every U, let's say, time steps, or every U rounds in this, let's say, notation. With that said, let's move now to the experimental setup. 3 data sets: original MNIST, fashion MNIST, CIFAR-10, 2 data distributions at different nodes. Case 1, where each data sample is randomly assigned to a node. In case 2, which is the non-IID case, where all the data samples in each node have the same label. So non-IID case, the harder case. 2 models, fully connected neural networks for the MNISTs, and convolutional neural networks for CIFAR-10. Training and control parameters we use: static learning rate for MNISTs, a static learning rate for CIFAR-10, number of communication rounds, number of clients that we simulate, number of local steps, number of selected clients, how often we do this client selection, mini batch size. Sketching dimension is 100 for the skip part, 10 for the selection part, and the comparison baseline is always federated averaging for the same values as the ones that we do. The metrics: we collect downlink and uplink communication volumes during training, and also we collect the accuracy values at the end. Now, X refers here to what we get with our method, Y to what we get with the comparison baseline. So we have a metric for the accuracy and a metric for the communication volume. So we have the accuracy increase or percent relative error for the accuracy, which means that if this thing is positive, then the accuracy is better. If this is negative, then the accuracy is degraded. And the percent ratio, or for the downlink and uplink communication volumes, to basically to compare, or overhead ratio. For example, a percent ratio like 20% means that we use 5 times less communication volume. So it's a good thing. The less, the better in this aspect. Now, in this figure at the bottom, on the left, you see overhead ratio for downlink, and on the right, you see overhead ratio for uplink, and both for versus accuracy increase, which is on the horizontal axis. Now, if we are to the right of 0 in both these two schemes, then we have no degradation of the accuracy, so we are good in accuracy. So the lower we are in these 2 plots, the better is, let's say, the communication volume savings that we have. So this is one part of the accuracy of the results, and the other is about the accuracy profiles. So we have 2 rows here. One row is for case 1 and of data distributions, and row 2 is about case 2, where basically we have this non-IID data distributions, where basically each node get, let's say, its own label. So try to keep all the labels together. So non-IID case, the bottom row. So we see how the classification accuracy evolves with the training. The red one is what we do. The blue one is what we get with federated average with random selection. We see that in the bottom row, we don't get all these bumps that exist in the random in the federated averaging with random selection. We are more stable. This is one thing. And the other thing, we also see that we have opportunities, and you see it at the middle figure of the top row, that we can exit basically some let's say local minima and get opportunities for doing something better. And this, let's say, trapping into local minima can happen in this federated averaging random selection algorithm, but we have the opportunity with this skipping things to avoid them. As a conclusion, combining our sketch to skip and sketch to select strategies in training, we can massively reduce downlink and uplink communication volumes by factors of order of 100. You saw the logarithmic scale in the vertical axis, or more with minor degradation or even increase if we go to the right of these plots that we saw, of the accuracy of the trained model. And also, in contrast to baselines, we can escape suboptimal descent paths, like the middle figure in the upper row in the previous slide, and can yield also smooth non-oscillatory accuracy profiles for non-IID data distribution, which corresponds to the plots we saw in the bottom row in the previous slide. So that's all from me. Thank you.
Thank Jorgos. Any question for Jorgos, or you can open your mic? Jorgos, we got one question in the chat box. You can read, or I can read out to audience.
Okay, since the server communicates the global model to the clients in each round, is there a need to sketch? Can the client compare the updated model with the global send at round start? No, basically, we also give the opportunity for evolving. So the client also does some computation, and at the end it does its client its sketching and basically the comparison.
Okay, thanks, Jorgos. Okay, thanks, Jorgos, for your presentation.
Thank you.
So we can go to our first paper called the semi-supervised cross-silo advertising with a partial knowledge transfer. Let's invite Wenjie Li. Wenjie Li, you can share your screen.
Okay, can you hear me?
Yes, we can.
Thank you. Oh, okay. I'm trying to show my screen. Just wait a minute. There's a little problem. Okay. Oh, I'm sorry. There's a little problem. I need to re-enter the conference. So maybe.
Or maybe I can ask the maybe you put to the next one. I can ask the okay, probably
yes,
you okay.
Yes. Sorry.
Yeah.
Sorry.
So I think we go to the next paper called the Federated long tail learning. Can I invite Zihan Cheng to present his paper?
Hi, can you hear me?
Yes.
Okay, so I'm stuck. So this is Zihan Chen. I'm a joint PhD student from Singapore University of Technology and Design and National University of Singapore. This is a joint work with Zhejiang University. It is a great honor to be here to introduce our latest work towards FL with long-tail data. It should be noted that this is a preliminary work and exploration on federated learning with distributed long-tail data. We try to give a comprehensive formulation and benchmarking for this topic, and also with some preliminary numerical results. We also highlight some challenges and also provide some potential research opportunities in this area at the last of this talk. FL has a broad range of applications in multiple areas such as healthcare, finance, and recommendation systems, and so on. So, but as everyone in this community know, the performance of federated learning training is affected and also constrained by the data heterogeneity, or it can be called real-world data distribution. Here we give a figure for visualization of the different data distributions. To be precise, we know that long-tail data can be regarded as a special case of the imbalanced data. So to avoid misunderstanding, here we regard imbalanced data in this work without typical long-tail characteristics. So to be more precise, I'll give a figure to demonstrate long-tail distribution. A few classes occupy most of the data. We can call it as a head class, and also most of classes only have really few samples. We call this class as tail class. So and the remaining classes we call it as a middle class. So long-tail data distribution, which is an extreme case of data heterogeneity and widely exists in the real-world data, and also has been investigated a lot in centralized scenarios, but it rarely explored in federated settings. So given the inherent challenges of the FL and the properties of FL federated settings, such as long ID data, and also the limited local data set size, so there will be some new challenges in this context. Here is a table for the performance of the current typical FL goals. We can see that in different classes, the many represent the head, the few represent the tail. So current FL methods varies a lot in different classes. So it is necessary to develop some specific method for this topic. Here is a detailed summary. We refer this task as federated long-tail learning with the abbreviation FL-LT. To the best of our knowledge, there are only a few works on this topic, so we want to give a pioneering investigation and envision some potential directions. I will choose the following points in the next few slides about the analysis, challenges, numerical results, and some future trends, and also as well as research opportunities. With regard to the formulation, we use a class-wise ratio of number of samples over the local data size in each client to denote the local data distribution. Similarly, we define the global data distribution based on the total number of images in each class among all the clients. Based on the two predefined distribution vectors, we can measure the imbalance factors from both local level and the global level, which can be calculated based on the maximum value and the minimum value of the data samples among all classes in the dataset. So this could be used to evaluate the imbalance level in both local and the global level. So considering the relationships and also the differences between the local and the global data distributions, and also recall that the local data distributions may exist in either local side or global side. So we categorize FL-LT tasks into the following three types. The first type is both the local and global data distribution follows the same long-tail distribution. And type 2, the global data distribution is LT, but the local data distributions may be diverse, not necessarily long-tail, could be balanced, imbalance, and long-tail. Type 3 is local data clients. They have long-tail data distributions, but the global data follows long-tail distribution. Long LT distribution can be a balanced or can be or imbalanced. To be clearer, all these three types can be found in real-world scenarios. For example, the medical image datasets in a local hospital from a big city might follow LT distributions, but the aggregated city-level dataset could be LT or long LT. So here is a visualization of the three aforementioned cases. deeper color represent more images in the corresponding classes. So this is the three cases we just mentioned. The tab 2 and tab 3 are more difficult. So we will focus on these two in the next few slides and also in the experiment part. Oh, sorry. In all three aforementioned cases, due to the similarities and the difference between the global and local distributions, the corresponding training targets could be different. In the first cases, as we mentioned, both local and global distribution are identical. So one single shared models could be applicable. However, for the remaining two cases, the local distribution and the global distribution are different. So one single shared global models is not applicable. So it is not appropriate to use the traditional Federated framework to tackle the training issues in such cases. So it is better to maintain multiple models in these cases. For example, the personalized FL frameworks. It has been discussed a lot in previous paper talks. So in the next few slides, I will show some benchmarking to discuss about the datasets and the methods. For long-tail datasets, there are two types. First types, we can use exponential distribution or the Pareto distribution to partition the traditional CIFAR-10 or ImageNet into a long-tail version. We can call it the CIFAR-10 LT or ImageNet LT, and also some real-world datasets, such as LHNAs or Google Landmarks. These are datasets with some inherent long-tail properties to stimulate some federated experiments. So we can use both ID and non-ID samplings on the LT or long-LT datasets based on your corresponding tasks. For the approaches, as we mentioned, in centralized scenarios, it has been investigated a lot, such as rebalancing or calibration or decoupling. For example, the rebalancing is has two types, reweighting or resampling. They are mainly focused on increase the importance of the tail class to get a better performance on tail classes. So for the next few slides, we'll provide some preliminary numerical results in order to review some insights. We choose 4 different methods in different topics: FedDef, FedProx. FedProx is widely used SOTA fidelity optimization methods for data heterogeneity, and also FedPer for personalized FL. As we discussed, it could be potential candidate, and CREF, the only one methods tackle fidelity data, but it should be noticed that the CREF is only aims to develop a single global model. So we carry out experiments on different settings sorted with difficulties level of the tasks in tab 2 and tab 3. We can see that the only one FedLT algo, the CREF, outperforms the traditional or conventional fidelity methods in almost all cases. But we can find an interesting point: the FedPer, a very simple personalized FL framework without any advanced technicals. The FedPer only maintains some personalized layers at the local, but it outperforms CREF in some very difficult settings, such as the global imbalance factor in as 100. So which indicates that the personalized FL framework can be a potential framework candidate in the fidelity tasks. So this is the last part. We provide some potential research opportunities for this topic. Just as mentioned previously, we can incorporate personalized FL ideas to learn a better LT oriented models. Also, we can develop some hierarchical FL architectures. For example, we can clustering the clients with same data patterns or distributions. Then in such hierarchical architecture, we can develop or learn personalized group level models to get a communication efficient algo. So the last two are reproposing some existing fidelity optimization methods or data set construction or sampling methods in FedLT context. So this is a conclusion part. So it should be noted that it is a preliminary exploration on this topic, as this is a very new topic. So we envision some possible directions and hope more research can be carried out in this topic. That's it. If you have some questions or some collaborations with us, you can email me or email Professor Zhou Liu from Zhejiang University. Yeah, the details can be found in our paper. Yeah, that's it. Any questions?
Thanks, Zihan. Any question for Zihan? Okay, thanks, Zihan.
Okay.
Okay.
Okay, thank you.
Thanks. So we go to our today's session last paper. The paper title is Semi-Supervised Cross-Silo Advertising with Partial Knowledge Transfer. Wenjie Li, hand over to you. You can share your slide.
Okay, I'm preparing. Can you hear my voice and see my screen?
Yes.
Okay, thank you. Hello, everyone. I'm Wenjie Li from Tsinghua University. I'm very glad today to introduce our work to you. The title of our paper is Semi-Supervised Cross-Silo Advertising with Partial Knowledge Transfer. It is a joint work with many colleagues in Tencent. And I will give my talk following this agenda. It is divided into 4 parts. The first part is about the background knowledge about display advertising. Display advertising is one of the most important business for internet companies to make profits. So it is very important. Let's take WeChat as an example. You can see the 2 ad slots in this figure. But how does the platform decide which how does the platform decide which ad to display? It is actually supported by the back-end real-time bidding advertising system. Inside the system, there are 2 main entities. That is the publisher, which is usually a media platform, and the second one is the advertiser, which is usually a merchant who want to show ads. So the core display mechanism is that each advertiser will bid for every ad request from the user to get the chance to display their advertisement in the platform of the publisher. So once the user sends an ad request to the publisher will organize an auction process to organize all the advertisers to take part in the auction. Once the auction is finished, only the winner of the auction can get the chance to display its ad. So the advertiser needs to bid at real time for each ad request and based on the user value, based on user interest. So the core part here is that they both need a more precise user preference model to estimate whether the user will click the ad or whether the user will reject their products after the click action. So a precise user preference modeling such as click-through estimation or conversion rate estimation can help boost the advertiser and the publisher to make profits. Let's take an example about a game company and other platforms such as WeChat. The game company knows more deep interest about the user, such as his game time, his game activities, and money consumption. But the ad platform knows more broad interest about the user for all kinds of products, brands, or contents. So these 2 key entities provides complementary information about one user. If we can collect all the data together, we can build more precise preference model, but it is not feasible in practical because of data security issues. So that's where vertical learning can help advertising systems. The first point is that it can utilize the complementary data information. And second, that is it's because of data security problems. But our motivation is that the traditional vertical federated learning is not that practical for advertising systems because of 2 main reasons. The first reason is that during the training process, only limited amount of effective data samples are available. That is, the overlapped samples in this figure, the overlapped samples with timely and clean labels in advertising system are much fewer than the ones without label. So there are lots of unlabeled data wasted in traditional vertical federated learning, but they may help us to build a robust model. And the second challenge is that once a federated model is finished, once the federated training is finished, the federated model, such as the split neural network, it consists of parts held by different parties. So when we need to conduct online serving, there's a high inference cost because we need an industry-ready cross-silo inference system in real-time advertising systems. And the system requirements such as real-time throughput and high throughput respondents is very hard to meet. So to tackle these two issues, we propose a framework named VFED SSD, semi-supervised split distillation, to tackle these two issues. Our framework is two-staged. The first stage is pre-training by utilizing the massive unlabeled data available in the advertising system. We propose a self-supervised learning task named MPD, matched pair detection, for this pre-training stage. And it utilizes the intrinsic property of alignment and multi-view of vertical partition tabular data. At the second stage, we use knowledge distillation to transfer knowledge from federated model to a local model to avoid the high cost of federated inference. That is based on two observations. The first is that in the main setting of two-party federated learning, only the active party matters because only the active party need to conduct online serving to make predictions. And the second, that we find that we can conduct incomplete distillation with only part of the input data available with acceptable performance. We can see the latter in our experiment part. So before we dive into details about our method, we should firstly clarify our setting. In this paper, we focus on the setting that is two-party vertical federated learning, which uses a split neural network as a backbone model. Because in the advertising system, usually we have two entities, that's the advertiser and the publisher. So we focus on this setting. And second, in advertising system, the data is usually aligned using the user ID. So our setting is similar to the vertical federated recommendation system, but the attributes is not limited to items. And in this paper, we focus on two advertising tasks, that is CTR estimation and the CVR estimation. So in the typical two-party vertical split neural network, there are some basic notations. That is the party who holds the label, we call it the active party, and the one who doesn't have the label, we call it the passive party. We denote it as the B. Each party can hold the bottom model, and only the active party have a top model to make the final predictions. And we use the letter F and G to denote the bottom model and the top model respectively. Specifically, in our paper, we use the data are all tabular data. So we first need to concat all the embedding vectors of each field into a long vector, and we call it the total embedded vector. We denote it as Z or X in following slides. So let's turn to the first part of our method, that is self-supervised pre-training. We have a very simple and intuitive idea to learn a binary classifier that's capable to distinguish whether the input attributes from two parties are matched. Let's take an example. Here are 5 federated samples, but only 2 of them are aligned. That is, the left part and the right part belong to the same user. For the other 3 samples, the left part and the right part are mismatched. We randomly permuted its order to conduct negative samples for our classifier. Although it seems very simple, but it is an advantage in implementation because the collaboration cost is very. We have a high collaboration cost in the data pre-processing and the training stage in vertical federated learning. So in our implementation of the pre-training task, the only thing we need to do is just to generate a random permutation matrix and multiply it to our batch of samples on the active party. We do not need the passive party to do any additional operations. And our loss is just the logistic regression, the batch-wise loss regression loss. But with such simple intuitive idea, we can get a good theoretical guarantee. That is, the prediction score of the classification top model in the pre-training stage. It is just an estimation of the lower bound of the pairwise mutual information about the mutual information between the inputs from two parts of the sample. So the number k here is just the number of negative samples we randomly generated. When the k equals 1, our classifier is just exactly the estimator of pairwise mutual information value. That makes a good guarantee for the quality of learned representation of our method. Then once the pre-training is finished, only the bottom model part, which are used to extract representations, will be fine-tuned and reused in the distillation process. And in the distillation process, we just train a student model, which is almost identical to original local model. That is only the input fields of the active party is available. And our training loss is just intuitive and effective. It is a combination of the original cross-entropy loss between the ground truth label and the prediction of the student. And we regularize the student model to provide a prediction score as close to the federated teacher score. So the students here can still maintain partial federated knowledge, but not all of them. We design this fashion of distillation because the student model can free from federated inference, but it can still performs better than raw local models, which we can still get benefit from the federation. Although at the inference stage, we do not need a federation. So there is an intrinsic disadvantage here that in the distillation process, the fields of the passive party is missed. The data missing is inevitable because we want to avoid the federated inference, but it is acceptable for our goal because we want to get a better local model compared to a non-federation. Because if we want to conduct full federated inference, it is almost infeasible in some industry cases. So I call it acceptable. And besides, we can further enhance the performance of the student model by explicitly learning the distribution about the probability of data from party B conditioned on data A. So that is also described in our future work. Finally, let's introduce our experimental results. We conducted the results on 3 federated data sets. The 2 are collected from real industry scenarios, that is come from Tencent game and Tencent advertising and its social media platforms. And the first and the one public data set is simulated from a very famous benchmark, CTR benchmark data set, that is CRE2. So let's firstly say the effectiveness about self-supervised learning. In this setting, we compare our presentation task with the raw vertical federated baseline. At this setting, our method achieves significant performance improvement. And with the intuitive pre-training, baseline named the self-training, we can find that although a very intuitive method can utilize the unlabeled data, but our MPD task can leverage the unlabeled data more efficiently. It can get additional AUC improvements compared with the baseline methods. And besides, we can see in the left figure that during the training process, the red figure is our method, and the blue figure or the blue line is the baseline vertical failure learning. Our method can converge fast and achieve the best performance at very early training stage. That is nearly 8 epochs here. But our total epoch is near 14 epochs. So second, let's see the validity of our split up distillation equipped with the pre-training. First, let's see the advantage of vertical distillation compared to local model. On 3 data sets, we can see that the distilled student model are better than the local models. And when we additionally equip the pre-training to the distillation process, we can get a higher performance lift on AUC that is very significantly in the CTR and the serial task, because in reality, 1% of AUC improvement is called to be significant to do online experiments. So our method shows the effectiveness on both the industrial dataset and the public academia dataset. Now let's give a summary to our work. We studied the problem of vertical federated learning in the setting of display advertising that is not well studied. And we take the first attempt to develop a self-supervised task for vertical federated learning. And we can pose a good theoretical property. And second, we develop a transfer schema, split KD, to meet the stricter system restrictions in advertising system. And our experiments show that both the MPD and the split distillation performs well on both data sets. That's all my presentation. Thank you. Do you have any questions about this work?
Yeah. Any question for Wenjie?
Hello, Wenjie. May I ask one question? And have you measured the relevance between the A fields and B fields data features? Actually, I'm worried about if they are quite relevant, so definitely you can use distillations to transfer knowledges.
Yeah, it's a very important question. We can in our paper, in the first part of our experiment part in our paper, we show the validity of the data fields of the passive party, and we can see that the federated model, all federated models are better than local models. And that means that the additional features added by the passive party can make a positive contribution to the learning process. So the basic vertical federated learning can perform well than the local model. Otherwise, it will drop, right? And in the distillation process, we can see that on different data sets, the raw improvement of the distillation method is quite different, and we can see the improvement of the raw split KD can be seen as a hint of the value of the fields additionally added in the passive party. For example, in the game social data set, the improvement of distillation is much higher than the one in the game ad dataset. So we can have a sense that the data fields, the passive data fields in the second dataset is better than the one in the first dataset.
Okay.
Thanks. Thanks.
Okay. Thanks, Wenjie. Okay. Thanks.
Thanks for the question.
So I hand over to Professor Yi for another next session of closing remark. Thanks.
Thank you, Dr. Tiu, for hosting this paper session. Okay, so we come to the last item of today's workshop, which is the award ceremony. Let me share my screen. Okay, so since we already had an award ceremony for people who are attending the workshop in person. So today we are going to give out the remaining awards to our recipients who are joining us today online. Okay, so the first award goes to this paper entitled MetaFed, Federated Learning Among Federations with the Cyclical Knowledge Distillation for Personalized Healthcare. The authors are Yiqiang Chen, Wang Lu, Xin Qin, Jindong Wang, and Xing Xie. Is any of the recipients here? Professor Chen, are you here?
Yes.
Yes, Professor Chen, yeah. Please, congratulations on receiving the awards. Yeah.
Okay,
thank you for contributing such wonderful work to our workshop. So this is the Innovation Awards for your paper. Would you like to say a few words?
Yes, thanks, Chair, and I think thanks to all the award committee. I would thank all of you from the bottom of my heart from the honor that our paper is selected for the FL-IJCAI'22 Innovation Award. For researchers, I think it's a formation of our professional study. It's also an incentive and encouragement to our study, which enable us to continuous research on innovation method and systems and applications in federated learning, especially focus on how to build ecosystems in this area. Moreover, I would like to thank my team, collaborators, and partner hospitals for the development of federated learning in healthcare. I believe we will do better in the future. In the end, I also would thank you, everyone now here, because it's very late in Beijing time. Because of the tireless effort of everyone here, I think federated learning has continued to grow. Thank you very much.
Thank you very much, Professor Chen, and congratulations again. Thank you.
Okay, thank you.
And the next innovation award goes to the paper entitled Cluster-Driven Personalized Federated Learning for Natural Gas Load Forecasting, authored by Shu Baozhao, Jia Liu, Guoliang Ma, Jie Yang, Di Liu, and Zheng Xiangli. Dr. Li, are you around?
Yeah, thanks, Prof.
Would you like to say a few words for receiving the award?
Yeah, we are very, very grateful to receive this innovation award. Yeah, thanks again to the FL-IJCAI organizers and participants for such a very successful and informative workshop. As introduced, ENN Group is one of the biggest natural gas distributors in China, and the work presented in this paper is very essential to our business and for the modern energy systems. Besides that, we are exploring other digital intelligence applications such as machinery predictive maintenance using vibration sensors, safety and quality inspections using computer visions and other special devices. Yeah, at various scenarios. Since 2019, we consistently investigate personalized federated learnings with incentive mechanisms for establish the collaborative digital and intelligence ecosystems for industry in internet across multiple industry domains, especially in energy domains. We have a large amount of real-world data and application scenarios and our industry experience to pre-processing the data and establish the test beds across different cities for novel technologies. So I would like to take this opportunity to call for collaborations with world-class researchers in this workshop. Yeah, thanks again. Thanks again to the chair.
Yeah, thank you, Dr. Li, for contributing such wonderful work to our workshop. Congratulations again for receiving the award. Okay,
thanks.
So other than the award ceremony, so that this actually concludes our workshop today. We would like to take this opportunity to thank everyone for joining our workshop. And the last bit of administrative matter goes to this announcement here, because we have another workshop coming up which is in conjunction with New RIPS 2022. This will take place in December in New Orleans, USA. The paper submission deadline is 15th of September, and the workshop will take place in December, on December the 2nd. Okay, so all of you are very much welcome to contribute works to this workshop. Okay. Okay, thank you everyone for sticking with us to the end of this workshop. I hope you have enjoyed the program. We have recorded the workshop so that later on we can put it online somewhere and share the link on our workshop website. So in case anyone wants to review the talks, you can find the video there. Thank you again and have a good evening. Bye-bye.